at the Institute of Geophysics. This is a university's laboratory, and well, if he's not going to, I will invite you all to assist next week. They have their 25th anniversary, I believe, which is going to take place. The ceremony and the sessions are going to take place in this same auditorium. He's also editor of the Revista Mexicana de Ciencias Geológicas. He has published 57 articles in SII journals. He has 1,870 citations, H factor 23. He has supervised 5 bachelor theses, 12 masters, and 5 PhD students. And he's going to be our first speaker, so go ahead, please.
Well, good morning. The first talk is something about age dating, and Humboldt, Alexander von Humboldt, he published a lot of things, but one of the most important is his Cosmos book, and this was a book with originally more than 1,000 pages. There is a reprint version edited by Hans Magnus Enzensberger, which came out in 2004, which is basically a reprint. And at least 30% of the text in this book is dealing with geology. So you can see here, for instance, at page 765, he is talking about the volcanoes of Soconusco in Chiapas. He is talking about the volcanoes in Tuxtla and Veracruz. And he is mentioning Orizaba, Popocatépetl, Toluca, and Colima volcanoes, which are the most important stratovolcanoes we have here in Mexico. Of course, he had at that time no idea about the ages of these volcanoes. I will tell you why. But he was able to measure altitudes and a lot of other geological components. He was also very busy with botanical observations at all these volcanic edifices. And basically, he lived, as you can see, 1769 to 1859. His visit in Mexico was in 1803. And at that time, there were only stratigraphic age determinations, which were relative age determinations dealing with sedimentary sequences and fossils. However, in the case of the basin of Paris in France, 2 French guys, Cuvier and Brongniart, they were able to establish the sequence of this basin, which is corresponding nearly perfectly to what was later the Tertiary, from 2 million years to 65 million years. So they proposed that this sequence must have an age about 58 million years, which corresponds very well with what was later established. Okay. However, Humboldt missed the discovery of radioactivity, which was for nearly 50 years. I am sure if this would have been discovered earlier, he also would have dealt with this topic. Brief history. 1896, Henri Becquerel, he discovers the radioactivity. 1898, this was a very short period, a very productive period in this case. Marie Curie discovers thorium, polonium, and radium elements, which are all radioactive. Later, Soddy and Rutherford defined the chemical mathematical conditions, the decay constant, and the activity in the case of radioactivity. Later, Niels Bohr gives the first atomic model for, in this case, for hydrogen. one proton, one electron, one neutron. And then this was the base for isotope geochemistry 2. 2 years later, Aston constructs a mass spectrograph. This was an equipment which was measuring the intensity of isotopes with photographic plates. But however, he was able to determine with this machine 212 of the 287 naturally occurring isotopes. And in 1940, Alfred Nier calculates the isotopic composition of lead. These are 4 isotopes, 2,4, 2,6, 2,7, 2,8. The last 3 are all radiogenic. He also designs a mass spectrometer, the first mass spectrometer, which was able to produce potassium-argon ages. Sorry. In this case, argon is a noble gas, so it is somewhat different as the solid element mass spectrometers, but he was able to determine argon isotopes with this machine. Okay. Coming back to Popocatépetl, those who are not familiar, there are some non-geologists here. Popocatépetl is situated in the center of Mexico. You can see here the Middle America Trench. This is the subduction zone. You can see 2 very interesting situations. Here's the Central American volcanic arc, which goes from Guatemala to Costa Rica. And this arc is nearly parallel to the trench. But the Trans-Mexican volcanic belt, you see it's oblique with respect to the subduction zone. This has several reasons. The East Pacific rise, the spreading center, is nearly north-south. And we have here subduction of cold, of hot and relatively young oceanic lithosphere. And here at the Isthmus of Tehuantepec, you have older oceanic lithosphere. And of course, you have also here a lower angle of subduction than in this place here. And these are several reasons because this magmatic arc is not parallel to the trench. There are a lot of volcanic edifices in this Trans-Mexican volcanic belt. Most of them are monogenetic cones. The Michoacán, Guanajuato volcanic field has a lot of them, Paricutin and Jorullo, which was also visited by Humboldt, or the Chichinautzin volcanic field, which is here located around Mexico City. These are typical monogenetic volcanic fields, but there are also these large stratocones like Colima, Nevado de Toluca, Popocatépetl, Iztaccíhuatl, La Malinche, and Pico de Orizaba. We are talking here about Popocatépetl. What you can see today, and those hopefully who go to the excursion tomorrow, they will see the present volcano is of course not a very old construction because there were a lot of volcanic events in the past. One remnant you can see here, this is a caldera remnant. So many of the older volcanic products of Popocatépetl are now covered by young material. Mostly all of you know that Popocatépetl reactivated its activity in 1994 and still going on. Here's a map which I took from the Memoria Técnica del Mapa de Peligros del Volcán Popocatépetl. Here's a map where you can see the cone of Popocatépetl, the crater, and all what is red are volcanic products which are younger than 23,000 years, which was a main event of a cone collapse of Popocatépetl. But you have also here some remnants of Volcán Tlamacas, one Paleo Popocatépetl, Volcán Expayantla, another Paleo Popocatépetl, and Volcán Venturillo. So these younger products were basically radiocarbon dated. I show you later on some examples. The problem is to date these older products, mainly because many of them are covered or mixed with younger material. There were some ages published by the potassium-argon method in the past. Also, the paleomagnetic guys, they did some investigations. I think it was in Experiantla or Venturillo, and they discovered that there is still the normal magnetic field we have today. So they concluded that all this stuff they investigate must be younger than 730 million years. There are other potassium-argon ages between 380 and 230, basically for an Experiantla, Paleo-Popocatépetl. Hugo Delgado did a lot of work, which is published in this book for the map, with Paul Rennie in Berkeley. They dated with argon-argon, Volcan Experiantla products, only one Volcan Tlamacas sample and some of Volcan Venturillo samples. So these ages are between 23,000 years and about 550,000 years. And here are the events which caused, for instance, the collapse of one Paleo-Popocatépetl, Volcan Tlamacas at this time. He proposed the collapse of an Experiantla volcano at this time, and he proposed the collapse of Venturillo volcano at this time. Okay. The techniques are, especially in potassium argon and argon, the techniques are now very specialized and very more precise than, let's say, in years' time, or let's say in 20 years ago. The potassium argon method is not obsolete. There are good examples for potassium argon dating, but most guys are now using argon-argon dating because there is an advantage. You can see an example, it's a very old sample, where you can see here a stepwise heating of the sample and a plateau which defines an age of 1,071 million years. A very good plateau, so the error is relatively small. This is a conventional dating, and you can also use laser single grain dating, where you haven't to do anything with the sample. You have to put the laser on, and you will get an age depending on the successive heating temperature. And then there's a plateau defined, and the error is defined basically by these errors of the individual measurements. So this method has the advantage to detect if there is argon excess or argon loss in the sample. Argon excess makes the ages too old. Argon loss makes the ages too young. If you have argon excess, the samples are first here, and then they go closer to the plateau. If you have argon loss, the samples are going from here down here, and then they go to the plateau. A problem with argon, potassium argon and argon dating is that you, for young samples, in my class I was always teaching about the lower limit of potassium argon and argon dating is about 5 million years. Now you can see there are much younger age determinations, but even Paul Rennie dated Pompeii, which everyone knows that it was 79 after Christ. He dated it he dated it exactly at that time with about 1,970 years, some 20 years ago. But you need potassium-bearing minerals in the samples. The Vesuv is has a completely other mineralogy than Popocatépetl. So you need sanidines, which are rich or potassium feldspars, which you don't have in Popocatépetl. So the conditions for dating Popocatépetl samples with potassium-argon or argon-argon are not ideal. So the errors are, of course, higher because atmospheric argon is mixed with radiogenic argon, and it's very difficult to detect the very small amount of radiogenic argon in the samples. So this is about potassium-argon dating. Then we have, of course, much younger products. Here is a very nice example from the pyroclastic flow from January 2001, where you have a dome fragment of the exploded dome, you have a pumice and a scoria in one sample fragment. Here, of course, you are a witness what the age is, so you don't need any age dating. But for older samples, especially in the range between a few hundred years and 50,000 years, you need a technique which is confiable, okay, like radiocarbon here. This was first applied by Willard Libby in Coihuilco here. You can see the age. He got the Nobel Prize for this. And now you can do it with much more sophisticated equipments like accelerator mass spectrometers, which need very small sample amounts. You can see here a very good correlation of age data from the last 23,000 years of Popocatépetl, which were all dated by radiocarbon. Okay, radiocarbon is okay, but it is limited by its upper age limit of 50,000 years. What can we do next to date more exactly the Popocatépetl events? One thing would be to use zircons with the thorium-uranium disequilibrium method. It's a method which has an age range between 10 and 300,000 years. You can see here two samples from Kos in Greece and Puy-de-Dôme in France. These are ages about 14,800 years, and these are 228,000 years. It works very well. You can also do it with thermal ionization mass spectrometry in a special method, which is chemical ablation. These are examples from Argentina. Granites, which are very young. You can see the errors are much more lower than with the other method. However, zircons can flow in a magmatic chamber for a lot of time. They crystallize with 800 degrees Celsius, and they can be produced much more earlier than the volcanic eruption. So necessarily, it is not the case that the zircon age always gives the eruption age. You have to pay attention on this. What is not done, however, we have some investigators, especially in geography, which are doing these methods, cosmogenic exposure ages with 10 beryllium or 26 aluminum or 36 chlorine. They have all half-lives which are very good, applicable for Popocatépetl. So in this case, you are dating age, exposure ages when the volcanic product is exposed at the cosmogenic isotopes and these conditions. Okay. What do we know in a moment? Tlamacas is I'm not a specialist on Popocatépetl. I'm only giving that was given in the volcanic risk map. Tlamacas probably collapsed at 550,000 years, but there is only one age for this. The original formation of Tlamacas volcano is even unknown, and we also do not know if there is an older volcano than Tlamacas. Next Payantla collapse is proposed around 180,000 years, but we have only argon ages on this. Venturillo collapse is about 23,000 years. There are some products which were well dated. Then there is probably a fourth collapse, which the remnants is the El Fraile caldera at about 14,000 years. This is very well established with radiocarbon. So except for the 23,000 to recent time period, the formation and eruption history of Popocatépetl volcano remains poorly constrained. Going back to the title of this talk, what does the evolution of dating techniques tell us? To perform a better geochronological eruption history of Popocatépetl, a larger database, especially from multiple dating methods, is required. This is not done till yet. Thank you.
We have time for quick questions. Are there any questions?
In the exposure age techniques, I mean, are there any physical challenges with interpreting whether the exposure is continuous or whether it can be interrupted? I mean, if I have an exposed surface and then it's covered and then it's exposed again, the same surface,
Yeah.
loose material versus something very, very competent, then do they talk about that in this literature?
Yeah, well, these ages I mentioned, I think it goes, the beryllium-10, aluminum-26, and 36 chlorum, they date an event when if a volcanic eruption takes place and there is no covering, then this age gives you this method gives you that age. If it's covered, there is this method. There are these methods here: radiation damage techniques with optical stimulated luminescence and thermoluminescence. This can date exactly the time from one volcanic layer when it was erupted to the covering of another volcanic layer. So these are different applications. This is total exposure. This can be partially exposure ages.
All right, we're going to move on to the next speaker. She is Angelica Cervantes. She's a Mexican biologist. Angelica is a Mexican biologist with a master's in plant biology and a doctorate in systematics here at UNAM. She did her postdoctoral research at the Botanic Garden and Botanic Museum Berlin from 2010 to 2012. Her interests are the evaluation of flowering plants, phylogenetics, integrative taxonomy, and biogeography, as well as conservation and sustainable use of biological diversity. She's currently a priority species advisor at Mexico's National Commission for the Knowledge and Use of Biodiversity, the CONABIO, a lecturer at UNAM, and she was awarded the Alexander von Humboldt Fellowship.
Facets, which is his profile as a botanist and biogeographer. Well, as most of you know, Humboldt was born in Berlin in 1769 and lived his first years in the castle of Tegel, which was in the outside of Berlin, but now is in Berlin. His childhood and adolescence revealed early signs of special interest in the nature, because he used to collect small rocks, insects, stones, and plants. His mother used to refer to him with the sobriquet, the little apothecary. Humboldt was influenced by his friend Georg Forster, a German naturalist, who accompanied Captain Cook to his travels around the world, And upon hearing his stories, Humboldt dreamed with the idea of making a journey around the world. After the death of his mother in 1796, Humboldt inherited a considerable amount of money that assured him financial autonomy to realize his dream. Carl Willdenow was a German botanist who introduced John Humboldt to botany during a visit to Berlin. Thenceforth, the study of plants became a passion for Humboldt. Since Willdenow had just published a work about the flora of the Berlin region, both discussed about the geography and the distribution of plants. This episode would be crucial in Humboldt's future work because with these ideas in mind, he made important contributions to the knowledge of plants related to their distribution, the vegetation types, and their surrounding environments. In 1799, Humboldt met Aimé Bonpland, a naturalist, a doctor, and an expert botanist, and the same year they began the trip to the Americas and visited all these countries. Until then, the exploration travels were due to political and economical interests, but the great novelty of Humboldt's trips lies in that it was, in fact, the first trip of exclusively scientific research with private funding. During his travel through the Colombian Andes, Humboldt took note of all the species of plants he found in his path and noted how the vegetation was changing along to an altitude gradient. In this drawing, the Geography Plantarium Lineamenta, he noted how changed the different zones of the vegetation in, for example, the Chimborazo in the first figure, together with the Popocatépetl in the first part. Then he compared these zones that he found with with the Mont Blanc in Europe, and he compared in the right side also the conditions with the Sulitelma mountain in Asia. He demonstrated that the climatic variation depended on several interrelated factors like latitude, altitude, and temperature, among others. So Humboldt used to compare and try to find connections in every one of the places he was stayed. And then here is the, okay, this is the Chimborazo, and here is the Popocatépetl. He noted here that the vegetation was changing. In the lower part were vegetation of oaks, and in the highest part were vegetation of conifers, pines, in fact. So this way of thought of Humboldt was comparing the different phenomena that he know in different parts of the world. In relation to Mexico, Humboldt also took notice of the changes of vegetation along an altitudinal gradient. Taking the Popocatépetl as an example, he noticed that in the lower zones were different species of oaks, alders, and conifers. After that, the limit of the tree vegetation is reached, which is around 4,000 meters above the sea level. There are only pastures and small plants that are specially adapted to the cold altitude and strong winds. Here are the Humboldt routes through Mexico. And during the stay in Mexico, Humboldt and Bonpland made different tours, always taking notes, making measurements and drawings also, collecting samples of rocks and, of course, plants. Humboldt was fascinated with the diversity of the Mexican flora, and during the trip he made from Veracruz 2 cofre de perote in the third roots, he affirmed that in the space of a few hours, the man of science walked all the scales of vegetation. In Mexico, they recollected in less than 1 year about 900 plant species, which is an enormous enterprise even for today's botanists. In the course of Humboldt and Bonpland's 5-year trip, they collected thousands of botanical material. They were the first to closely document the location and altitude where the species were found, although no one can say with certainty how many plant specimens were collected by Humboldt and Bonpland and how many of them survived the trip across the Atlantic. It is estimated that they collected around 6,000 species, of which about 1,500 were new to science. At present, Humboldt's plant collection were divided between Paris Natural History Museum and Berlin's Botanical Garden. Unfortunately, during an important part of the Berlin collection was destroyed during the Second World War. To date, about 3,000 surviving specimens are sheltered in the herbarium of Berlin Botanical Museum. Well, in addition to the enormous scientific value of his botanical collection, Humboldt brought to Europe the amazing shapes and colors of the American plants, which he exceptionally portrayed in his field trip notes and books. Humboldt himself illustrated his travel diaries, and when he returned to Europe, he hired the best artists of his time to illustrate his books. Among them, the wonderful drawings of the French botanist Pierre-Jean-François Turpin, and all these drawings are made by Turpin. Well, when Humboldt returned to Europe in 1804, he worked on his notes, and in 1807, he published in Paris the first book about his journey, which is this Essai sur la géographie des plantes. The lithographies that accompany this work include the silhouette of Chimborazo in the central part, in which one can see the names of the plants here distributed at different heights. And the measurements of the environmental conditions were in the lateral parts of the central figure. And he recorded altitude, atmospheric pressure, temperature, humidity, the aspect of the sky, among other factors. For the first time, Humboldt visualized plant communities based on environmental variables, a novel idea that today is our base to understand ecosystems. The botanical books, product of the exploration journey, were done mainly by Bonpland in a first instance, and later by Carl Sigismund Kundt, a classical cabinet botanist who was responsible for organizing and working on the Humboldt and Bonpland plant collection. That's why the name of the species discovered by this naturalist are accompanied by the abbreviation HBK, in reference to the authorities that describe this species. I will show you this in the next slide. As Kundt made the systematic treatment of the species published in Nova Genera and Species Plantarum, it is widely accepted that, at least for this contribution, his name should prevail as the authority of the species. So these are some of the botanical publications of Humboldt, Bonpland, and Kundt. So these are some of the Mexican plants discovered and described by Humboldt, Bonpland, and Kundt. So here is the publication, but who made the description, the systematic work was Kundt, So that's why the name of Hund prevail as the name accompanying the scientific name. They describe it as Pinus religiosa. Later, the name changed because this author changed the genus here, and this is the name accepted today. This is the abeto, or the oyamel, or a Christmas tree in Mexico. So this kind of forest are normally above 3,000 meters. And these are the forest of the Mariposa monarca. And the epithet, the specific epithet of the name is in reference to the tip of the branches. You can see here, the branches looks like the Christian cross, and that's why this species was named like Avis religiosa. This other species is Salix bonplantiana, a species that Kuhn named in honor to Bonpland. And this tree is very common in the Xochimilco region and is part of the lacustrine systems of the Valley of Mexico. And also is a fundamental part for the building of the chinampas in Mexico, which are these island vegetations in where you can cultivate different plants like tomatoes, chilies, etc. Humboldt was undoubtedly the last greatest naturalist. His travels and ideas influenced great personages like Charles Darwin. They exchanged correspondence and met in 1842. Darwin admired Humboldt and wrote to his friend Joseph Hooker, Humboldt was the greatest scientific traveler who ever lived. Humboldt died in May 1859, and in November 1859, Darwin published his work on the origin of species by natural selection. This work is the cornerstone that gave rise to the modern biology. I believe that Humboldt would have been delighted to know the theory of evolution, which explains the mechanisms that gave rise to the enormous diversity of life that surprised him so much. Thank you very much.
We do have time for any questions. Are there any?
Hola.
I'm curious to know if from the collection of plants that he recorded, how many of those are extinct nowadays?
Oh, it's difficult to say because, for example, there are about 3,000 specimens survived between Paris and Berlin. They are not totally documented, and the first step is to clearly document which we have of these collections. So at this moment, we don't know if one of these plants are extinct or not. So we still need some basic knowledge about the collections. Yes.
So Humboldt was trained as a geologist. He was a mining engineer. He crawled in gold mines. He came to Mexico to be interested in silver. And yet he was obviously heavily influenced by Bonpland and became, in essence, also a botanist. So he made many observations on the geographic specificity of plants,
Yes.
as elevation and so on. Did he ever talk about the potential of the lithology, of the rock type, of the rock or soil chemistry to influence plants, or was that too early to
No,
talk about?
in fact, in the drawing of the Chimborazo conditions, one of the conditions, which is written in the columns, is soil. So he noted that some plants are related to certain types of soil. Yes.
Any other question?
Well, 200 years before the visit of Humboldt to Mexico, there was already a collection of plants that this work was very well described by the native Cruz and Mariano. So this codice went to Europe and didn't stay in Spain.
Yes.
This codice travels to France and England. Do you know if Humboldt was aware of this work and this has influenced his searching in Mexico? This is one, and the second one is also in Colombia already was a scientist, Jose de Calas, who did this plant geography. And he was also the one who studied the soil properties in the influence in the growth of the plants. So who is first? Humboldt giving this information of, or he had this information from what he was already known in America?
Yeah. With reference to the first question, yes, this Códice Badiano is a small book that have the medicinal plants that use the native people here in Mexico. This small book goes immediately to Europe. He passed for Spain, and at the end, it was stored in the Vatican libraries. So nobody knows about his existence until people of the Vatican rediscovered the book and then made the talks with Mexican people to return the book to Mexico. Now this book is here, but I don't think that Humboldt knows this book. And about, yes, Humboldt was very astonished about the American botanist. As you know, as you said, he know Caldas, also Jose Celestino Mutis, and also Mexican botanists. So he admired the work of these persons. So I don't know who was the first to note this relation with the environmental conditions and about the development of plants, but Humboldt, I am pretty sure that he was the first one to document very precisely and using different apparatus to document closely the conditions around the plants. Mm-hmm.
You mentioned the description of conifers, of pines by Humboldt, and even you mentioned the Christmas tree there. So these kind of pines, they are all over the world, and well, they're in Europe, they're in Asia, they're in North America. Is it that we have in Mexico some special species which are only occurring here, or?
Yes, well, Christmas trees are different species of conifers. So in Mexico, we have this one, this Abies. This Abies religiosa is endemic to Mexico, and for Christmas trees in other parts of the world, people used to use other trees, other species. Yeah.
Any other question?
Okay.
All right, thank you.
Thank you very much.
Our next speaker was going to be John Curl. He unfortunately is sick and he's not going to be able to join us. So we're going to be moving on with the speaker after him, which is Servando de la Cruz. Servando de la Cruz is a senior research professor here at the Institute of Geophysics. He's editor-in-chief of Geofísica Internacional. He is a physicist from the School of Sciences of UNAM with a master's in geophysics from the University of Toronto in Canada and a doctorate degree by the University of Kyoto. His field of research is volcanology, fluid dynamics, and geological hazards. He is a member of the Mexican Academy of Sciences, the International Association of Volcanology and Chemistry of the Earth's Interior, the American Geophysical Union, and the European Geosciences Union. Member also of the American Geophysical Union Natural Hazards Focus Group. He is member of the IUGG Commission on Geophysical Risk and Sustainability, and he got the National Prize of Civil Protection in Prevention from the Mexican government in 2006.
Thank you very much. Good morning, everyone. Today I will try to express the situation in which many scientists are, not only in Mexico, many places. Phenomenon which we are considering. So it is actually a probability, and so if we have, for instance, an earthquake, the probability of having a strong earthquake would be the hazard in a certain region of a particular place. So hazard is also a function of the position of the situation, of the geographic position. And the other parameter which was involved in that definition was vulnerability, which is a function of the exposure. For instance, if we have a volcano or in the middle of a city, the exposure of the people around the volcano is very high. But if the same volcano is in the middle of the desert, where nobody lives, so the exposure is null, is zero. So there is no vulnerability, and then the risk is zero, even if the volcano erupts. Now, hazard is a property of the nature. It's a situation, a natural situation, and we cannot modify it. The probability of a hurricane or a volcano or an earthquake, there is nothing we can do to change that. But vulnerability, we can modify in some ways, and that's the essence of risk management. So if we put here, preparation, a parameter in the probability that we can reduce the vulnerability mostly through the reduction of exposure. So there is something we can do to reduce risk, and that what we can do to reduce risk is reduce vulnerability, and we reduce vulnerability through the preparation, which is essentially a series of many, many possible actions involving a very complex problem. Here we have some images of the effects of the eruption of Volcán de Colima in 1913. This is a town located about 25 kilometers northeast of the volcano, Ciudad Guzmán, and you can see that the amount of ashfall It was extremely important. Okay. Now, up to the middle of the past century, both hazards and vulnerability were more essentially static parameters. The way to manage that situation was through the basic hypothesis that the phenomena, and particularly the eruptions, follow patterns, statistical patterns which are similar to those in the past. So the basic idea in that time was that the future, what is going to happen in the future, the key of the future is in the past. So we have to study the past under the basic geological approach, and then studying the distribution and in time and in space of the products of past eruption, we can construct scenarios of what might happen in the future if one of the past eruption will be repeated at some time. But after the 1970, the rapid development of technology for volcano monitoring permitted to introduce a dynamic component in this static concept. So the static concept is very important because it sets the basic background on which the parameters associated to the volcano monitoring can change that probabilities, static probability. So when, after the 70s, the management of hazards becomes more dynamic on the base of monitoring parameters. So at the same time, preparation becomes also a dynamic parameter, because previously, for instance, the management of risk related to static situation was based mostly in the what we call use of the soil or use of the ground. So we can say in this particular region, we cannot construct because in the past there have been so many eruptions and so on and so on. But in countries like Japan, for instance, in which the population pressure is so high, they have to raise their level of acceptance of risk, and then they are mostly based on the possibility of accepting higher risk, provided there is a dynamic possibility of handling, of managing the risk. And that's mostly based on the results of the parameters. So for instance, in Japan, many towns are constructed or are allowed in regions of volcanic hazard, which, for instance, in Mexico wouldn't be accepted. So the perception of risk is quite different. Now, in this case, means that those towns in Japan or in other countries rely on a monitoring set of equipment and a monitoring scientific group, which is continuously assessing the probability that some hazardous phenomena can affect that particular settlement. Now, that's what I'm pointing out. Can we handle the decisions related to a situation like the one I mentioned? I mean, if there is a town in an endangered situation, and then under this dynamic risk situation, people is allowed in a zone which can be affected by volcanic products, and then we're on a monitoring system trying to decide whether the people can continue there or not. Well, that's the main problem associated with this approach. And you can see there apart from the scientific, purely scientific issues here, there are a lot of ethical, moral, and philosophical problems involved. For instance, in seismology, there was a strong movement in the last quarter of the past century about the possibility of predicting earthquakes, which was very similar to the one in volcanic science. And that was mostly a pressure from the decision makers, mostly politicians, in which they need to be fed with decision factors. And that was reflected in one document of the United Nations in 2006, in which say that the objective of early warning system is to empower individuals and communities threatened by hazards to act in sufficient times. If you analyze this text, it means that they are transmitting the responsibility of the decision making into mostly the people in charge of the monitoring systems. That's a very complicated situation. Now, one of the main issues associated with this condition is the nature of the different types of precursors of a natural phenomena. For instance, in meteorology, we have a lot of factors which permit a lot of tools which allows to analyze, for instance, a hurricane. And there is a lot of research related to the prediction of the possible paths that hurricane will follow. So in that case, there is a significant background of what to do in the case of handling this. But in the case, when we talk about seismology or volcanology, we have a problem. We cannot access the interior of the Earth to see what's happening. So we don't know if what we are observing, as we call precursors, what really means, to what extent are related to the possible occurrence of the phenomenon, which will or might not come. So to say that in a very short way, we need to see if or to resolve to what extent what we're observing is deterministic or not deterministic. So the basic idea here is that precursors are some sort of phenomena we observe in the surface which are causally related with something which is happening on the ground, for an earthquake or for a volcano. We know there is a causal relationship, but we don't know if that causal relation is deterministic or not. So that's the main issue. Now, in the seismological problem, there was a lot of research in the 70s, and they define different types of precursors. One is the informational or chronic phenomena, which in the case of volcanic risk is mostly what we call the hazard map. So it is the static information available. For instance, we know that some region is seismic, other region is not seismic. We know that the coast of the Pacific in Mexico is much more, there's much more seismicity than, for instance, in the Gulf of Mexico coast. So we know that that region is much exposed to seismic activity. So that's informational phenomena, or informational precursors, in the sense that they are static in time, they do not change in time. And in the case of volcano, will be essentially the hazard map. But that's, again, static information for this one. Then we have the causal phenomena, which is what I mentioned some minutes ago, and that's related with some signals which we know are related with the phenomena we're trying to predict, but we do not know to what extent they are deterministic or not. And that's what we, in the case of volcanology, call the unrest. For instance, if in a region or a volcano there are some earthquakes or there are some fumaroles which were not before there, or there are some deformations, well, we know that that means that there is a change inside the volcano, but we don't know whether they go into, they will lead to an eruption or not. So this is the causal phenomena. And then we finally have the predictive or forerunner phenomena, which we know that, they are concatenated. There are causal phenomena, which they are concatenated and go in a deterministic way to signal when an eruption will occur. And that's, I would say, the main aim of volcanological research, trying to detect which phenomena are actually predictive or forerunner. Now, informational phenomena are not necessarily causal, but causal phenomena are not necessarily deterministic. Okay, this is the same thing in a schematic way. So we have the probability space, which is the chronic information, that the map is saying that there were, as Peter Schaft told, there are a few very large eruptions, there are a higher number of intermediate eruptions, and there are many small eruptions, and then we construct a map with that, and that's the chronic information, or chronicle information. And then we have a causal phenomena. We know that Popocatépetl has been in unrest since 1994, but we don't know if that unrest will end in a major eruption or not. And what we are trying to determine or to find is this small probability space, the deterministic precursor recognition, and that's, I think, the main challenge in volcanological science. Okay. This is an example of a deterministic process, a deterministic forerunner or a causally but deterministic behavior. This is an example of Colima volcano in the late 90s, in which the energies, the seismic energy, the small amount of seismic energy that was being released by the volcano was accelerating in a way which fit very well with a model, a deterministic model. So at about this time here, this is the seismic energy, and about this time there was made a deterministic prediction that would be an eruption in any of these possible time windows. And the eruption occurred a little bit later, but it occurred very close to the predicted time. There was a case of prediction. Now, what's the bad news? That this situation appears about maybe less than 1% of the occasion. So we continually have these accelerations and no eruption follows. Or sometimes we have the eruption, but the acceleration was not observed previously to this one. Now, one problem with this predictive or forerunning phenomena is that they might tell us something about the time at which the eruption will occur. But so far, we cannot infer or have sufficient information about to what extent that eruption will be small or large. And for the main problem is that we also don't have a very clear way to measure the size of eruptions. The eruption has so many manifestations, unlike earthquakes. In the earthquake, we have one single manifestation, which is the acceleration of the ground. So we can measure the intensity of an earthquake, measuring the acceleration of the ground. And from that, we can infer the energy release at the source of the earthquake through the magnitude. So there are two parameters which define completely the nature of the seismic phenomena. But for volcanic phenomena, we can have ash, we can have fragments, we can have earthquakes, we can have pyroclastic flows, and each of these phenomena release energy in a different way. So there is no simple way to measure the total energy that a volcano is releasing during an eruption. So to determine or to trying to measure the size of the eruption, in the 1980s, it was defined the volcanic explosivity index, this parameter here. And it is a compounds number which involves the height of the column, the total volume emitted by the volcano, the time, the duration of the eruption, and so many parameters are more or less correlated to define some volcanic explosivity index classes, which we have some examples here, where in the Popocatépetl volcano, this is the maximum value that has been, but most of the time it has been in the BA2. Now, it is another example of a BA4. We have the Chichón volcano in 1982, which is a very high base 5, and this is the largest eruption in the 20th century, Pinatubo, in 1991, in which the eruptive column reaches more than 30 kilometers altitude. And the important thing is that this is a logarithmic scale in the sense that every level is more than 10 times the previous one. Okay. Well, going back to the main subject, is that can we handle life or death decision making based on several different forecasts, which are mostly causal, and the deterministic ones are very rare, are very difficult to understand? Well, most of the time the answer is no, unless the decision makers are provided with an adequate, non-technical, unambiguous focus. Because the decision related to civil protection is not only scientific, it's also social science decision. And there are also a legal framework that's extremely important. No decision can be made if there is not a legal framework which supports the possibility of failure of a decision or a failure of a forecasting. Well, in the case of Popocatépetl, we have been experimenting that situation since 1994, because the eruption started more or less suddenly, and at that time there were several risk maps, several hazard maps like this one. And as Peter told us, there are many eruptions, and this is a statistical, very simple statistical analysis, and we can see that, for instance, the mean return time of the BI5, very large eruption, is about, say, 10,000 to 12,000 years. For the magnitude 4, like it's about 1,500 years. For the BA3, it's about 160 years. For BA2, it's about 40 years. That's only a statistical result, and that doesn't mean that this is a periodic behavior. But I'm going to go faster, and we have a monitoring system which is operated, and then there are a lot of data arriving every day, and the decisions will be made based on that information. There is already a system which is working rather well, and the Popocatépetl in the last since 1994 has been on an eruption which we call a semi-crisis eruption. in which the eruption continues in a rather mild way. There are placement of lava domes. The lava dome explodes, open the system again. A new lava dome grows, closes the system, more explosion, and so, and so, and so. And there are about 49 domes which has been completely, which has been in place and then completely destroyed. Now, some statistical work on the worldwide database says that this kind of eruption ends in a Plinian phase, in a bay 4, 5, or 6, about 20% of the time. And then we're in this kind of situation. So we have, for instance, increase in the unrest. So we have to make a decision because the unrest is accelerating, for instance. So the decision is to evacuate. Was that a right decision? Well, at this stage, we don't know. But maybe there is an eruption, so it was a right decision. But we don't know now. We have to learn different. But it might happen that actually the activity reduces again, it stops growing, and then after that happens, everybody starts saying that it was an over-hasty decision, was not a good decision. Then we have to make a second decision. People is already evacuated, some towns already. So what we do? We are now in this situation. Would you recommend returning the population? Well, maybe the second decision will be, okay, everything is calm now, we'll return. But now the activity accelerates again, and then you have returned the people, and then the people who has been returned don't want to be evacuated again. So you're in a worse situation. That happened actually. Sorry. Okay. But it might be also that you return and the activity decrease, and there was a right decision. So that's the kind of situation in which we are now, and what we are managing that. But we're using an approach which was developed by philosophers, mostly by Karl Popper, which is called the demarcation concept. So what that means elicitation. That we try to make a scientific committee as large as possible, as many components as possible, in many different possible fields of volcanology. And then when a situation like the previous one develops, everyone gives an opinion. And what we look is only the coincidence of opinion. All differences are rejected. And when there is that element in which there is coincidence, is the basic, the essential element for the recommendation to the Civil Protection Authority. I think I am very past in time, so that's what I wanted to say. And that's the way it works. That is later translated into a very simple way to that involves 22 million people who want everybody to understand, to have the same perception of what's going on in the volcano. And that's why the traffic light alert system was developed, in which these traffic light levels are the level of preparation of the people, not the level of the volcano. So this is a traffic light alert of the people. And this is one of the examples of the elicitation or the demarcation process in which everybody is given an opinion and only the coincidence are analyzed. Okay? And then from that, series of scenarios are offered to the decision makers, and then the decision maker can try to make a decision adequate with this. That's the way we're trying to handle it. Thank you very much.
All right, we do have time for one really quick question, if there is any. No? Okay.
I heard few days before that the person was thinking to move people, the people that has the highest reach, of course, because I understood quite well. I remember Sheridan and everything that said that we have to convince the people to say go, and then nothing happened, and then again, and move, and they lose time and properties and many things, and the government too, that maybe I think we have to think in that decisions that the people remains in places more safety than they are at this moment, no?
Yes, it is extremely difficult because, for instance, if you don't move the people, then media and says why people is not being evacuated. And then if you evacuate the people, then mostly the evacuees would say nothing is happening. And then it's extremely difficult, and every movement will lose confidence for the next one.
Yes.
All right, thank you. All right, so our final speaker for this session is Elizabeth Castañeda. Elizabeth is a Mexican physicist from UNAM's Faculty of Sciences. She has a master's degree in earth sciences, and she's currently working her way into a PhD program. From 2012 to 2018, she worked in the Volcanic Risks Department of the National Center for Disaster Prevention, the CENAPRED. She teaches young scientists at UNAM's School of Sciences and at the Earth Sciences postgraduate program. And now she's working at the National School of Civil Protection, also from CENAPRED. She's working designing and applying training strategies for risk mitigation.
Hello, everyone. I am Elizabeth, and I work in National Prevention Center, CENAPRED. And during this time, I have observed that the link between scientific and communication now is very clear. And my presentation goes with this direction. I begin to show the basic elements of communication, and there are two basic elements. One is the sender, and the other one is the receiver. And it's very important, the message but in the communication process is very important. What did you say and with the thing in the sender? And the other question is, what did you understand with the receiver? And process is very important because it's like a waves in this process. There are a noise and interference in the message. It's like a waves. This is a process very similar to the waves because you have the emission and then you have the receiver. And when I think the process communication is very similar, I think that it's very important to reduce the effect to the interference and the noise with the message. In the strategies to reduce risk, the first step is identify the hazard. For example, volcanoes, earthquakes, landslides, radiological floods, and other. This is the work of the scientists, but it's very important because this is the base for make the message for the population, for the common people. And in many cases, there are noise and interference in this message. Actually, there are many modern social media, but in many cases, their noise are good because in many cases, there are a problem because a help to make interference or the noise with the message. What is the importance of the correct communication process? The important is to save lives. Because, for example, I have two examples. In the first case is the volcano eruption. And the second case is the volcano Fuego Guatemala. And there are many differences. And the principal, in this case, nobody died. In this case, there are more than 300 people die. There are different situations. There are many factors that produce these different effects. But the principal characteristics is the people. Because in this case, the people decide live to themselves. In this case, the people know anything about their volcanic risk. And in this case, there are many examples very amazing because the people and the authorities of the protection civil take a photograph and video when the current flows of the volcano is very clear, very close to these persons. And this case, the people maybe is more preparing to the volcanic risk. And it's very important that before anything study about the research, it's very important make the social vulnerability studies because this concept have two essential themes. In this one, social characteristics, and on the other, social economics. And with this social vulnerability, have the ability of the prevention, ability of response, and risk perception. In 1 year ago, there are in Mexico one strange case of the explosion in Tlahuelilpan because the people stolen the gasoline and the WhatsApp, for example, or social media is a very factor for this case because the people know this case and invited of the people to the stall more and more and more. And few hours later occurred this explosion. There are many people die. And it's very a strange case because the people know what is a warning or hazard to the stolen the gasoline, and these people prefer the stolen this gasoline and fuel that your life. And it's very important because the people know, in many cases, the people know what is about the hazard and don't listen. I don't know. In many cases, the self-protection, the people don't have responsibility. Is very strange. In this means that an effective communication process must consider culture, background, and therefore assure that people are able to, one, listen to alert message, two, understand its contents, internalize and create the importance of the mission, confirm their interpretation with the other people, and five, act or respond to the message to safeguard their health, life, and property. And what about volcanic risk? There is like a rating of the volcanoes, the more dangerous volcanoes in Mexico. And with the National Risk Atlas, this tool is a compendium of all hazards in the country. I have examples of the Popocatépetl volcano, Chichon volcano, and I analyzed the radio of the 20 around the volcano, and there are different vulnerability social. The level is high and low, and is different for different volcanoes. And the strategies of the communication is very different for the big cities, for example, like City Mexico. I have the conference press and maybe modern social media. But for the local communication strategies is very different because the vulnerability social in this place is very different. And I need maybe the close to speak with the people for these strategies. And I think that this is very important in this case, because I need the process of the communication was effective process, and it's very complicated. The conclusion, we are on the road, many actions have been done, but we still have a long way to go. Thank you.
Are there any questions?
It seems that the main problem is the credibility. How do you handle credibility?
Yes, I think that this the credibility is correlated to the social vulnerability, because when the people maybe have more economic or social, more level social, the people have more ability of prevention, and maybe the ability for risk perception is more high. This is fundamental. For this reason, it's very important make or develop of the studies for a specific local place. I don't know.
So the problem, I mean, I will be abstracting the idea that I'm telling you. But so in biology, in the previous talks, you hear about Darwin, and Darwin had this idea of natural selection, And it seems to me that communication in your case involves some level of education.
Yeah.
And education, it's, last night we were talking about this subject that there is some evidence that, for example, mathematics is correlated with some familial heritage. So if this idea is true, that only some people with some particular genetic background is capable of learning mathematics,
Yeah.
and the other ones won't, then education is useless, or it seems to be useless in this case, right? So then communication as well will be useless. And so natural phenomena will be getting rid of this type of people. I think what I'm saying is some kind of moral issue here. But my question is, are you considering all these aspects in your communication strategies, or this is something that is not part of the
No,
equation?
yes, I consider these ideas, but I agree with you. But I think the main subject is for example, when the people live in the specific place, made a rating of the risk. For example, in Mexico City, all the time think, oh my God, I stolen my bag. I don't know. But I think that it's very important that people learn about this thing. I know.
Yeah, I mean, you could be expecting that people could learn, but then you could also expect the people not to learn, but still act according to whatever you want them to act.
Yeah.
That's what I was trying to say. Because if you are really willing to deliver the right message so that they understand the risk and all the hazard and all that, perhaps you are in a very problematic situation.
Yes. Okay.
Okay, well, you agree with Gabriel, but I don't. Yeah, I think that absolutely it is not possible to translate the natural selections hypothesis or theories of Darwin to the social aspects, to the social sciences. It's absolutely a mistake. So this is not such a thing as you are genetically prepared or have the attributes to be successful socially. So this has nothing to do with biology. No, this is something different. So just I wanted to make this statement.
Any other question or follow-ups?
Yes, and relating this to contribution, that's exactly the idea of the traffic light. The traffic light, it just sets a condition. Traffic light is a message that the risk is not acceptable. Only that. So you don't need to specify or to expect that people to understand the details of the phenomenon or whatever. So the basic idea is in this communication is to not to increase the information, but actually to reduce the information. So the minimum information is given, and that minimum information for a red traffic light is the risk is not acceptable.
Any other question?
But I think that it's important that in schools, in these areas, in the very, very low grades, the boys and girls starts to know about earthquakes and volcanoes, because it's quite common in their lives, to try that they change many things because it's the only way, really. Because I remember the people of Colima volcano that we talked with them and say, you know, your house is on a pyroclastic flow. You can see it, this. No, it's nothing going to happen to me. That is the response. But for example, I think that many things works because after these maps and things like this, the government avoid to install stores like Conasupo and social programs until very, very high in the volcanoes. Then if you stop these kind of things, the people leave the places because it's not comfortable to live. The problem that we have at this moment is, one, I'm in accordance absolutely with Servando de la Cruz, because when you try to talk to the people about these dangers or these risks, always thinks that there is a second reason to move them, because they know that maybe in few years another persons are going to arrive to these places to live. That is the problem of the credibility about this. The problem is really a deeply social problem. But if we start in the schools to say, this is a volcano, this is the kind of risk, then the people starts to have in their minds this. Because really the problem is that the people, for example, after the big earthquakes or something like this, they don't want, or I asked of the Mexican people, do you want to hear about the earthquakes? No, it doesn't matter. They don't want to see if this is lateral, tectonic, volcano, it doesn't matter. They don't want to hear because the risk, the danger is very difficult to manage for the mind. But I think that if we start talking in a very, very familiar form with the people, then the people is going to be more perceptive, and if they know about the evacuation programs and things like this, or what measures we have to know or to do when the seismic alarm sounds or something like this, we start to change our mind, our chip, because we needed to do that. Thank you.
All right, any other questions, please do them outside during the break. We're running out of time. Right now, well, just let's give her another round of applause. This was the final session for this, well, the final talk for this session. We're gonna be heading back here in 10 minutes, 11:50 to the next sessions, please. Just hold on, there's one announcement.
Just one thing, we are having a coffee break, but there is a movie that while we have the coffee, we can have and watch the movie. Yeah. So come
Hello, everybody. We are ready to start. And in the session 6, we have some aspects of the physics of volcanoes, and we are I'm glad to have the presentation of Robin Matosa, who is professor at the University of California, Santa Barbara. He has a training on volcano seismology, and his recent interest and giving very nice contributions to this ultrasound or infrasound signatures of volcanic eruptions and its correlation with seismic records. Now we leave the work, leave the word to Robin Matosa, please. Go ahead. He's going to talk about seismo-acoustic signatures of explosive volcanic eruptions. You start now.
Okay. How do we turn this microphone on? Okay, thank you very much. So by measuring seismic wave fields and acoustic wave fields at volcanoes, we can get complementary information on how volcanoes work. So in particular, looking at seismic wave fields at volcanoes, we can track the migration of fluid from deep down in the Earth's mantle all the way to the surface. And seismic waves at volcanoes are generated by faulting and fluid transport processes, basically, in the solid Earth. By measuring atmospheric acoustic waves, we're dealing with the shallow and subaerial eruption processes, and in particular, explosive volcanic eruptions produce very powerful infrasound signals. So we talk about infrasound. So your ear can hear between 20 hertz and about 20 kilohertz. So of course, anything above, well, we saw this yesterday, anything above 20 kilohertz we call ultrasound. Anything below 20 hertz we call infrasound. And then when you get down to frequencies of about, periods of about 1 minute, you start to get the effects of gravity and buoyancy on the acoustic particle displacement. So we start talking about acoustic gravity wave regime. So the physics changes slightly, but between about 0.01 and 20 hertz, we're dealing with purely acoustic waves, so the wave physics is the same as ordinary audible acoustic waves. It's just that we can't hear them, so we call it infrasound. And this corresponds to large sources, so large wavelengths, 15 meters to 100 kilometers. So generally it's produced by large things in the atmosphere that can displace large volumes of air. Many of them are shown here. And we've known that volcanoes produce long-period atmospheric signals, infrasound, since the eruption of Krakatoa in 1883. This actually produced audible signals as far away as these locations here. We believe that this is now actually a nonlinear acoustic effect, reshocking at altitude in the atmosphere. But it also produced very long-period barograph disturbances that were recorded at these Victorian barograph stations around the world. These were remarkable 100 to 200 minute period waves. So this is way below the Brunt-Weissala frequency of the atmosphere. So buoyancy is a very strong effect. And these signals produced were recorded doing 7 laps of the globe. This is some of the barograph recordings here, including in my hometown of Liverpool, England here. Okay, so there was a little bit of work that went on in volcano acoustics over the 20th century, but it really started to take shape in about the 1990s. That's when we started to get increases in infrasound sensor technology. And that was when it was recognized that if you put infrasound sensors at volcanoes, the acoustic signals that volcanoes radiate are predominantly in the infrasound band. And so it was discovered at Stromboli and in Japan that volcanoes produce these very rich infrasonic signals, including harmonic resonance type signals, shallow conduit resonance. But I don't have time to talk about all the interesting signals that volcanoes produce. So today I'm going to focus mostly on the signals produced by explosive eruptions, and these are the most powerful infrasound signals from volcanoes. So this is an example of quite a small explosive eruption, a phreatic or steam-driven eruption at Mount St. Helens in 2005. And we were operating a small aperture broadband infrasound array, about 100 meters aperture, and a broadband seismometer about 14 kilometers away from the volcano. And so this is one of these helicoidal plots, so seismic on the left, acoustic on the right. So each one of these is a 1 hour waveform, and then it goes down the screen like this. And so if you look at the seismic record, you can see the seismic signature of this explosive eruption. And you can see that this is quite modest compared to the seismicity before and after. These are repetitive, what we call long period seismic events, particular type of volcanic earthquake. And if you only had the seismic data alone, this might be quite ambiguous as to when or even if an eruption had occurred. Whereas with infrasound, you get this large, unambiguous surge in acoustic energy, and that allows you to pinpoint the precise timing of the eruption and the duration. And it turns out that's very useful information, especially for remote volcanoes that aren't monitored by any other means. More recently, we've been working, this is just another example, at Yasur volcano in Vanuatu. This is just a nice drone video taken by Ben Kennedy's group at the University of Canterbury, my collaborator. And this is just to illustrate the kind of Strombolian type activity that we see. And so we had a broadband seismic network and broadband infrasound network around the volcano. And so this is just the type of complementary information you get with seismic and acoustic. So these are broadband stations. So first of all, you're seeing these Strombolian gas slug ascent and bursting. So you see these 10-second very long period or VLP pulses associated with the gas slug ascent through magma plumbing system. And then when this bursts at the surface, you get this higher frequency seismic arrival associated with the burst. And then with infrasound, you get essentially a high amplitude blast wave, and then these kind of shock-like infrasound signals that are produced. So even if you just limit yourself to explosive eruptions, of course, there's a huge variety of styles of explosive eruptions, so you get a great variety of different types of infrasound signals associated with the different styles of explosive eruptions. And so it's useful to think of these as spanning a spectrum of processes, so end members. So we talk about, on one end of the spectrum, individual short-lived explosion waves, or sometimes blast waves. These may last just a few tens of seconds at the most. And on the other end of the spectrum, we have these very large, sustained, long-duration signals, which we call volcanic jet noise. And this relates to more sustained sub-Plinian, Plinian-type eruptions. So the idea here is that these signals are produced at the base of the eruption column in the gastrous region, where we have a very large natural jet flow. And as I said, these are just end members, so you also get behavior in between. So sometimes you get an individual blast. This can then uncork the conduit. You get a bit of jetting behind that, and so you can get a blast followed by some sustained jetting. So it's just a useful construct. So yeah, so just focusing on the long duration end of the spectrum, this is just a hypothesis that we proposed a few years ago, is that the infrasound signals from these large sustained eruptions are generated in the same way as acoustic signals, audible acoustic signals from jet flow from man-made jet engines. And so the idea here is that you have jet flow in the exhaust flow of these flight vehicles. You have turbulent jet, and the acoustics of this is similar to what's happening in the gas thrust region, or the large natural jet flow at the base of the eruption column. Of course, this is much larger, so you have longer wavelengths and lower frequencies, and it turns out it's infrasonic. And it scales with this Struhal number here, where F is the frequency of sound produced, D is the expanded jet diameter, and Uj is the jet velocity. So I don't have time to go over all the details here, but one of the ways you can look at this is by looking at the spectrum of sound produced. So this is acoustic data from a laboratory jet noise experiment, so a pure error jet flow into lab in an anechoic chamber. And you can see this well-known similarity spectrum. So this is the characteristic spectrum of jet noise. And we see a similar shape in the infrasonic spectrum. You can see that this is in kilohertz frequencies there. So this is a small centimeter scale lab jet. And these are infrasonic frequencies, so 0.1 to 1 hertz here. So it's a similar process, but operating at much lower frequencies. And so this idea has gained some traction. We've now got, we've seen this at several volcanoes around the world, and we've got colleagues that are working on laboratory experiments. And recently there was this nice paper by Chermanara et al. So they're actually doing full numerical simulations of eruptions and computational aeroacoustics, computing the aeroacoustic wave field and getting this infrasonic similarity spectrum from jet flow. So so you can use infrasound to get information on the source physics of these eruptions. But the other major advantage of infrasound technology in particular is that these acoustic waves tend to propagate very long distances in the atmosphere. And so I'll show you briefly how that works. So so it takes place in these sound channels. So this is a very first-order approximation. It's a convenient approximation. It is an approximation there. You can think of the sound speed in the atmosphere being the sum of just the regular adiabatic sound speed, so proportional to the square root of temperature. These are just constants. And then you have to add in the wind in the direction of propagation. So n is the wavefront normal here. So a familiar example of this is for an audible acoustic example. Let's say you're standing in the atmosphere, you've got an adiabatic lapse rate, so temperature's decreasing away from the ground. If you've got a firework or something, an explosion at altitude, because of that temperature gradient, the sound is going to refract up above your head. So if you're standing here, you'll be in a shadow zone and you won't hear the sound. But now instead, if you have a wind flow here going from left to right in this figure, this will then add this modifying term. So if you're in the downwind direction, the sound will be refracted, ducted down to where you're standing, so you'll hear the sound. Whereas if you're in the upwind direction, you'll still be in the shadow zone, so you won't hear it. So so the same principle applies to infrasound in the atmosphere over larger spatial scales, longer wavelengths. And so basically, infrasound propagation is controlled by vertical temperature structure of the atmosphere, vertical gradients in the temperature, and then vertical gradients in the horizontal wind structure in the atmosphere. And this gives rise to three main ducts, so the troposphere, the stratosphere, and then the thermosphere. And so you get propagation over thousands of kilometers. So the thermosphere is primarily controlled by the temperature gradient, so this results in an isotropic radiation pattern, so it's the same in all directions. The stratospheric duct is primarily controlled by these high amplitude winds, so you can get up to tens of meters per second winds in the stratosphere. But this does mean that this is an anisotropic duct, so it depends which way the winds in the stratosphere are blowing, similar to the example we just showed. And this is there are seasonal variations in stratospheric winds, so you get variability in the long-range propagation characteristics. So there are lots of open source infrasound propagation tools available. If anyone's interested in this, I'm happy to help you out and show you where they are. So we've got all kinds of infrasound propagation tools now. Basically, if you give us an atmospheric specification, we can compute infrasound propagation. This is just an example of one of these approaches. This is a parabolic equation simulation. This is very similar to methods that are used in hydroacoustics, ocean acoustics. And this is just an example showing a regular atmospheric profile and then perturbed by this fine-scale structure of the atmosphere, these gravity wave perturbations. You can also do things like finite differences, 3D wave propagation. So we have the tools to compute the propagation, but actually one of the fundamental limits currently is just knowledge of the atmospheric state. It turns out that with infrasound, we're very sensitive to these fine-scale variations in the atmospheric profiles, and these are often smoothed out of traditional weather specifications that we get. So we get heavily scattered fields, and often the ducted infrasound waves are resulting from these very marginal ducts, these very small perturbations on the profiles. So anyway, we're living at a time now where we've got very good infrasound data globally. This has been driven by the opening for signature of the Comprehensive Nuclear Test Ban Treaty in 1996. And this led to an international effort to create the International Monitoring System. This is a global hydroacoustic, so ocean acoustic, infrasonic, atmospheric acoustic, and seismic monitoring network. And the infrasonic component looks like this. So it will be 60 stations total. These are the white triangles here. The red triangles are the world's potentially active volcanoes. And 51 of them are now built and sending data to Vienna. And so each one of these white triangles here is actually more than one infrasound sensor. They're actually these small aperture infrasound arrays. This is one in California here. You can see the spatial wind noise reduction system. This allows you to filter out the effects of wind turbulence. Zooming in on this French station, IS-22 in New Caledonia. So if you look at this on the ground, it's going to be about 4 different infrasound sensors, spatially separated by about 2 kilometers or so. And so these are different infrasound sensors. So this allows you to differentiate between real coherent infrasound signals and incoherent wind turbulence noise. And then because you have an array, you can also get direction of arrival information, so you can get your back azimuth of your coherent plane waves, and you can get trace velocity, so you can see the angle of arrival. You can see whether your wave is coming from the stratosphere or at higher incidence angle from the thermosphere. So here's an illustration. So we can do array processing with this array. So here's an example of I-22. We've got volcanoes in the region. This is some array processing that I did using cross-correlation methods. This is 6 years worth of data. Back azimuth of arrival. Each one of these dots is a coherent infrasound signal, color-coded for its mean frequency content here. And basically the green dots here are ocean microbaryons, so these are created by distant storms out in the ocean, so similar to the ocean microseism in seismology. We also have volcanoes here that are persistently active, so we see these nice volcanoes. We have these high-frequency signals are surf noise, so this is waves breaking on the island coastlines. And you can see this seasonal variability in the signal characteristics. So this is actually a propagation effect. Remember I was talking earlier about the stratospheric wind. Depending on the season, the winds in the stratosphere are blowing in different directions. And so it turns out that depending on what time of year it is, you're listening to sounds coming from different directions to the array. We've recently demonstrated that these long-range, this IMS infrasound network is very useful for detecting volcanic eruptions. So a good example of this is the Sarychev Peak eruption in the Kurils. This is one of these very remote volcanoes that had no local monitoring system. The closest seismometer was 350 kilometers away, didn't record anything. And yet we recorded infrasound at 640 kilometers, all the way out to Kazakhstan, 6,400 kilometers. And so this is in the stratospheric duct. The winds in the stratosphere were blowing east to west this time of year. And then because we have an array, we can get direction of arrival information, we can get the back azimuth, we can cross the beams, we can get source locations. You can see our source locations are scattered. This is atmospheric crosswinds, so we get some deviations with the atmospheric winds, but we can locate the source, in this case to within 15 kilometers of the volcano using remote infrasound. And then because we have the waveform, we can get precise timing and duration information. So this is 5 days worth of these waveforms. So each one of these waveforms is 1 day. And you can see the individual eruption chronology. So 3 explosions, a lull in activity, main sustained Plinian jetting phase, and then multiple explosive eruptions. So we've got all of this eruption chronology in much higher temporal resolution than is possible to get with satellite data in this case. And I know I'm running out of time, but what we're currently working on is trying to move away from just looking at individual case studies, but actually doing the reverse problem and doing blind searches through all of the available infrasound data globally. This is, of course, a much more difficult problem because you're then trying to identify infrasound signals from volcanoes within all of this coherent ambient noise. Here's a good example from Eyjafjallajökull in Iceland, 2010. So we had an infrasound array in the UK, 2,000 kilometers away or so. And you can see here's the signals from Eyjafjallajökull here in back azimuth. But we also have ocean storms, microbaryons producing infrasound, which is moving around, but it's sometimes the wavefront parameters intersect. So you have infrasound signals with the same azimuth and the same frequency. And so you have to create more complex methods to discriminate your signals. But in general, having multiple infrasound arrays at different directions, you can do a better job of locating it. And finally, we've developed a method that can you can use the back azimuth arrivals from multiple stations, combine them. We call this a brute force grid search cross-borings approach. And so this is just the example of Sarychev Peak again. Here's Japan here. And you can see over 5 days, if you stack the coherent infrasound detections, you get this coherent blob which grows over time and allows you to detect the infrasound signal. So that's it. So basically infrasound relates to source physics that are happening in the shallow subsurface and then in the atmosphere. Explosive eruptions in particular produce very powerful infrasound signals, and these can often propagate thousands of kilometers, and so we can detect them at long range using relatively sparse networks. So this is an advantage on traditional volcano monitoring, where you have to be quite close to the volcano. And so we're working on ways to use remote networks to identify these eruptions in remote areas. And then another thing that we're kind of pushing for, hopefully, is just to add, we're encouraging people to add more infrasound stations around the world. And this will, of course, if we have more infrasound stations, that makes our job easier in detecting these signals if we have a denser network. So, thank you.
Very, very nice talk, Robin. We have time for some questions. Please, Dr.
It's a naive question. Perhaps it's already known if the eruptions of volcanoes are linked. So in your data, when you are analyzing many different stations, are volcanoes that are erupting at the same time and some others later, something like that? There is a rhythm, let's say?
Yes, I mean, that's a really interesting question. We can't answer that yet, of course, but one of the ideas of this work is basically to create a systematic global catalog of detections of volcanic eruptions. So, of course, there are many methods of doing that, and the Smithsonian maintains a global catalog of eruptions, but we're trying to do it in a little bit closer to the way a global seismic catalog is produced, so a quantitative acoustic parameter. But, of course, it's difficult to do that, and right now we're only seeing basically the largest eruptions globally. So to get down to that question, we need denser networks around volcanoes to pick up these smaller signals.
Thank you very much for your talk. Yeah, last year in June, 50 kilometers from Sarachев Peak, occurred an eruption very similar. It's more or less the same magnitude of Raikoki volcano.
Yes.
Do you have some data about this or some chronology like this for Sarachев?
Yeah, so I have a student and a group of collaborators who are working on that, and it's quite funny because as you mentioned, it was almost the same time of year, so it was within a week, I think, and so the atmospheric conditions are very similar, and so we're seeing similar infrasound wave propagation. But yeah, there are certainly very good detections on the three closest stations. So
there's the next island to the north.
Yes, Raikoki. Yeah.
Yeah.
Yes, it's right here.
This one,
basically. So yeah, so there are very good signals. Yes, and the satellite data for Raikoki are very good too. So we're seeing these Himawari plume altitude, and we can see it. Each one of the eruption pulses, you can see it in satellite data, and then you can see the infrasound signal as well. So it's very nice data.
Thank you.
Is there any other question? Please.
Yes, so I guess...
Dobson?
Thank you. So I guess for the automation detection, you're going to be using template matching. So how many different templates do you think you will need to really capture the full physics of the different kinds of eruptions?
Well, so actually here with infrasound, we can't really do template matching, and that's because the atmosphere is so variable, and we have things like gravity wave perturbations, and so infrasound waveforms are just not as stable as seismic waveforms, and so we can't really make those assumptions that the Green's function is not changing. And so this is quite crude compared to the way traditional seismic detection is done. All this is doing is looking for signals that are arriving back azimuth value, and then projecting that back azimuth value back. So you're throwing away all of those interesting phase characteristics. So we have to basically use much more clumsy, robust methods for infrasound signal identification. But it would be nice to get to the point where we have the atmospheric specifications parameterized so well that we can actually get into those more detailed methods.
Yes. What kind of sensors do you use?
So we use a variety of infrasound sensors. So there are different sensors on the market, and we have some that are manufactured by Hyperion. We have some that are manufactured by Chaparral. I'd be happy to talk about different sensors, but there are several different options.
But they are similar in working at regular microphones. I mean, in the audible range.
Some of them, there's different technology. Yes, I didn't have time to talk about this. So some of the microbarograph technology, it's more like an aneroid microbarometer. So some of the original technology, it's like a deformable bellows device, which is connected to the atmosphere. So you're deforming this chamber, and then you get a signal from that. But then some of the signals are more like a regular microphone, yeah, with feedback built in to get the low frequency response.
Thank you.
Thank you. There are many other questions, but maybe we have to follow. Next talk. Thank you very much, Robin. present from the organizers. Well, next talk will be by David Dawson. He is professor of air and material science at University College London. He's interested in the mechanical properties and chemical properties of rocks, and from a multidisciplinary point of view, he's expert. He's now performing high pressure experiments in rocks, and we are glad he's going to talk now of what can seismic waves tell us about the deep interior of the Earth. So it will contribute to uncover the mysteries of the interior of the Earth. David?
Thank you very much, Alejandra, for organizing such a diverse and interesting meeting. So, it's a long title. You could also call it, perhaps, Where the Wave Field is Not Enough. I brought with me a scale model of the Earth. It's an apple. If you were to cut it in half, the core goes about halfway through the apple. Okay, so the Earth, the radius of the Earth is 6,300 kilometers or so. The core of the Earth goes out to 3,500 kilometers. Okay, so the core starts at 2,900 kilometers depth in the Earth. The skin of the apple is about the same thickness as the crust of the Earth. And the very deepest borehole that we've ever drilled is about a third of the way through the skin of the apple. Okay, so we have no direct access to the Earth's interior. And so all we have is seismic waves. Okay, this is the most important thing that we have. By far the highest resolution come from seismic waves. Okay, so we have P waves and S waves, and they have slightly different information, but basically they tell us the density variation with depth, the compressibility, and the resistance to shear strains. Okay, and shear waves also give us something to do with the anisotropy of the rock. Okay, so when you have an anisotropic rock material, then the shear wave splits into a polarization which travels more quickly and a polarization which travels more slowly. And that tells us something about the anisotropy of the rock, which is related to deformation of rocks in general. Okay, that's all the information that we have from seismology. So we can do some quite good things nowadays with very large arrays and very careful data analysis. And we can make tomograms. This is now, I'm going to be talking about the core mantle boundary, so the region from 2,700 kilometers depth to 2,900 kilometers, the D double prime region just above the core. This is a P-wave velocity tomograph for that region. And we can see that there are slow regions and there are fast regions. So generally red is slow in these things. Blue is fast, and this is for shear waves. We see very similar things, red underneath the Pacific, and blue so fast around the Pacific Rim. So that's kind of consistent with subducting slabs, cold subducting oceanic material reaching the core mantle boundary underneath the ring of fire, underneath the Pacific subduction zones. Okay, so this is what the velocities tell us. The shear waves. This is a simple, for shear waves, we have to simplify the seismic signal. Okay, we can't get the full anisotropy. So what we do is we simplify it into a ratio of is the horizontally polarized shear wave faster or slower than the vertically polarized shear wave. Okay, and for the uppermost mantle, we see that the horizontally polarized shear waves are much faster. And that's associated with plate tectonics, flow, causing the olivine crystals to align, so horizontal flow in the uppermost mantle. We see through the most of the mantle actually very little anisotropy, and then down in the D double prime region, again we see this horizontal polarization on average faster than the vertical polarization. And if we do look at the anisotropy tomographs, we see a very similar signal to the velocity tomographs with this horizontally polarized fast regions around the circum-Pacific Rim and then these vertically polarized regions in the center of the Pacific and underneath Africa. Okay, that's fine, but of course we want to interpret that in terms of mantle flow. So what we do, okay, I should just say previously that this increase here is thought to be related to the change in crystal structure. So throughout the lower mantle, from 660 kilometers down to 2,700 kilometers, the main mineral is perovskite, which is this structure here. We have silica octahedra, which are connected on their corners, and magnesium sitting between the gaps. When you compress this, what happens is the tilt increases. So these little triangular volumes decrease as these octahedral tilt increases. Eventually that becomes unsustainable, and it actually breaks down into this layered structure, which is post-perovskite. And because it's layered, it's very strongly anisotropic in many of its properties. So it's thought that the increase in seismic anisotropy is related to the stabilization of this phase. Okay? So if we knew the way that this deformed, if we knew the orientations that it oriented in under flow, then we'd be able to interpret the seismic anisotropy in terms of mantle flow. This is what this is. So these are observed seismic tomograms for anisotropy. This is assuming flow shear between the layers, which is a logical thing to assume. And it's actually probably about the best fit that we can do. And you can see it's actually not very good. Okay, we recover these red regions, but actually we have a lot of other red regions as well, which are not consistent with their mantle flow. Okay, so what we do is we take the PNS wave velocity tomograms, we invert those for density, and we turn that into an instantaneous flow field. From that flow field, that's how we get the anisotropy. So we get the texture generation and the anisotropy. Okay, and it doesn't work. Okay, it's very bad. Okay, but should post-perovskite in D double prime be deforming by dislocation creep? Probably not, because the core mantle boundary is the hottest region of the mantle. Okay, so you're closest to the melting temperature. We have a free slip boundary condition where the material is flowing on the liquid outer core. So, and the grain size should be very, very small because it's only recently transformed from perovskite to post-perovskite. So actually it should be deforming in diffusion creep. Now the problem is that the canonical view of diffusion creep is that texture is destroyed. Okay? People think only dislocation creep produces textures. But we think that it should be deforming in diffusion creep. So we have a conundrum here. So about 10 years ago, we started looking at the diffusion properties of post-perovskite. There we go. We published it in Nature. This is, post-perovskite is stable at 1.2 million atmospheres pressure, so we can't do experiments on it, magnesium silicate post-perovskite. So it's all ab initio simulations. We use vineyard theory, so we find the saddle point, and we find the energy difference between the ground state and the saddle point. This is then the activation enthalpy for diffusion. If you calculate the phonons at the ground state and at the saddle point, the difference between those two phonons, densities of state, is the attempt frequency. So we can get the full diffusivity out of it from ab initio simulations. If you do that across the lower mantle, these values for perovskite, for magnesium and silicon, and for oxygen agree within a factor of 3 with the experiments. And again, for periclase, they agree within a factor of about 2 with the experiments. So they're very, very good. So we believe these for the perovskite. But when we get to post-perovskite, what we see is that diffusion of silicon and magnesium in the 1-0 direction is 8 orders of magnitude faster than in the B direction, in the 0-1-0 direction. This is a massive anisotropy. This is more anisotropy than you get in electrical conductivity in single crystal graphite. So as I'm an experimentalist, my colleagues do the simulations. At that point, I think there's something wrong. Okay, why do we have so much anisotropy? It's more than we know for any other material. So I spent the last 10 years trying to find low pressure analogs where we can do the experiments and the simulations and see whether or not the simulations actually predict in systems where we can actually do the experiments. It's worth it. So this is, it turns out the fluoride system is very good. Perovskite transforms to post-perovskite in the region of 10 to 15 gigapascals. So this is a nice multi-anvil pressure range. We do standard diffusion couple measurements, both for the bulk and for single crystals. It's quite difficult. The crystals aren't very large. Yeah, they're maybe 10 microns long and 1 or 2 microns in diameter. But we can recover the diffusivity out of those. And it turns out that the simulations agree very well. So within that system, experimentally, we see at least 3.5 orders of magnitude of anisotropy, and the simulations suggest there should be 4 orders of magnitude of anisotropy. So across all of the systems that we worked on, and in all of the different phases we worked on, there's an agreement of a factor of 3 or better for 4 species, 3 different phases, and they span 6 orders of magnitude of variation in diffusivity. So the simulations do a remarkably good job. As an experimentalist, I'm a little bit sad about that because it means that I'm out of a job. But it means that we can believe the simulations on the magnesium silicate system as well. Okay. So we have 8 orders of magnitude of anisotropy in chemical diffusivity. What does that mean for diffusion creep? Does it still destroy textures or does it generate textures? This is just the first 9 terms of the viscosity tensor for which is the bit which is relevant for plane strain on an orthonormal crystal system. Within the post-perovskite anisotropy, where diffusion in the A direction is 4 orders of magnitude higher than in the C direction, which itself is 4 orders of magnitude higher than the B direction, you can simplify it for a cubic crystal to this, and you can see that the diffusion is rate limited by the strain rate is rate limited by diffusion in the intermediate direction, which is kind of sensible. If you want to have diffusion creep, you have to remove material from one face and add it to another face. So you're always convolving diffusion in 2 orthogonal directions. So for a cubic crystal, it means that you're rate limited by the second fastest diffusion direction. Okay. But of course, if you're deforming your crystal, it doesn't remain cubic. It starts to strain and changes shape. So if you were to stretch it with the fast diffusion direction in the stretching direction, that means that the second fastest direction is thinning, so the strain in that direction gets faster. Okay, so here we are. We start with a cube, and you stretch it, and eventually the strain rate increases massively, okay? Because as you stretch it out, you're thinning that rate limiting direction, and diffusion is dependent on the length scale squared. So you get this very strong strain weakening rheology until eventually the crystal length in the fast direction is the square root of the diffusivity difference of the length in the intermediate direction. So in this case, it's a 100-to-1 ratio. Okay, because there was 4 orders of magnitude difference in diffusivity. So you get a weakening until you get to this aspect ratio of 100-to-1. And you also make a very needle-like texture, okay? So that means you will make a strain orientation. You'll get alignment because these are needles. The needles aren't stable at 100-to-1 aspect ratio. Yeah, when you deform by shear strain, here we've got our needle. You always get some rotation. And when you have long needles like this, they don't cartwheel. They end up breaking up by boudinage. So you get a grain size reduction effect as well. Okay? And because diffusivity has a grain size squared dependence on it, then you get a very strong strain weakening rheology. So what we think happens is you start here, you get your weakening. At some point, this becomes unstable, and it breaks up. So you go more to an equant shape again. So you get another weakening from here, and so on. So you get runaway weakening, okay? This means that you're going to get strain localization. You'll generate texture. So the lower mantle, the D double prime region, the lower mantle, will end up looking rather like crustal rocks with strong strain weakening and the strain partitioning in these very highly sheared, very highly textured regions. The regions around it don't see much of the current strain. And what they see is historical texture, Okay, so perhaps the reason that we can't interpret the observed seismic anisotropy in terms of present flow is because actually d double prime looks like this, and you wouldn't expect to be able to see that with this current seismic resolution. To give you an analogy, this is Scotland. If you were to look at the seismics of Scotland, then we have a very strong southwest northeast region here, which is all related to the Caledonian orogeny. So this was the closure of the proto-Atlantic 500 million years ago. In this region, below the Moyne Thrust, this is all Lewisian gneisses, which are 3 billion years old, and they have a strong texture which runs this way. And this is about a 1.2, 1.4 billion year old texture. Okay? So if we looked at this with seismics and try to interpret that in terms of current plate tectonics, we'd be on a hiding to nothing. Okay? And this is actually what d double prime is like. All is not lost. Okay? These very strongly anisotropic regions of local shear will be very strong seismic scatterers, but I'm afraid that'll be another half an hour to explain that, so I'll finish there. Thank you.
Thank you very much, David. It's very interesting. The experimental work, so you work with very tiny samples and a very high temperature or very high pressure as well. So this is a very, very frontier subject. There is a question, please, Don.
What is the iron content down there? And is there any conceivable role for redox state in influencing any of the considerations?
So the iron content is probably quite variable in the d double prime region. It appears that the regions which are seismically slow, the large low shear velocity provinces, need at least some chemical heterogeneity in them. And it's thought that they're probably enriched in iron. We don't know how much by. Perhaps maybe it's 20% iron rather than 10% iron. The main effect that might have, and the oxygen fugacity might have on the rheology, is the effect on the extrinsic vacancy concentration. We think under these conditions it will probably be dominated by intrinsic vacancies. So within perovskite and post-perovskite, you can charge balance ferric iron by putting ferric iron on the magnesium site and aluminium on the silicon site. And that seems to happen within our experiments. So it seems as though there aren't many extrinsic vacancies, and it's probably an intrinsic vacancy concentration which dominates. So under those conditions, probably oxygen fugacity won't have a very large effect.
Okay. Is there any other question? I'm wondering, the anisotropy you found can be extended your studies to more shallow materials, which are of interest in the oil industry. So all your studies are for tectonics, but you study the whole mantle boundary. But in the case of oil industry, you think your experiments can be adapted to shallow conditions?
Yeah. So once you're into the oil industry and sedimentary rocks, anisotropy is often produced by sedimentary layering rather than by deformation. And I think that's quite well understood. But you're right, this concept that anisotropic chemical diffusivity produces anisotropic creep is very important for low pressure things. So one technological application is certain printed circuit board fail by what are called growth of tin whiskers. So when PCBs are coated with tin, then the tin is anisotropic in its diffusivity. It's a tetragonal structure. And where you get the crystals oriented in different orientations, the differential strain between them causes growth of a very thin whisker of tin, which eventually collapses and can short across the board. An understanding of tin whisker growth is basically an anisotropic diffusion creep process. So it does have low pressure, potentially quite big applications.
Okay, thank you very much, David. Please give us a big applause.
And now I get to eat the earth.
You can eat your apple now. Well, we have now the talk of Dr. Donald Bruce Dingwell. He's an expert in magmas. He's going to talk about waves in magmas, and his research areas cover geomaterials, experimental geosciences, geochemistry, geophysics, petrology, silicate metals and glasses. He gave a course for the students here, and we are glad that Don is giving us a talk. He recently, so last year, he got the Doctor Honoris Causa from this university. We are glad Don is giving us a presentation.
Thank you very much. It's, of course,
one moment.
Great challenge to speak and type your password in at the same time. So, somewhere behind there is what I want. This is not it. This is it. Okay. So thanks very much to Alejandra, who has brought us all together here. It's been very invigorating, very refreshing. And I'm very impressed with the quality of the participants. It's clear that we're dealing here with people with some really great minds in the room. That's okay, because as a child I had 3 older sisters and they were all smarter than me. So I got very comfortable with being surrounded by people smarter than me, and it's been one of the secrets of my success. So I responded to the order of Alejandra to talk about waves in this way. Actually, making waves in magma, you probably know that that's a double meaning. Making a splash or making waves means having an impact, at least an apparent impact. But I'm going to point out to you that magmas can also carry waves, and that these waves may actually be quite relevant for how eruptions are triggered. So if I step to our friend Mr. Humboldt for inspiration, you don't have to look long. If you Google Humboldt volcano, you will immediately be have images thrown at you where the role of this remarkable property that magmas have, which is to bring mass and energy from the depths to the surface at great efficiency, that this was obviously a central belief that Humboldt had. I think much has been written about Humboldt's perception of volcanology and the Earth system, and how after his time this perception was altered. And of course we all remember what we've already been told, which was that within his generation, of course, he went from a sedimentary Neptunist view of his teacher for the origin of basalts to one which was utterly different. So I really want to bring Humboldt's love of volcanism back to the center of the Earth system sciences, and I've been working at it for decades now, and I think it's beginning to take hold. So this is a really simplistic, this is the first diagram I put in a proposal 10 years ago to the European Research Council, saying that eruptions are not only the problems of risk and hazards, they're not only the opportunity of volcanologists, they're actually a very central part of major exchanges within the Earth system. And eruptions are basically the way that the lithosphere we're standing on talks to the biosphere, the hydrosphere, and the atmosphere on a punctual a very extensive basis and a very continual basis, dozens and dozens and dozens of times a year. So basically a constant background, if you will, in the Earth history, in the Earth system. And of course, we're always trying to break things down into simplified models. That's the way that we work in experimentally. You're almost always working deterministically, and therefore we break it down into a very simple model. This is in German, but I'll just briefly say what is here. The fundamental matter of lavas which are coming to the Earth's surface due to the conditions at the surface of the Earth, our particular planetary pressure and temperature at the Earth's surface, almost inevitably yield a system which is saturated in a volatile on the way up, which creates nucleation and growth of the bubbles of that volatile, and even foaming as you get it, obviously in pumice, which is delivered in many volcanic eruptions, and a fragmentation. I won't say anything about fragmentation because that's Betty Shoy's presentation, which she has asked me to present on her behalf afterwards. She's ill. Sorry. Okay, so the basic notion of how we move these magmas is that there is a twofold nature of these magmas, that we have the ability of these magmas to flow, but that it is limited. And that beyond the ability of these magmas to flow, we switch into an entirely different regime, which is the dusty gas, which is solid materials being carried by a low viscosity fluid phase. And all I want to speak about now is a few words about this side of the diagram, and later Betty's contribution will be entirely about that. I hope it's the last time I do that. Okay. If there's anybody in the room who hasn't seen volcanic ash before, there it is, an SEM shot on the upper left, showing the fantastic textures that we get. Incredible anisotropy of porosity, loads of kinetic information if we're intelligent enough to remove it all and classify it all. And of course, on the right, the world of the petrologist, where the optical examination of materials reveals beautiful regular single crystals, which are also forming fragments of ash, and also beautifully irregular forms of glass chips, plates, and so on, which were bubble walls. That's the stuff that's coming out of Popo when it produces ash. So we try to characterize how waves can pass through volcanic melts and volcanic magmas by controlling the viscosity. And we can get information on the passage of waves through melts by looking at the damping of the viscous damping of the waves. And you see here two experimental methods for determining the viscosity. One is a high temperature, so-called concentric cylinder viscometry. If you ever had to do a viscosity experiment in high school in physics, you probably did this with some motor oil or something to demonstrate the principle of viscosity. And on the other side, because of the extreme range of viscosity, which you're about to see, you have to appeal to techniques which are essentially solid state deformation techniques, creep experiments, kind of thing that David would be very familiar with, because we can also make the glasses creep just above their flow point. And you end up with a picture of the, first of all, the bulk chemistry of terrestrial liquids. These are 10-component liquids. They have 2 alkalis and silica. Silica goes from 40 to 80. That's a huge range of chemistry that the Earth gives us. And the alkalis also go from a few percent all the way up to almost 20%. Also a huge range. And these 2 chemical factors largely contribute to the variation of the viscosity. And you can see here the viscosity variation, where every color corresponds to a single chemistry over there. And this is many, many, many years of work to produce it. And you can see 2 ranges of data, which refer to the 2 experimental techniques that I showed you before, the high temperature, low viscosity, and the low temperature, high viscosity. And there is a gap between, because here you have the problems of instability of crystallization, because these are metastable determinations. So just to point out the vertical scale, we go from about 10 to the 0 to about 10 to the 12 Pascal seconds. So we have about 12 log units of viscosity. And next to electrical conductivity, it's perhaps the most variable bulk feature of rock masses within the Earth. And it's highly dependent upon one variable, which we know is highly variable during volcanic eruption: water. In the beginning, at depth, there's a lot of water dissolved. This is weight percent of water, weight percent of water. This is the log of the viscosity. And at the surface, when we have these pyroclastic materials thrown out at us, we know we have only about 0.1 to 0.6 weight% of water. And the journey from the right to the left is one of constant viscosity at the beginning, but then as you see, just as you approach the Earth's surface, suddenly the viscosity starts to increase because the water, which is the primary volatile influencing viscosity, leaves the liquid chemically and diffuses into the growing bubbles, doing its job as it should, but leaving behind a dehydrated liquid. And with a high silica liquid, which is the classical composition of an explosive volcano, this is the reason that it is, because the viscosity jumps, and now you have to push that material, which is logarithmically increasing viscosity, more or less at the same strain rate as all of the low viscosity stuff below. It's all attached, it's all connected, it's all coming up. And it's that exponential growth in the stress which is required to push it, which creates the greatest problem. So you can put waves through melts. This is from a book we published 25 years ago. This is an experimental apparatus of Sharon Webb, who I met about 35 years ago. And basically, you can send acoustic information and acoustic waves through the melt phase. And most people will say, well, yes, I know that. With longitudinal waves, which essentially have a compressional component to them, it's well known. But you can also do it with shear waves. And that you would say to me now, I hope some of you better physicists would say that's impossible. Liquids don't carry, have rigidity, they don't carry shear energy. But it's a question of the frequency dependence, and if you do high enough frequency transport of shear energy through silicate liquids, then you can indeed send send acoustic waves of a pure shear character through a silicate melt and get a value for its shear modulus. And here you have a plot of signal amplitude coming from that device of Sharon Webb, where you see, obviously, you can read off of here very nicely what a wavelength is. You have an acoustic sensor, which gives you a precise frequency that you're monitoring. You have the frequency and the wavelength. You can obtain the speed of the waves. And from the speed of the waves, you can obtain the elastic constants of the material. And, excuse me, at the top, you can see, if you look closely enough, that there is a damping, that there is a fall in the absolute height of the returned energy, so that if I fit a curve to that damping, I can obtain a viscosity from these experiments as well. And of course, there is also dispersion in these experiments. There's a frequency dependence of the result that you get. This is the so-called inverse of the Q factor, the quality factor in seismology. And you can see that it depends on frequency. This is clear indication that you're playing with the relaxation of these systems in a region where the self-diffusion of the actual liquids is taking place. And there's a vast literature in the crystalline world on bulk modulus versus volume, modulus volume systematics. The modulus is roughly inversely proportional to the volume, because some things with larger molecular volume or molar volume have more room to compress and therefore have a lower modulus. Large volume, small modulus, okay? These are for glasses and liquids. Okay, and ultimately, as I mentioned earlier, the volume models that we use for calculating all these things for silicate melts are derived from measurements of density, which give you the very first coefficients here, the partial molar volumes in all of the major oxides that we're interested in silicate melts. But the DVDP data, which you see here, come exclusively from these longitudinal wave propagation studies in silicate melts that were basically largely concluded in the 1980s. So that's all for liquids. Now I want to show you an unpublished thesis. Parts of it have been published, but I've gone back to the original source by Itai Kurzon of the Hebrew University in Jerusalem, working together with Oded Navon. He published a thesis called Viscoelastic Bubbly Magma, Implications for the Nucleation and the Growth of Bubbles, and so on and so forth. Now, nucleation and growth of bubbles is something which is intrinsic to the processes of pre-eruptive ascent in magma conduits. And knowing whether the nucleation is taking place at depth, whether it's taking place in the conduit, has all to do with determining what the driving force and the stress distribution is to bring these things to the surface. And the notion that the viscoelastic response of bubbly magma, the mechanical response, could have implications for nucleation of bubbles is a very interesting one indeed. Because out there we have seismicity traveling through the crust. Whenever there is a significant earthquake, and especially if there's a significant eruption. And there are also, out there in a country like Mexico, all of these latent magma chambers which are distributed within the crust, the Mexican crust. And if we can send seismic energy into these magma chambers, been postulated a long time ago, that you might actually have a trigger for destabilizing, for unsettling these liquid bodies, largely liquid bodies, which are nested in the crust. And so the question is, how critical is the state of magma below our feet? In other words, is there a certain amount of excess energy which I require in order to push this system out of its stable regime and into eruption? And we don't know the answer. We really have no idea about the order of magnitude of energy input that might be useful as an eruption trigger. And what we're talking about here now is essentially triggers from without, external triggers. And this is a fascinating area of modern volcanology. Can we classify eruptive events into those which are basically inherently or endogenically triggered from their own differentiation of the magma, which causes a lot of stress due to phase changes? Or are those partly caused by external additions of stress, which then can potentially even induce a phase change? So the notion that you can induce a phase change, in this case, nucleation of bubbles by seismic energy, is the whole message that Curzon added to the discussion. And of course, his whole way of arguing is to discuss what we call mechanical elements. So combinations of storage of energy using these components, which are springs, elastic springs, and these so-called viscous dashpots, which are purely viscous energy loss moduli, okay? And by the combinations that you can imagine, these probably remind you of electromagnetic circuits. It's exactly the same logic, where here you have your capacitor and here you have your resistance. And by building these together in various combinations, you can estimate what kind of response would occur if you put now a sinusoidal stress front into the magma by adding, for example, longitudinal waves into the system. And you can also evaluate the damping of these waves as a function of frequency. And I hope you can appreciate from the shape of the lines that there can be very interesting journeys. I think I'm losing my power, yeah. There can be very interesting journeys from the low frequency up into the high frequency, where you can even have different frequency dependence of the rate of change of damping as you go from low to high. And so the basic idea is that you have a bubble which is growing, or you perhaps have an oversaturated liquid which has not yet nucleated its bubbles. The oversaturated liquid is one which is inherently unstable. All it needs is some energy to be put into the system, which will allow the nucleation to effectively overcome the surface tension, which is trying to stop nucleation. And so the big question is whether or not seismic waves can generate this in magmas. And it will be a question which is fundamentally answered by answering the question of what waves in magma are capable of doing. This is just one curve which shows you the bubble growth law. I'll just fly over it because any of you might have questions related to it, and you might also be inspired to think about this. In the beginning, we have the nucleation issue. We have to overcome surface tension, which is trying to stop what we're trying to do, which is nucleate a bubble. Then we come into a viscous regime so that the viscosity plays a big role, because the viscosity controls the retraction of the melt out of the space which the bubble is about to occupy. And then we go into a square root solution, diffusion, and finally get up to something where there's been a depletion of the reservoir for the growth of the bubble. Okay. I'll read this sentence to you from Curzon's thesis. The initial analysis of the results indicates a correlation between bubble growth and the intensity of the pressure signals obtained during growth. However, more is required. So we're trying to do this in Munich. We're trying to put sinusoidal loads on magma and see whether or not we can generate bubble nucleation as a result of that. And if we can, then we may answer what has otherwise been enigmatic, which is how very, very external seismic energy can be responsible for triggering eruptions. I just finished with 2 more slides. Paco, have mercy on me. Somebody else showed a slide very similar to this earlier. These are all cartoons. Humboldt could have drawn most of these things. He probably would have done even a better job. So we don't have any idea in detail about the texture and the wavelengths of lava storage in the crust. And when we think we know, as in the case of Krafla caldera, where it was predicted that at 4.5 kilometers there was a sill of active lava, it was drilled and it was intersected at 2.5 kilometers. I mean, that's very embarrassing to me as an earth scientist to tell non-earth scientists that we miss it by a factor of 2 within 2 kilometers of the crust. Remember what Dave Dobson was just talking about. So the idea is that if we've accidentally intersected this magma at depth, then why don't we depart on the radical idea that we can do it on purpose, that we can go into an active sill and we can stay there and institute sensors and perhaps even go in twice and through the one drill hole put in acoustic waves into the magma and in the second one see what arrives. Manipulate this relatively small and controlled volume of a sill in Iceland and see what happens and see whether we know what we think we know about these accessible and relative shallow magma bodies. The financial reason it might take place is because it's high enthalpy geothermics, which one can obtain if one approaches but does not enter the magma. And this is a big push in Europe now to try to develop these high enthalpy geothermics. So you may, in the next 10 years, hear of people drilling into active magma to test all of our wonderful theories and answers that we believe we have on the evolution of magma in the crust. Thank you.
Thank you, Don, for this exciting talk, touching the frontiers of knowledge.
I hope.
We have time for questions. Dobson, David, please.
So I guess what you're talking about with the seismic thing, from what I could tell, a lot of it was based around homogeneous nucleation. Once you have crystals, and particularly broken crystals, presumably it's much easier to start to nucleate bubbles. So do you see a much higher sensitivity to seismic effects when you have a bubble-rich magma?
So we don't know yet. I would have my own prejudices, but they'd be nothing more than that. I might anticipate that the homogeneous is more reliant or dependent on external triggering. But the idea of experimentally testing is to do both cases. And we certainly know from early nucleation studies of Hurwitz and Navon that it's very phase specific. So it's a lot of petrology in there, which is always very attractive for people trained in that.
Any other question? As you see, this field is, I think, is strongly nonlinear and very difficult to grasp all the consequences, but it is a challenge to do that. Please, your question.
Thank you. Very interesting. Thank you very much. I have a question about the last thing that you said about for drilling a hole near an active seal. And couldn't that trigger perhaps a volcanic eruption if you alter the strain?
Yeah, locally.
Yes.
The stress, yeah.
Yes, the stress.
Yes, indeed. And in a way, that's the question we're asking. I mean, when we say volcanic eruption, you probably know that we can be talking about the volume of material in this room, or we can be talking about thousands of cubic kilometers, right? So really our vocabulary in volcanology puts together things in one phrase which are almost fundamentally different things. Yeah? So would we trigger something large with this? I find it highly unlikely because I think the system will adapt to this local perturbation of its stress. Will we trigger something small? Almost certainly, and in fact that's the hope, that we can actually see exactly what we're capable of triggering and what we're not capable of triggering. When they drilled the initial holes in Krafla, they jammed, not surprisingly, pulled the stem, went back in 24 or 48 hours later and met the foaming lava coming up. So clearly you can trigger an eruption on that scale. But it's something we have to discuss between us as scientists and not run out of the room and say we'll trigger an eruption, because they will immediately multiply it up to 100 cubic kilometers, which we're not going to trigger. The reservoir is simply not there. The point being, we don't know exactly in detail how the magma is going to respond. That's exactly what we want to know. That's exactly what we want to know.
That reminds me the butterfly effect. So we hope it's just tiny
Well, I think my question had a lot to do with that also, because I remembered that Krapla eruption, well, actually, even before the eruption, when they're actually drilling and then cut into the lava, into the magma at a certain depth. At that time, could we go back and look at that data again with this new information and probably come up with some of these other parameters?
I think it would be certainly worth trying, yes, yeah. Because our physical view of these things is vastly different now, yes.
Yeah. So the risk is not so big. So you have any other question? Okay, thank you very much. Oh, please.
At the beginning you mentioned that eruptions were a way in which the inner part of the Earth was sharing its composition with the outer part. And my question is, so you mentioned some of the elements. I was hoping to see very heavy elements, and perhaps the density of the atoms that you're giving is telling you how deep the lava might be. I don't know, it's just curiosity that.
Okay, I'm not sure that I understand you, but we're dealing here with a 10 major component solution. It's a simple solution. It's a high temperature liquid. Its density does vary. The biggest component in varying the density is its iron content, next to all the others, because through the vagaries of nucleosynthesis, we get a lot of iron on the Earth, and it happens to be the one with a higher density, stable. But beyond that, relating the density of melts to the depth of their origin, you know, in a very crude way, it will probably work. But the iron content of the liquid depends upon the differentiation of what we call the differentiation of the system. And the differentiation of the system is the crystallization and extraction of crystals, and therefore the generation of lavas of an altered chemistry. And that's really what controls the evolution from great depth to subvolcanic depths. So we go typically from very low silica contents and high magnesium contents up to systems which are more enriched in silica and therefore have slightly lower densities and may have higher or lower iron contents depending upon the exact crystal phases which have done the job of differentiating it. That's the whole world essentially of what we call magmatic or igneous petrology, is working out the details of the sequence of liquids generated by crystal fractionation. And that's essentially what controls the density of the final liquids which are available for volcanic eruption. Some systems do it very efficiently, very rapidly. Basaltic systems, for example, you can literally have differentiation in lava flows. They can fall from the top to the bottom. And other systems, the highly explosive ones, have a terribly hard time differentiating at the late stages because they're so viscous, and physical mechanisms of extracting the crystals are very damped in time. And much more.
So, please give us a big applause to Don. So Don is going, Bettina Shaw is unable to be here. She's also at LFU, and Don, on behalf of Dr. Shaw, she's working on fragmentation. Yeah. He's going to present on her behalf about the story of explosive volcanic eruption. Please.
Okay, so my apologies on behalf of Bettina Scheu. Bettina Scheu is a scientific officer at the University of Munich. She's been there for 20 years, and she runs our lab of explosive volcanism. And our mutual colleague, Christian Montanaro, is also here, is going to speak later about phreatic eruptions. This is a unique facility worldwide, and people come from all over the world to do experiments in it. And I will say, I hope to say what Betty would have said. She's gone into Humboldt's life a little more deeply than I have. I don't think I need to go into this in any detail, but it is to remind you that in a time when he was a young man and being trained to be able to inspect mines in Upper Franconia, he was much better at that and could be trained much better at that, at recognizing gold and its grade in a mine and minerals. then he could talk about the origin of volcanism. At that time, it was a nice intellectual or academic pursuit, but on the other hand, they were training geologists for other reasons. And frankly, 25, 35 years ago, I was being trained in Canada for looking for gold mines, so it's not that much different in the meantime. You know better than I do the fabric of geoscience and all the challenges it brings with it. So there was Nepionism versus Plutinism, and poor old Humboldt was a student of Abraham Gottlob Werner, who was really viewed as the father of geology and of field studies of geological environments in Germany. And of course, that had to be worked out first before one could argue back and forth about the theories of rocks. One had to have this critical observational ability, and it is my understanding from being an import into Germany that that is essentially what Abraham Gottlob Werner did for us all. Betty has now gone into it in even greater depth, and of course she's referring to what's already been shown here, and I'll jump over it. Basically, here's Jorullo, and here Pichincha. So he was all over this place and had lots of ideas about volcanoes, and people have been whispering to me for decades that he had lots of ideas about volcanoes, many of which have not withstood the test of time. And here you have the same picture I showed earlier, so I will jump on. This is a reference to what I just said about the differentiation. These are paths of chemical variation of magma based upon the participating crystalline phases which can occur in magmas. So this is the fundamental paradigm which was finalized in its acceptance at about 1945 to 1955 by an experimentalist who demonstrated that he could match the chemistry of rocks by looking at how they crystallize and differentiate in the laboratory, a guy called Bowen. And just a word, I always try to provoke my fellow volcanologists, because I'm not really a volcanologist, and I'm sure Betty's trying the same thing here. You have this tremendous playing field of phenomenology, of volcanology, which is the reason that a lot of people get into it. It's absolutely fascinating what you can see in terms of the kinematics and the deformation, which is clearly behind the events. But basically, all of what you see is in some way a reflection of a very small number of properties of the lava, and the foremost being, of course, the viscosity of the lava. And of course, they lead to a range of results as a result of the energy concentration and the distribution of strain which occurs in these eruptions. So Betty's experiment basically consists of doing this part of the story, of actually turning a bubbly liquid at depth, which is what lava is, into what we call a dusty gas. And didn't you ever want to work on something that sounds as cool as that? Bubbly liquid, dusty gas. Wow, there's a lot of physics going on here, right? And physicists who have not yet encountered volcanology are almost always excited about the playing field of classical physics, which a volcano really is. And there's very few examples, unless you go into biology, of course, where then the biophysics gets really exciting, which have such a variety on the Earth's surface. I mean, sedimentation is great, but it's not as complicated as what's going on with the materials in volcanoes. Okay, this is our experiment. This is, so if Betty was standing here, she'd come up to about here. And this is a top part, which is the atmosphere. It's called the capture tank. And this is the bottom part, which is called the autoclave, which is basically the magma chamber. So like any experiment, it's very simple. Magma chamber, atmosphere. Okay, just like the volcano, we hope. There's lots of questions you can ask. How much pressure? How fast? How fine is the material which comes out? And we developed terms for those over the last 20 years. That was a fun task in English of saying, what will we call this? The variation of grain size density, we call the efficiency. The amount of pressure to do it, we call the threshold. And the speed and the permeability, of course, also play a role. There's two big players, of course. There's the strain, which is essentially going to do the job. The strain rate is going to be very critical in whether we can fragment rocks or not. And of course, rate is not enough. You need the essential magnitude of stress in order to overcome the strength of the rock. And those are the two things that we try to control very carefully in our experiments. And this is the list of topics which Betty would try to take us through. She's going to talk about, or I'm going to talk on her behalf about the threshold and the influence of permeability on fragmentation, if we can get to it. Okay. So this is the threshold. There it is. After hundreds of experiments on at least a dozen different kinds of rock here. Now I've truly lost my... So on all these different rock types, which are highly different chemically, which have different crystal contents, different silica contents, have erupted in different ways, from lava flows to explosions. If you try to measure the tensile strength of the rock, of a vesicular rock, a bubble-bearing rock, you can plot all the results versus what? Bubbles. Nothing to do with the rock itself. Okay, just the void spaces. So for petrologists who spend their whole life picking apart the condensed phases of rock, this is always very depressing. And I was trained as a petrologist. So anyway, it goes from about 3 or about 30 bars, if I can use bars, 30 atmospheres, up to about 300 atmospheres. That's what it takes. So if you can decompress a lava at a high enough rate, and if you use up to 300 bars, you can pull any rock apart, essentially. If it's a highly porous material down at 70 or 80% porosity of pumice, then you can pull it apart with only 30 bars. That is for solid state Earth scientists. That's very little pressure. Okay, so they're always amazed at how little pressure we're inspired here. The whole thing depends upon permeability, because the pressure which is contained within the experiments is delivered by the pressure times the volume of the bubbles. The gas pressure in the bubbles times the volume of the bubbles gives us the potential energy in the system. And so if we have extremely high porosities, which is the range up to 80%, which we experimentally investigate, the question will certainly arise in many of your minds, hey, why do you need to break the rock? Why don't you just let the gas bleed out of the connected bubbles? Because at 80%, you can reasonably expect there's some permeability between the bubbles. And you can, but it turns out that the permeability expresses itself as anomalies in this diagram. Outliers, as somebody would have said the other day, which I do not believe deterministically are important, but we can explain them. So what we have here is apparently high fragmentation thresholds, but by the time that these high permeable samples have actually been fragmented, there's been a gas loss ahead of that, so that the delta pressure is already reduced back down onto the curve. And so you can nicely explain that based upon a tremendous amount of work to measure permeability of every single fragmented sample before we fragmented it by a PhD student, Sebastian Miller, who admirably did that unsteady permeability measurements. So permeability plays a role, but we can tame it. We can put it in the cage at low permeabilities. It's logarithmically varying, and we know exactly when it gets out of the cage and starts causing problems for us. And we must remember that volcanoes are degassing all the time, that the normal state of a volcano is not eruption. That eruption is a mistake, an accident, something which went wrong with the volcano, and that gas decides to take the mountain with it on that day. Okay. I'll just show you some videos to make sure you truly appreciate how these experiments look. This is what's happening when we decompress lava. We do it at 1,000 degrees and at the pressures inside volcanic domes and with dome rocks. So we're there with the right material, the right time scale. And basically, that's what happens. It tears itself apart purely by decompression from above. Because the bubbles still have the pressure has gone above, the delta P is between the internal pressure bubbles and that which was above. And above, you can see one more example of it. You can see this one will now decompress to the left, which is up. You can see the ash being formed. It's the only people in the world who really make volcanic ash in the basement. And that is new volcanic ash made from volcanic material, just like volcanoes do it. And you can see that there's a lot of potential for image analysis and reduction of this to understand all of the parameters that we need to describe the vagaries of flow of these materials as they're coming out of an exploding mountain. We should not be surprised by that. We're really not surprised. And then we actually get the pyroclastic products, and we can actually measure it. We can measure the dynamics and take pictures of it. These are high-speed videos of a few milliseconds of an eruption in our lab. And here comes the pyroclastic cloud. And this is the same stuff which is coming out of Popocatéptl if it goes up, or even if it has less energy and it goes down in the deadly way, going down the slopes in the form of a pyroclastic flow of sufficiently high density. So you can see, I hope I give you the impression that we can make a science out of these explosions. Now we can look at their dynamics, we get all of the stuff afterwards, We can characterize the grain size distribution, characterize the amount of surface we have created. We can estimate how much energy that took out of the system. We get the ballistic energy. You can really start to build the eruption back together in an energetic model for the eruption. And Miguel Alatoro, who is here in the room, was one of the pioneers of all of this when he was doing his PhD in Munich. And there's the freshly created ash. So this would look like the surface of a car if it was downwind of an ash eruption anywhere in the world. But this is stuff that we've made. We know exactly how we made it. We know the delta pressure. We know the chemistry, and so on and so forth. So one of the great exports of this lab is ash for experiments, because ash in the Earth system is, I would put to you, one of the great challenges left in understanding how volcanoes influence the Earth system. It's basically ash and gas which is doing the job if it's a global effect. And being able to make it under controlled conditions and in a well-characterized way is a very different story than going out and scraping it off of some surface in nature. Also absolutely necessary, but only by the comparison of the two can you subtract out effects of reaction and transport and all of those other things in between. Okay, this is just to show that the speeds that we get for the fragmentation, we can measure the pressure drop below the sample and the pressure drop above the sample. Sorry, above, no, it's dying again. We can measure the pressure above the sample, and we can measure the pressure below the sample. This one is disintegrating. And in a very simple way that any 10-year-old would tell you to do it, the speed of movement of the front can give you an indication of the energetics of the system. And we used to call these pressure waves, and then we were hit on the hand with a stick and told we're only allowed to call them pressure fronts because there's no restorative force associated with them. They're a one-way phenomenon. So you see the pressure drop curves in green above, in blue below, pairwise for different experiments. You see that the speeds of the fragmentation, of the disintegration of the magma in the volcanic neck are pretty low. We even have lower estimates in this. So we can get it down to tens of meters per second. We're almost down to the speed with which we believe magma is delivered to volcanoes from great reservoirs at depth. And this may simply allow us to explain why we have what we call explosive eruptions that run on for days and weeks, because the supply rate is roughly in equilibrium with the processes which are evacuating it from the volcano. So we have some sort of eruption front, fragmentation front, which is rattling away at depth, maybe changing its depth over time. And someday, we may be far enough with acoustics, with seismics, and with the physics of these materials that we can put it all together and actually define an eruption lifespan in terms of exactly what happened during those days or weeks of the eruptive system. Okay, I'm going to jump ahead to the summary. Magma fragmentation, I would say it's the defining process of explosive eruptions. We have it because of these peculiar or particular properties of the high silica liquids, which upon dehydration become ridiculously viscous, and essentially the stress that you would need to viscously flow them overrides the strength of the rock. It could not be much simpler than that. And so the shortcut is taken. You give up on viscous flow, and you simply go through brittle failure, okay? The experimental approach has allowed us to say a lot of these things, and it allows us to put the orders of magnitude of these processes into a quantifiable form. And this is a field, volcanology, which basically did not have this experimental side in a significant way. There were a lot of fluid dynamics experiments before, but nothing approaching explosive processes. So we think that we've sort of added the third leg to the stool, which gives us a stable platform on which to understand these things: simulations, observations, and experiments. Every university vice president would say, of course you do. But if you've gone to, and if you go today to most geoscience departments, you will find a lot of them which do not have an experimental part of their department. It must be very difficult to explain it to the vice president how they do modern science without it. Am I being pessimistic, David? It's gotten better over the years, right? Okay. The fragmentation threshold and speed, I've told you. The fact that permeability does reach in and take over and deny us large explosions, thank goodness, most of the time. The efficiency I didn't go into in any great detail, but I'll say to you simply, as we add more overpressure, we get finer material. So we have more energy available, and we put more energy in developing free surfaces. And if we go to higher temperature, we actually see a decrease in the grain size distribution. We see a decrease in the fraction of fines. We suspect this might be a little bit of viscous deformation, still possible at a higher temperature. Goes in and robs us of a few percent of true brittle fragmentation in developed surfaces. Okay, I'll leave it at that, and I hope very much that you have some suggestions and questions. Thank you.
Very interesting and very challenging. I imagine there are some questions.
I can play a video. I can play a video while we ask for the questions.
Yeah. It's similar.
It's the favorite, my favorite video. So here you see an experiment. It's about to show you what you already saw. But Miguel will remember this. He was there at the time. We thought we had a malfunction of our high-speed cameras until we sped up the rate of exposure and discovered that we were generating what we define now as near vent lightning without having any we went to the Institute of the Physics of Lightning, which there is in the Technical University of Munich, of course, and we said, "Hi, we've seen lightning experiments. I don't know, did you go over and talk to them then, Miguel? I don't remember who did." And I think the first question they asked you was, "Great, what voltage did you apply to the experiment?" We said, "We didn't apply any voltage." And apparently this was a big deal for the lightning physicists to realize that there are other ways to do lightning experiments. It made their day, I think. Okay, thank you very much.
Thank you. Thank you very much, Don. There is a question by Anna Lillian.
I wanted to know if you could go on a little bit about the higher temperature that you were mentioning, with the grain size and the fragmentation.
So we simply observed that when we went 600 to 800 to 1,000 degrees, that we can measure the grain size distribution very precisely. We don't get the entire grain size. We don't get the entire sample, I have to confess. With a 3-meter tank and with ash, which is going down to micron size, you can wait forever and you will not get all of it out of suspension in the air. So we do wait for a while and then we wash down with distilled water and then dry it out. And we get 99 I don't remember the exact number, 99.6 or something % of the mass. That's not a problem. But the surface area, that's where we're probably far lower. But as far as we can tell from the fraction of the surface area that we get and from the portion of the curve which is more coarse and therefore completely sampled, it shifts to a lower fraction of fines as we creep up towards what is the glass transition temperature of the system, essentially. And even though we're going at very high decompression rates, I didn't show you, which should keep us away from any kind of viscous possibility, because viscosity requires time, we just have the suspicion that there are parts of the system that are somehow able to respond and relax a fraction before they are destroyed by fragmentation. If any of that can creep in, for whatever reason, whatever origin, we will not get that part in terms of the efficiency of fragmentation. The energy is lost by squeezing the sample somehow. In fact, one part of the way we do the experiments is we make sure that the samples are in there and heated up to a temperature where the matrix glass is liquid, such that it can relax into the container so that there are no stored stresses before we do the experiment, because they would distort our results. And every rock which you can pick up has stresses in it. And we have to get rid of those before we can then apply the stresses that we want and precisely have an independent variable that we can use to plot our results.
Well, very, very interesting. And as I say, used in the frontiers of science, in the frontiers of knowledge. Definitely different. So let us give us a big applause on behalf of Betty Shaw. Next, to Betty, yes, and also for you. Now, Miguel Alatorre Ibargüengoitia, who works on this subject for his PhD, and now He works as a researcher at the University of Science, Arts of Chiapas, at the Institute of Research on Administration of Risk and Climate Change, which is a very, very broad responsibility. He will present us a nice talk about pulsating volcanic eruptions with very challenging results. Are you ready? We have a technical problem.
Okay, thank you, and thank you, Alejandra, for the invitation. And I'm going to say a few words of how all these experiments translate into the nature. So I'm going just to show you how all these things show into the surface during the volcanic eruption. So I'm going to show you just some videos of these volcanic eruptions when we see the manifestations of all these processes that Don was talking about fragmentation and ejection of the particles and all these things. And one thing that I'm going to focus is about these pulsatory volcanic eruptions. So when we realize that one apparently single event in reality is comprises of several pulses. And this has been observed in different types of eruptions, including Strombolian eruptions and volcanic eruptions, but probably it's also a feature that we can also observe in larger magnitude eruptions, but probably we have not looked into that with great detail. So for those of you who are not volcanologists, I'm going to show you just a video of the kind of eruptions I'm talking about. So this is a typical Strombolian eruption from Stromboli volcano, which is very short-lived. And this is a volcanic eruption from Sakurajima volcano in Japan. So you also see the incandescent material that are ejected as ballistic projectiles. And this, again, sorry. This is the ballistic projectiles, or the lava fragments that are ejected. This black part is the volcanic ash, and then we have also a lot of lightning. That's the one that don't show in the experiment. And this is the kind of eruption that we have had frequently at the Popocatépetl volcano during the last 25 years frequently. But during the last 10 years, we've been using also high-speed cameras to look at these eruptions and look into more detail. And I'm going to show you the video of a Strombolian eruption, like the one that I showed you at the beginning, but looking with this high-speed camera. So to see a jet that is very similar to the ones that we are producing in Munich in the experiments. And you also see that this is, even when this is a very short-lived eruption, this is in reality comprises several pulses of material. But now we can look with this with the high-speed camera. We didn't have this temporal and spatial resolution before. So we can see all these magma fragments and this ejection, which is very, very remarkably similar to the experiment that we're doing in Munich. So when we look at the speed, at the ejection speed of each of the individual particles, we have this. So if we zoom in, then we can distinguish these individual pulses. Another interesting observation, well, here we have also this pulses. This is a different event. Another interesting observation is that usually Strombolian eruptions, such as the ones that I showed you at the beginning, were supposed to have the ejection velocities in the order of 40 to 50 meters per second, and actually that was part of the definition of Strombolian eruptions. But with the high-speed camera, we can see that even these small eruptions can have much higher velocities. So this shows us that the way we measure and observe different phenomena controls how we analyze them and make our characterization. Another interesting observation is the pyroclastic collisions that now we can look, and this is also related with the pulsation, because the collision between the particles is basically controlled by the different pulses within one single eruption. So this is to show you a video of Fuego volcano in Guatemala. Look at this particle here, and then you see there is a collision. There is another particle that is moving there. There is some ash puff because of the collision, and this is a falling particle impacting a rising particle from a different pulse within the single event. So you see here again, this white cloud, this is the ash puff that we can see because of the collisions in these pulses. This is an example, again, this is again Fuego in Guatemala. All these white lines here are ash puffs because of these impacts, the collisions between falling particles and rising particles because of these pulses. This is also this is Sakurajima volcano, and again we have some colliding particles, falling particles and rising particles impacting together. So this is again, we cannot only go into the observation of nature, but we can also reproduce certain aspects in the laboratory. And this is the experiment that Don was the setup that Don already presented. When we have a certain rock sample, we pressurize it and then produce rapid decompression and see what happens. So these videos, we already see a couple of examples from Don, but here I'm going to show again. And interestingly, here you see that the particles, the sample is fragmented layer by layer. So it's produced in different layers. And in this particular experiment, which is interesting, this layer got trapped here. Then we have some continuation of the ejection of the particles, but these particles got trapped because it expanded, and the system remained pressurized. So we can have here some ejection of the particles that is moving through this layer by permeable flow, and this could correspond to the passive degassing that we sometimes have at the volcanoes. So the compression event already happened, and then in the second part of the video, this was like 100 times the time that it took for this decompression event. So much after the main decompression event, the particles are still moving together here in circles because the system is still pressurized. We have some ejection of particles, which is this passive ash venting that we have at the volcanoes sometimes. So we see some ash particles, but they were not produced by any decompression event anymore. But if something happens, there is a pressure oscillation, and then all this material is pushed from below, and then we have a new ejection of the particles, which was not produced by any decompression event. So this will not be recognized very simply in these acoustic or seismic signals, and then we have the ejection of the particles. And of course, we can also look into the waves during these experiments. Here we have the microsignals using piezoelectric pressure transducers. This is the work that Alejandra is doing, well, we're doing together. And this is the signals that we get with the pressure piezoelectric at the walls of the autoclave and then at the bottom. And here you see these kind of signals that are related to this layer by layer fragmentation. And this is also signals that are very similar to what we sometimes observe in the volcanoes. So this gave us the idea that some of the processes that we are investigating in the laboratory can help us to understand better what we are observing in nature. So this is an ejection, the second part, looking at the ejection of the particles. This is also similar to what Don already showed. But here what I want to, well, this is the gas that was on top of the sample. And then here we have the ejection of the particles, but here you see that these particles are ejected in clusters. So they are, even when the sample was relatively homogeneous, we can see some clusters of particles and then some gaps with relatively low density, which is very similar to this pulsating activity that we can have in nature as well. So here is one, here is another one, and I think there is still another one. I mean, this was taken at 20,000 frames per second, so the whole experiment lasts just 100 milliseconds, so you cannot see anything. Here is another pulse. So even when just a single decompression event, we can have this kind of pulsation. So here is again the video. I didn't know Don was about to show this video, but I will show again the lightning video together with the electric potential that we have recording with these antennas and the pressure here at the vent. So interestingly, this lightning is related, and all the electric signals that we have here, to the formation of this turbulent shell. So the system is pressurized, and then we have fine materials, and these fine materials is dragged into this turbulent shape, and this produces the separation of charges that is necessary for lightning. So for lightning, we need two conditions. We need overpressure in the system, and then we need fine material that can be dragged into this turbulent shape. This experiment, the ejection of the particles continue for 200 milliseconds, so 20 times the duration of this experiment. But then the overpressure is over, there is no turbulent shell, and there is no lightning. So the ejection of the particles by themselves is not producing lightning. We need this overpressure, and we need the fine materials to be dragged into this turbulent shell to separate the charges. And of course, this is also, we can also look into volcanic lightning in nature, and like the Sakurajima volcano, the video that I showed you at the beginning, and they can also have a very nice view of how this lightning propagates and produce in nature. And we found that the processes that we observe in nature are very similar to the processes that occur in nature for these near vent discharges, which is also very, very interesting. So in summary, we have some pulsatory activity that often observed in strombolian and volcanic eruptions. This produces, for instance, pyroclastic collisions, as the ones that I show you in the beginning. This pulsatory activity can be produced in some cases, not always, but in some cases with this layer by layer fragmentation. So the way the fragments are ejected is not homogeneous, it's in pulses by layers. And of course, the lightning can be associated with the movement of clusters of charged particles because of this overpressure in the system and the presence of fine material. And well, of course, this is a work done by many people, and together with Alejandra Arciniega, with Don, hopefully in the future with Christian, Omar, which is also here, and Anna, and many other people. Thank you very much.
Very, very interesting and very challenging. We have time for some questions.
The shape of the tunnel from where the eruption is coming from, is that trying to reproduce something that you see in nature, or this is just the convenience that the equipment?
You mean in the experiment?
Yeah, the cylinder. So the volcanoes, do they have this regular shape? Because
No.
What I was wondering is if your pulsations, in your case, in these experiments, they happen like you showed. They can happen in a cylindrical shape, but in nature, probably the pulsations might be the consequence of irregular shapes in the.
Yes, of course.
So how can you distinguish?
Well, of course, we cannot distinguish very easily. I mean, we don't know the geometry of the quantities in the volcanoes. Usually, most of the time, we don't know the geometry. The cylindrical geometry is the simplest one that we can have in the volcano. But even in this cylindrical geometry, we can have these kind of pulsations. Then it means that in nature, we can have even more complicated patterns. And especially the fact that, for instance, we can have some trap layers. I'll show you the video again. So even this is and this is also interesting because this is an interaction between the particles and the conduit. The conduit also is moving like this, and this is something that we are observing with the sensors, with the piezoelectric sensors, because the conduit is moving like this. So there is a two-way interaction of the particles. But if this occurs in this very simple geometry with this simple material, well, we can imagine all the complexities that we can observe in nature. But this can help us to understand better all these kind of non-linear processes.
That will be the next step, to do irregular conduits. But now ask Ana Lilian.
We started with irregular by changing the throat of the vent, the vent opening. So we've done some systematic studies there. Vent opening, flaring out, flaring in, and how it influences the shape of the jet. More to do with shape.
Okay.
Ana Lilian, please.
When we consider lightning, do you have an idea about what volume you would need or what percentage of you would need of the fines? Because there's some of the eruptions that produce lightning that have quite a bit of large fragments. For instance, large pumice fragments and later have the fines. But like at Chichon, there were very large fragments at the beginning, and that's when the lightning occurred. And afterwards, you got all this fine ash. So do you have an idea of what the volume or concentration percentage differences there would be?
In the experiments, we made some experiments with glass beads, and we used only two populations. One was like 500 microns, and the other one was 50 microns. And we noticed that if we have higher concentration of fine part material, we have more lightning. So the more concentration of particles. It's not clear if there is a systematic change or it's just a certain amount of finer material that are a certain size that can be related with this the particles that are small enough to be jagged into this turbulent shell. Yeah, exactly, according to the Stokes number. Why we observe lightning mostly at the beginning is because of this. Probably is because of this overpressure that we have at the system at the beginning. I mean, the video is only 8 milliseconds, and the experiment lasted 208 milliseconds at least. And we also only have lightning at the beginning when we had this overpressure in the system. Afterwards, we have, of course, fine material, ejection, but we didn't have the overpressure in the system. This is what we need because this overpressure produces this turbulent shell, and the small particles are dragged into it, produce the separation of charges, and then generates the lightning.
We should say that we hope that the discharge intensity is proportional to, is a proxy for the fine ash budget. That's something we're testing now as well. Yeah. The hope that it can be applied in nature as a monitoring system is a large part of what Corrado Cimarelli's project is about, such that he can set up antennae around these eruptions, doing it at Sakurajima, and using that as a proxy for the flux of ash which is coming out of the volcano. You know, you would think, I've been saying how easy it is to work on volcanoes because you get everything, right? The products of the process, which you don't get for earthquakes in fault zones. But in fact, quantifying it is amazingly difficult at this stage. So when you have people predicting ash dispersal over Europe from Iceland, the biggest problem they have is the source function, how much is coming out of the volcano. It's very embarrassing for us.
Those videos that you show are very nice, and that layer by layer fragmentation is very striking. Do you know what controls the length scale of that fragmentation? Is it the conduit diameter, or is it the propagation of the pressure wave through the...
Yeah, Betty knows. Betty knows. There is a paper and a theoretical model explaining this. I don't remember right now at the moment, but it's...
It depends if this is the gassing and the compression wave that is generating. Actually, it is not strongly dependent at the beginning of the size of the conduit, but it is just some layering effect.
Yeah, but in these experiments, the conduit diameter is quite close to the layer width. So at some point, you'll go from a far field to a near field problem, won't you? So.
Two comments to that. Absolutely, the one thing that we cannot reproduce. So the one thing we cannot reproduce is the bulk volume, the bulk length scale of a system. And since the first day that we thought about doing these experiments, we've been asked this. But what we can reproduce is we can produce as in the classic logic of rock deformation, we can make sure that whatever the failure mechanisms are between the individual phases, that they are much, much smaller than the scale of the sample, so that they are representatively contained. But we have changed the conduit diameter up to a factor of 2, I think was the maximum. And you want to say anything about that? About the fact... So we've been able to change it by a factor of 2 and try to look at incipient diameter-based effects. And Betty tells me when she's ready to talk to me that it's not important.
For the fragmentation threshold of the sample. So it also depends how much pressure we store in our sample. So the pressure store is also related to the size of the fragment and the layering we produce. So that's the other aspect to consider when we look at the videos. How much we are above the fragmentation threshold of the rock itself.
You want to answer?
Agree.
You agree. Okay, thank you very much, Miguel. It is a very, very challenging problem. Talk will be given by Christian Montanaro. He comes from a volcanic region near Naples. And he's currently working on stream-driven eruptions. These are triggered by explosive evaporation of hot water trapped in pores and cracks. So it's talking to us about the effect of hydrothermal systems response to steam flashing waves. So it's also very, very provocative subject. Please.
It is.
Go ahead.
I knew that I was facing some trouble with this title. Well, first of all, thank you for inviting me. Thank you, Alejandra, for letting me be here, part of being of this Humboldt family and this special occasion. I know it's not like I will just to say it's not a real waves what I'm talking about. It was just try to fitting my title to the subject we are going to discuss. Anyway, what I'm talking gonna be indeed about talking about hydrothermal system. What you see here is, for example, these are some images of what is the superficial manifestation of hydrothermal system in geothermal areas. So they vary from like steaming ground floor, from bubbling mud pool and formation of sinters, sulfurs, and all sorts of things. Now, Alexander von Humboldt was not, it's not going forward. He was unfortunately not focusing too much on hydrothermal system. Probably he would have contributed with brilliant ideas. One of the statements from his book of On Cosmos says that liquid and aerial fluids flow permanently from the bosom of the Earth through the universally diffused network of communicating fissures. So the brief and impetuous eruptive phenomena are here placed beside the Great Peaceful Spring system of the crust of the Earth, which beneficially refreshes and support organic life. So in this statement, it was giving a lot of information about hydrothermal system and geothermal fields. Okay. So, and he was in this statement also saying basically that geothermal system and hydrothermal system, they form in part of the Earth where we have an elevated heat flow, and structural setting allows for fluid circulation. This is just an example of a stratovolcano conceptual model. And basically we have fluids rising from magma through factors, and they meet with groundwater and mix and basically circulate and form hydrothermal system. And as I already mentioned, at the surface they appear as a different feature, like hot spring mud, pool fumaroles. And this is also representing a resource for us. Usually hydrothermal systems are exploited for both energies. And this is an example again from New Zealand, Rotokawa geothermal field. Basically at the now Hawapurua power plant, they managed to extract up to 175 megawatt per day. But they are also exploited for tourism. This is again another example from New Zealand. Is the beautiful champagne pool in Waisapu Wonderland. And this remained true until hydrothermal environment are disrupted. And that happened for manifold reasons. But what happened is that when they are disrupted, basically steam-driven hydrothermal eruption is the result of this disruption. So these are kind of some recent events from the 2012 to the recent eruption 2019 of steam-driven eruption. Even though we look a lot to volcanic eruption, actually the one generated by this kind of phenomena are the more frequent one, and unfortunately the more deadly one. So from this example from New Zealand, hydrothermal eruption at Te Mari crater, Tongariro volcano, basically a landslide unroofed the hydrothermal system, and the consequence for this was a large eruption producing huge ash plume cover part of New Zealand and launch of ballistic blocks. This is another example of on a smaller scale hydrothermal explosion in Iceland, where a fast lake drainage basically destabilized the underneath hydrothermal system and provoked several small eruptions. Now these two events were likely isolated. The timing was, this one was late at the night, and this one was in a very remote place, so there was no fatalities. Unfortunately, 2014, Mount Ontake in Japan, the volcano decided to explode after a long time of overpressurizing the hydrothermal system. And on top of the volcano, there was a sanctuary, and people were walking up there, and 57 people died for this eruption. The most recent event is the one in White Island in New Zealand. It's still unclear what happened. Possibly the shallow hydrothermal system failed, and what was formed here was an explosion of ash and blocks, and ash was basically coated with acid. So there were 20 people close to the crater, they died, and other tens of people far away from the crater, they were heavily injured with chemical burns. So destabilizing hydrothermal system is not a good thing, and has really usually bad consequences. How this eruption works, basically, when we destabilize and disrupt an hydrothermal system, what happens is that fluids inside the rocks expand. They can be either liquids, they can be gases, or they can be a combination, and they fragment and eject rocks. Now this hydrothermal system, usually the rock which hosts this kind of fluids, they can be of different nature. They have different lithology, different properties. The eruption itself can be triggered by manifold triggers, and I will tell you a bit more in a minute. And the other terrible aspect of this kind of destabilization of the hydrothermal system is that they are awfully unknown and hardly predictable in terms of timing and size of the eruption itself. So here is like a small conceptual model of an hydrothermal system. So we have several host rock with the lithostatic pressure growing through in depth. We have fracture along which fluids are rising and create thermal gradient. Usually you have shallow levels of cap rocks which keep the temperature elevated in the system, and at the shallow part there are generally fluids close to boil, as we saw also from some of the picture at the beginning where we have this kind of bubbly water at the very surface. So there are several causes which can destabilize the hydrothermal system. They can be like earthquake, which can fracture rocks and basically have a pressure shift within the hydrothermal system and create steam. Or we can have overpressure and breaking of cover due to sealing mechanism. Through time, the fluids rising into the hydrothermal system are precipitating mineral, and this is lowering the permeability. Or we can have a fast injection of some magmatic fluid, and that's similar consequences. The other reason can be like hydrological perturbation, for example, rapid lake drainages. When this happens, basically we have a superficial breaking of the cover, the boiling start in the very shallow part of the fluids, and there's a propagation of a flashing front that here I dare, unfortunately, to call steam flashing wave. Of course, it's not a real wave, but allow me to use these terms here. And these flashing fronts propagate into the Ostrock according to a top-down excavation model. This is the general and most accepted process. Is energetically favorable, but despite this, we don't really understand, or there are not really many studies about this model. So in the last years with Betty and many other colleagues from New Zealand and Iceland, and in the future from US, we did several studies and we applied what is the potential of our beautiful laboratory system in Munich. So what we did was to use the compression experiment to basically simulate hydrothermal eruption in the lab. So what we can do is that we can reconstruct the geology of a certain area, so characterize the representative Ostrock lithologies, and with our apparatus we can play and run all a sort of series of experiments at different initial pressure temperature, simulating the hydrothermal system, using all the different Ostrock we want representative of a certain hydrothermal environment. Don and Miguel already give you an introduction about the decompression experiment. I will just add some more information. So we use a shock tube apparatus, which consists, which allows to basically decompress our system and allows the flashing and of the water within a certain Ostrock. It consists of a high pressure autoclave and ambient temperature tank. We can basically put the rock saturated with fluids into the autoclave. We can seal the system with diaphragms. We can heat up the furnace with a furnace and basically recreate our small version of an hydrothermal system. When we do this, basically we keep our, when we heat up the system, we keep the pressure in a way that the liquid, the water within the system remain liquid. And when we reach the simulation, the temperature condition and pressure that we want to exploit, we basically explode this diaphragm and we create a decompression wave that travels to the rock, flashes the water within the rock, and the expansion of steam is basically launching the material outside. So during all the procedure, what we do is monitor what happened with pressure transducer and thermocouple within the autoclave, and we also monitor what happened at the exit with high-speed camera. This is one example of our type of experiment with steam. As you can see, it's a bit different from the one that Don and Miguel have been showing. Since I deal with steam, in this case, we had to put light, very strong light, behind our, like say, our plume to see through it and better observe what is coming out. So what we can get from this kind of experiment at the end is like knowing the pressure, temperature condition, and water into the sample, we can estimate the stored mechanical energy. We can also estimate and calculate fragmentation threshold and speed, something that Don has already been talking about. We can measure the ejection velocity for each particle coming out, and we can also collect material within the tank to analyze the grain size that we got at the end. So what means in practically, I mean, to give some more significance to this parameter, the stored mechanical energy is basically how much energy in our hydrothermal system is available for fragmenting and injecting rocks. In terms of fragmentation threshold and speed, well, the threshold tells us how much energy we need to break one of the rocks in our hydrothermal system. And the speed is telling us how fast, once we boil the water at the shallow level, how fast it propagates into our host rock. And so it gives information, for example, about eruptive pressures at the beginning and eruption durations. Another important data is the ejection velocity that tells us how fast the particles are ejected, and this can be useful to estimate, for example, ballistic impact area, something that Miguel is very interested in. And grain size distribution tell us a bit more about the efficiency in the fragmentation process, something that Don has already been mentioning, so I will not go too much in detail. So as I said before, I've been working in New Zealand. This is like, well, the northern island of New Zealand. And this is the volcanic zone where most of the volcanism and the geothermal field are concentrated. The one that you see in blue are the cases we've been studying through years. We've been looking at a kind of recent event and been looking at kind of past event. This is like one case from Waimangu Valley. Is another beautiful feature for tourists in New Zealand. The last eruption was in 1973. This is again Champagne Pool, which last eruption was 2,000 years ago. Temari, you've been seeing already something. And Rotokawa geothermal field, which is quite particular field located close to Taupo Lake. It exploded more than 12 times in the last 20,000 years, so has a very high frequency of eruption, and it produced gigantic eruption with breccia deposits that have thickness up to 12 meters close to the crater. And the last one, least but not last, Lake Okaro. It's another exploded crater. Last, well, the date is about 900 years ago. I'm just going to show you a bit more of this recent study, so some results which came out recently. And so Lake Okaro, as I said, is located in the central part of the Taupo volcanic zone. It's located close to the Waimangu Valley, and as you can see, is basically surrounded by fracture system and also cut by some of the fracture system. Just to remind you, fractures in the crust are very fundamental pathways for fluids and magmas. Okay, so when we looked at the morphology of this lake, basically we saw that there is a very complex morphology, and this morphology is related to several eruptive events. So this area suffered a first phreatic explosion. So along one of this fracture, there was magma or fluid, magmatic fluid rising, which basically flashed cold groundwater which was present there and created the first explosion. This explosion also opened the way with new fracture to fluids coming from this deep source, which over the time basically created a post-eruptive hydrothermal system. And after enough time where there was alteration, erosion, external and sediment influx, there was a second perturbation of this gigantic hydrothermal system that caused a very large eruption. We thought that one of the reasons can be either earthquake or hydrologic perturbation, considering the overall geological context. What we did was to collect and characterize all the main lithology which were found in the breccia, which were somehow reflecting what is found in the ground underneath the lake area. And also we used data from the borehole around the lake to basically reconstruct the scenario before the eruption. So what we can see is that this hydrothermal system was developing mostly in different type of lithologies. We have at depth some sort of tuffs, which are considered to be the strong substrate, overlain by intermediate pumice flow and the matrix from the first event. So we have consolidated to unconsolidated to weakly compacted material, unaltered to altered. I need to get to a bit too fast now because the time is running. But basically, we characterize the petrophysical properties, and here are mostly shown the porosity and permeability. And you can see that unaltered to altered material group in a different way. So we have an altered tuff of low permeability and porosity. We have altered tuff, which can be further distinguished in slightly altered and heavily altered one. And then we have very permeable and porous ash tuff and pumice. And we have sort of in higher permeability mid porosity matrix of the first event. So these are samples were used for running experiment, and the experimental conditions were decided based on the condition estimated in this area by previous studies. Now, considering all what I told you before about what we do and what we know in the experiment, we can use all our data to basically estimate the energy involved in this eruption. We can measure we can estimate the mechanical energy, available for fragmenting by knowing the mass of the water interpores and knowing the initial pressure and temperature, we can estimate how much steam is produced, and so we can calculate the mechanical energy as a source. We can either calculate the fragmentation threshold, or we can do experiment to determine, and this fragmentation threshold can be put in the equation that give us the fragmentation energy component of the explosion. And the mass of particle and the measured velocity with the high-speed camera can be used to calculate kinetic energies. So in this plot, we have the explosion energy normalized for the unit volume. And against it, we have, let's say, the fragmentation energy as percentage of the total energy, and as well kinetic energy. This graph is a bit weird, but I try to explain it as best as I can. There are a few colors of the symbols, again, are the same as before. We have black unaltered tuff, yellow and green are slightly to highly altered tuff. Light gray are pumices, and then we have dark gray and oranges, which are loosely unconsolidated material like ash tuff and matrix. So what we can see from this plot is that, for example, the weakly consolidated material doesn't consume too much to be disaggregated rather than fragmented. And this means that basically we have less energy spent in the disaggregation, more can be converted into kinetic energy. So particles are ejected faster, in a faster way. And as well within the, let's say, the consolidated rock, we also observe that the highly altered tuff, they also consume less energy compared to slightly or unaltered material. And again, we have more energy converted in kinetic. So these are, of course, they have implication for also what is the potential eruptive dynamics. So now this kind of energetic aspect can also be seen through another kind of parameter, which is the fragmentation speed that we saw during, which we can register during the experiment. In this case, symbols are the same. We have the fragmentation or unloading velocity plotted against explosive energy. And is again a sort of repeating pattern. Weakly or unconsolidated material, it's the boiling front in this material move extremely faster there compared to consolidated material. And in this case also, we have that highly altered tuff. In highly altered tuff, fragmentation front is moving again faster than compared to unaltered material. Gonna go super fast. Here is also looking at, the fragmentation efficiency, looking at the amount of very fine produced. Again, same pattern, so I will just go quickly through it. But just to give you the idea that using all this information, so geological, field data, theoretical estimation, and mostly of all experimental data, we can finally we can start to understand better this kind of eruption and give them some number, quantify some information. So this is like the pre-eruptive setting. And when we put on top all our information, we got, let's say, the eruption developing using the geological information. So disruption of the system, formation of flashing front, migration in a different way depending on lithology. And we know we can estimate the reason, the trigger of the eruption. We can estimate the explosive energy, how this is partitioned within the different lithology, and how much this is converted into kinetic. More in detail here, you can see from unaltered to altered tuff to poorly consolidated matrix and weakly consolidated ash tuff, how fragmentation speed is increasing, and as well as ejection velocity is increased as well. So all this information can be also, well, we hope in the future to start to put all this quantification into numerical modeling for other assessment of this, as you can see, extremely dangerous eruption type. And these are just take-home points, but I think it's mostly what I say. So.
Well, this is a really complex problem. So Yellowstone is a toy problem. Yellowstone is a hydrothermal system, but a very simple one in comparison with so.
Well, we're going to work on Yellowstone. We start a new project probably next summer. So we're going to try to apply all this knowledge that we built through years in the Yellowstone, some of the delicate areas.
It's kind of tall model, but it's okay. we have time for questions.
Yes,
and the temperature, and then you drop the pressure. Just wondering, the other scenario would be just raising the temperature until you cross the vapor curve. Is that something you thought about, or is it possible to do experimentally?
To increase the temperature. Yes. Well, we thought of, we thought about it. Actually, that should be more like what we refer like as a phreatic mechanism, like sort of bottom up. So you have a heating from below, and this is like the flashing of cold water, and then it's a slightly different mechanism. But I mean, in the end, we had thoughts about it. But for this kind of like let's say work, I was just showing what we've been doing in terms of hydrothermal mechanism, where you assume shallow, almost close to boil fluids, for which the easier mechanism will be breaking something at the surface and decompress from. That's why we follow this kind of, let's say, thermodynamical path.
So I guess within an individual hydrothermal system, you have quite a complex lithological structure.
Oh, yes.
So in terms of identifying risk from your quantifying risk from your experiments, how good are our geophysical estimates of lithologies under those kinds of conditions? Can we tell the difference between a highly weathered tuff or an altered tuff or an unaltered tuff geophysically?
Oh, that's a great question. I mean, this is our all like first step in trying to quantify and better understand what we can do. I think geophysical characterization of like lithology, for example, from well cores, from drillings, and all this sort of information are all small pieces of the puzzle that they can be put in this, let's say, big complex problem. We are trying now to do another project in New Zealand and involve also the like embracing and getting engineering people, which will try to model this kind of thing using data from a Rotokawa geothermal field, where they have like lots of information from drill core and also on the property of the substrate. So that's our initial target, where we try to upscale the problem from the lab to a larger view. So again, this is all work in progress, and I think it's very, very challenging, and we need support from everything and everyone. So.
Thank you. We have another question.
Well, just from curiosity, the geysers in Atacama follow the same mechanism?
I mean, yes, that's just like doesn't explode violently, but is basically, I guess, is a same cycle of compressing and decompressing the liquid system. So when the water just reach, the bubbling in the water reach a certain, overtake the weight of the column of water, because they just start to explode and follow a cyclicity. I think there have been quite a few work done by John van der Mooibloek and other people, like Scholl Orwitz and group from USGS on the thing. But yeah, it's like the same concept, but just not as explosive as what happened into hydrothermal eruption. And usually that's like a rising of fluids within conduit, while here you have sort of sealed, layered strata which are disrupted and explode. I don't know if I answered the question, but.
Okay, well, give us, Christian, a big applause. I thought your paper would be published.
In review now in geology,
yes,
so I hope so.
Yeah, we cross fingers. Well, this is lunch time. Very interesting and very complicated.
the Alexander von Humboldt Foundation in Mexico. So, welcome.
Thank you very much, Alejandra, for organizing this Humboldt Collect. Can you hear me? I think that I'm too short. And for the opportunity to talk to you about the different kind of financial support that you can get from the Alexander von Humboldt Foundation, that is including, for example, the organization of this kind of meetings. And I have to explain or to openly say that I am not a member, I do not belong to the Alexander von Humboldt Foundation. I am appointed, as Alejandra said, the scientific ambassador. That means that I am only, like they ask fellows, Humboldt fellows, Humboldtians overseas to help them to communicate the different programs, to encourage our colleagues in our countries to apply and to help to grow this community. So, So I think that what makes the Alexander von Humboldt Foundation different to most of the other foundations that also support scientific work or fellowships is that their principle is that they support two things. The first of all is scientific excellence, and the second one is that they support the people. They what they evaluate and what they want to help to develop is the person. So they do not support a specific project as opposed to other foundations. And it basically, to be award of this, you have to have been successful in your previous career and to convince that you will be able to pursue the scientific project that you are proposing. But it can be like any field. And they have very flexible support throughout the career, but I have to highlight that it is starting from the postdoctoral position. So it is for people that already got the PhD, not to get on grad studies, but it is from the postdoc to the end of the academic career. So they have programs for all the levels. It is very important that they support any discipline, a scientific discipline, and it doesn't matter from which region of the country you come from, they support like every place. So there is not a particular quota or amount of fellowships, for example, that there is not a policy that I have to support, like, for example, 5 fellowships from each of the 5 continents. So everybody competes, all the applicants compete in equal circumstances with all the other nationalities, and all the ones that have a good previous academic formation and an excellent and scientific project will be awarded. It doesn't matter that will be like 10 people from the same country and none from other countries. Also, the person that wants to go to Germany, they have the freedom to choose the host, the person, I mean the lab or the institution where they want to work. They don't have a work there. And I think that also a very important feature of this kind of organization is that the relationship with the foundation and with the fellows starts with the fellowship and it never ends. So it's what someone said yesterday, that once a Humboldtian, we are always a Humboldtians, and this is an example of that. There is really a worldwide network of people, of scientists that have been over Germany or Germans overseas, that creates this great network that continues throughout the years. And there are programs from the foundation that helps us to continue and to do this collaborative academic work. And so among the principal programs, there are several programs. For the sake of time, I won't talk to you about all of them, but I just, of course, choose the ones that are relevant to Mexico. And I just want to highlight that there is opportunity for all the levels. So one thing is that the foundation doesn't care about the age of the applicant. So it doesn't matter in which year we were born, but it matters in which year we got the PhD. So they start counting once we graduate from the PhD. And they have different programs according to the years that have passed once we graduate. And there are mainly, relevant to Mexico, two main programs. One that is called the General Humboldt program, and the other is the George Foster program. The difference between them is only the degree of competition, because for the Humboldt Fellow, every citizen from the world, from any discipline, can apply. And for the George Foster, they support any discipline, but they are focused on the researchers that were educated in non-such favorable countries, that I could say like developing countries. And but it is not that it is like easier to get the fellowship because you are competing among us, because we compete, and the academic level and the exigency, the definition of academic excellence is the same for both of the programs. The only thing is that they will consider, for example, one example that the people from the foundation explains is that they will take into account, for example, a scientist that was educated in a country in Africa, for example, where there is also war and so on, and have like 5 papers. It's way, or they could predict that he will be really successful if this same person, you put it in a, in a very favorable condition, as opposed to a person, for example, in Japan, you have 5 papers, maybe you are average. So to demonstrate, so that they, when you apply for the George Foster, they consider if you are outstanding in your regional area. And but once you are selected, the amount of support and all the other features are exactly the same. And there are these 2 programs, either Humboldt or George Foster, for different ages, like for postdocs fellows that they graduated just like before, up to 4 years ago. There are experimental researchers that graduated up to 12 years ago. And for more consolidated scientists, then there are the same programs, as you can see here, but here there is a important difference. I mean, it's not just the name, that they are no longer fellows, but they are awardees. And here the amount of money is significantly higher. And they give support. So mainly here the fellowship is to support the fellow, the person to live in Germany. And there is the amount to support the research is small. It is helpful, but it is not so significant. And for the awards, there is more support to do research itself. And well, I think I can go a little bit more in detail. Well, I think in this community, this is not that important, but another thing to highlight, these are examples of where in Germany there are the research centers, institutes, universities, and you can see that they are all over the country. And one feature of the Alexander von Humboldt Foundation is that they do not favor, I mean, you are not in an advantage to get the fellowship if you go to a very, like known, for example, for a Max Planck Institute that are very well renowned, you have the same likelihood to be supported if you go there than if you go to a very small town and a local university, because they focus on the person. So it matters what you have done and not, and they don't want like to centralize, like the support, and they trust that the scientific, the academic quality is equivalent all along the country. So you can really freely choose the best scientific subject that you want to pursue, and you don't have to worry about going to a more renowned place. And So I already told you the difference. I'm sorry, I say. So these are the difference between the Humboldt and the George Foster. And there is also, I didn't highlight, but the George Foster is also, there are no quotes. There is not a particular number of fellowships that have to go to a particular region. And another thing is that what they highlight for the George Foster programs is that the research project has to be relevant to the development of the country of origin, which means that any subject is possible because any subject is relevant for the development of any country. So, and if we are underdeveloped, I mean, everything will be like new and will be supportive. So you really can trust that you can propose whatever scientific field you are interested in. And the features of the fellowships are, if you want to go, for the PhD students that are here, if you are interested in doing a postdoctoral stance in Germany, those fellowships last up to 24 months, opposed to the experienced research fellowships that are a little bit older ones. You can be up to 18 months, but the difference with this one is that it's more flexible in the sense that it can be, you can divide the stance in 3 terms. Like you can spend some months, come back to your country. Most of the people that's already experienced, they have already a position in your country, in the country of origin. So you cannot sometimes live the whole year or for 2 years. So it's flexible. You can keep your work here and go and to do the collaboration in Germany. Other important thing is that it's also flexible. There is not deadline. There are no opening or calls for specific dates. You can send your papers anytime during the year. The selection committee, they come together, they meet 2 or 3 times a year, and they analyze all the applications that arrive in the previous months. And so you can basically, whenever you are ready, you can submit your papers. And so this is the time frame that I already mentioned. And this is the amount of fellowship, of monthly stipend support that you get. And so this is this amount for the postdocs, and this is the amount for the experienced researchers, and the amount for the awards are higher. And I can tell you that this is a very good amount that is enough to dedicate to work completely, I mean, full-time in your research work. You don't have to look for complement support. And there are additional benefits to this support. So what are the criteria? I mean, what is what are the important features to get the fellowship? The first thing is that you have to have, for example, to get the postdoc, to be above average if in the scientific productivity. If you are applying to the George Foster program, you have to be above average in your region. If you're applying for the Humboldt, you have to be above average in the world. And basically these are publications. And well, this is the time that I mentioned to you. And basically is what they analyze, and the quality of your publications. You have to have been already accepted in a German institution. So when you send the applications, you already have to have been in contact with the colleague in Germany that will be the host, and you have to plan the research project yourself in accordance with the host. So the host has to be, to agree that you develop this scientific project in their lab or in their institution. But it's very important that in the application, the applicant demonstrate that the main idea came from the candidate. So it's not that you are going to work for the PI or the researcher that is in Germany. To be successful for the Humboldt, you have to demonstrate that you as an individual, as a scientist at the end of your academic formation, you are the one that had the original idea. And there is no obligation to know German. You have to know English. There is not a test, an English test that you have to pass or a certificate, because since all the application is in English, and you already contact the German host and wrote the scientific project, you already, in fact, prove that you have good English. So that is good enough. If you know German, it's a plus. If you don't know German, they invite you to learn, and they support you to take courses. And the same is for the experienced researchers. So, so as I mentioned, they help you to take the course. And what is very important for them is that the foundation supports the family. So if you, I mean, if there is a partner and your partner doesn't work, then there is an extra support to support your partner. If you have kids, they give you also an extra support to support your kids. But so they really want to keep the family together. And there is a very, well, not a very small one, it's like 300 euros only to support the research cost. And what is the most cool aspect of this fellowship is that at the end of the stands, there is a study tour trip that the foundation invite you to go all around Germany, not as a tourist, but to learn the culture and the history of Germany. And this is really a fantastic opportunity, and this is what really fosters the Humboldt community, because you interact with the Humboldtians that are in Germany in all the disciplines in that same year. And so if you want to have more, I mean, this is just like a glimpse. If you want to have more information, you can go and visit their websites. This is how to our web pages where you can look for German scientists in all the different institutions. And there are also another organizations that also provide fundings in addition to the Humboldt Foundation. And so maybe in the last 2 minutes, I want to give you some quick statistics about the different the distribution of the fellowships. Here in Latin America, we are very underrepresented. And so that is, I want to encourage you, especially the young people, the students, to apply. In the last years, every year there are less and less Mexicans applying for this fellowship. And so I don't know if this is because of the, since there is so much high, that it is of excellence academic, maybe there is an under self-esteem, I don't know, why you are not applying, but please apply. You can trust that you are very well educated. And so this are the fellowships that have been given. This is the percentage. So as you can see that it's not easier to get the George Foster. Believe me that the academic level is exactly the same. These are these statistics are only from 2014 to 2018. The number of fellowships that have been given to Latin America and in particular to Mexico. You see, we are now in the very low numbers. If you look at the years before, there were 5 or more. And since Humboldt supports all the disciplines, in the natural sciences, we are more represented, but you can, it doesn't matter in which discipline you are. These are the, also the fellowships given just to Mexico in the different areas. And okay, so just I wanted to highlight for the awards that are for the more consolidated scientists, there are these, the difference is that they don't apply themselves. They have to be nominated by a colleague that, that says that they are outstanding scientists. And there are several of these awards that have been given to Latin America and even to Mexico. And there is also some support to come back to Mexico after the fellowship ends. And there are, as we are now enjoying that, at Humboldt College, there is support to do, to do return visits to Germany. And there are also grants to support research and exchange in, with the German colleague. And so I just wanted to, well, I am the scientific ambassador in Mexico. Recently, the foundation named another colleague. He's also an ambassador from the Alexander von Humboldt, that he's in Querétaro. And this is the webpage that you can just go in there. And it has like a search engine. You put in which year you got the PhD and what is your country of origin, and it displays all the programs that are applicable to each one of you. So, thank you.
Thank you very much, Susana, for this explanation. But please, if you have questions, is now or after, you can just try to Susana, because or during the dinner, it's another option. So, some question now?
When is the next meeting of the committee that decides?
I'm not sure, but yeah, they meet like in October and February and in between. Mm-hmm.
They meet depending on the number of applications, so they don't have a fixed date.
Ah,
Usually
okay.
3 times during the year.
Okay, did you hear? I don't know. Yeah, so
Okay.
yeah, basically you wait like 4 months to hear the response. Mm-hmm.
Okay, so let's move to the next talk. We have a Margarita Valdovinos. She had a degree in ethnology, so now we are changing a little bit the subject, but she's going to be talking about waves in a way. So, she got the prize Fray Bernardino de Sahagún, given by the Instituto Nacional de Antropología y Historia. She got her PhD here in Mexico, and she has a master's degree in Paris. And also she PhD, also she got it in Paris and with high honors. In 2010 and 2011, she pursued a postdoctoral research at the University of Texas at Austin, specializing in linguistic, anthropology, and descriptive linguistics for Amerindian languages. She also did another postdoc in ethnologisches Museum the Iberoamerikanischen Institute, well, this is German, Institute of Berlin, where she studied the materials from expedition to Mexico of the German ethnologist Konrad Theodor Preuss. Since 1998, she does field work among the Coras. She goes very often to Nayarit, and she is currently a researcher professor. And exactly, can you tell me now, because you are not any longer here in Mexico City, in UNAM? So
now in Yucatan temporarily.
yeah, but it's also a UNAM campus, yes. Right? So she's now in Mérida. No, yes, and she's also a Humboldtian.
Hi, everybody. Well, first of all, I want to thank Alejandra and all the organizers for this wonderful event. And I think there are very little occasions to meet with other peoples, and for me with hard scientists. And it's very good, but at the same time, it's kind of a challenge for me. So I want to start saying that the phenomenon I'm going to be studying now, it's between 85 and 255 hertz. That is human voice. Okay, but well, I'm an anthropologist, and what anthropologists do is to organize a series of knowledges around a particular experience with people. And in this case, I've been working with Cora people, as Alejandra mentioned. There are around 28,000 people who live in the west of Mexico, in the mountains, in la Sierra Madre Occidental. And what I'm going to do here is to try to answer the question how language became a field of analysis. And And I'm not going to treat this particular case of the Korea, but this story that I'm going to be telling found me as I was studying choral language. So I'm going to stop in 3 moments of the study of language. First, the pioneer work of the missionaries, then the turn to a more theoretical approach to language that comes at the 19th century, and finally to the arrival of the scientific explorations and the first use of technology for the recording and the study of language. Well, when we want to think about colonial studies about language, we have to go sometimes back in time. And I'm going to go even further back, and I just want to mention that the first ever known study of phonetics, I mean the sound of languages, was done by Panini, who was a philologist who worked over Sanskrit. And this is just to show that what I'm going to talk about is the Occidental perspective of the analysis of language, but there were other theories. And the story of these missionary people studying languages started actually in the Renaissance, where people started looking at, with a lot of interest in Greek and Roman literature, art, objects, etc. And they realized that the only way to know more about these cultures was reading their texts. And thus, they needed to learn the language. So the old treatises about language were recopilated and studied, but new forms of analysis of these languages appeared. So we have the first elaborated grammars of Latin and Greek. And actually, this created a model from which people were thinking in a new way languages. And of course, this started to, the result of this was the production of new grammars of Latin and Greek. But lately, we have also, with these models, new interpretations of Arab and Hebrew. Both of these languages had grammatical traditions themselves, but this time they were recuperated and put into a new model that was the model who was creator for Latin and Greek. And the same model was then used to the study of vulgar European languages as Spanish, English, Italian, French, and so on. So these languages were considered not superior languages and then not apt for grammatical studies. But then people started realizing that they could also be analyzed in the same way as Greek and Latin. And the same thing happened with Amerindian languages. And I'm going to treat the story of this part of the study of languages. Okay, when I was trying to put this together, I found a great work of a colleague of mine, Concepcion Hernández de León Portilla, and I want to mention her because I think what she did was amazing. What she did was analyze all the grammars written by priests during the colonial times. There are 52 in 24 different languages. So she started studying all the structure of these grammars, and she realized something very, very interesting. They were all inspired and constructed around one particular Latin language that was produced in the Renaissance. And this is the Introducciones Latinas from Antonio de Nebrija. He was a Spanish guy, and he was studying actually a lot of languages. He's famous mainly because he wrote the first grammar of Castilian Spanish, because he wanted to copy what was going on in Italy at that time, when grammars of Tuscan language were done, and from this, Italian became later the national language. So he wanted to do the same with Castilian. But here, my interest in Nebrija is the grammatic that he constructed for Latin, then was copied and used in different forms to construct all the grammars we know of indigenous languages of this time. And just to summarize all these, like the method that was established from this, we could say, tradition, is in the following order. First, the analyst should analyze the sounds of a language, then attribute a graphic representation for them, then start to document texts of this culture. The same was done with Latin and Greek. The texts were in rocks and in different expressions of the material culture. But in the case of new languages of the New World, well, they have to be recopulated. So these people were writing texts of oral traditions with this alphabetic representation based in Latin, and then elaborate vocabularies, and after that, with all these materials, elaborate what is called artes. Artes are grammars that are always accompanied with documents and a vocabulary. And from this first moment, what we can take as the further development of these lines of analysis of language are the creation of phonetics, that's the study of sounds of human languages, then phonology, which is the analysis of the combination of these sounds, later the orthographies, which is a very complex process. I mean, it's not just hearing a sound and then putting it in the Latin alphabet, it's very complex. And moreover, the grammars that we know now of different languages in the whole world. And these grammars actually are the analysis of the different levels of language. So we can see morphology as the way words are composed, then syntax, the way sentences are composed, semantics, that is the analysis of meaning, and then pragmatics, which is the analysis of the content of a sentence and its relationship with the context. Oh, I don't know how late I am, but okay. The second moment, 19th century. This moment started once we have a lot of materials from which we could start to do another level of analysis, and this is comparative analysis. So here I'm just gonna mention 3 figures that seem important and that can show us like more or less what was the movement of this time. First, Lorenzo Hervás y Panduro, he was a Jesuit. The Jesuits were expelled from the Spanish territory in 1767. So he was expelled too, and he was living in Italy. He was responsible of the library of the Quirinal, and actually he got the possibility to collect the materials that all his Jesuit colleagues and other missionaries had written about Amerindian languages. So he started comparing the paternoster translated in all these languages. He got 300 paternosters. So he started comparing the structures of language, the compositions of sentences, and so on. He created 40 grammatical sketches of comparative grammars. I'm going to come back to him, but I'm going to talk briefly about Franz Bopp. Franz Bopp was a specialist in Sanskrit. And in this time, there was the idea that Latin, Greek, Sanskrit, German were related in some ways. But he wanted to prove that they were not just related. They had a common grammatical structure, and that's what he did. So he was... okay, here I go to the Humboldt brothers. Okay, Alexander was traveling in America. He was looking at nature, at social facts, but also at languages. So he started collecting these all artes of indigenous languages. When he came back to Europe, he found his brother, Wilhelm, who was at this time an ambassador of Prussia in Italy. And he was meeting with all the Jesuits, and he was gathering all the grammars at the same time that his brother was doing it in America. So when we met, Alexander decided that the person who needed to do the study of language was his brother. He gave him the around 20 grammars that he collected during his trip. And then Wilhelm started analyzing these materials. Wilhelm met Hervás y Panduro in Italy, but also Bopp in London. So he was aware of these theories, and he started doing the same job with a particular American language. He was interested in this time in Nahuatl, which is a language spoken by the Aztecs at that time. And he did the same. He started doing grammatical sketches from the notebooks and the artists from the missionaries. But then he died. So his texts were never published. They were recently published in a compilation that it's amazing because they show all the work he did from South America to North America and all the grammatical sketches he designed. But one of his assistants took his notes, and he was supposed to prepare them to publish, to go into press, but actually he started studying what he noted, and he went further, And the name of this guy is Edward Bushman. And actually, he founded the idea that then became the realization of a linguistic family of all the Americas called Utoaztec. This is the family of the Nahuas, but also the Coras. And one of the books used in all this research was a vocabulary of the Cora that was bought by Alexander von Humboldt in his trip and then given to his brother. And the notes are still in manuscripts in the National Library in Germany. The further development of this part would be the consolidation of phylogenetic linguistics. That is the study of the relationship of languages through time. So for example, now linguists, since 100 years ago, they try to reconstruct the primary language that is at the base of a whole family of languages. This is called a proto-language. So we have Proto-Latin, Proto-Cora, Proto-everything. But also the relationships between language and the distance that there is between one and other languages. These phylogenetic linguistics also have allowed the definition of dialectal variants of language. And just to give you an idea of the richness of this situation, in Mexico we have 11 linguistic families, from which we have 68 linguistic regroupations, and in these we have 364 different languages spoken, almost all nowadays in Mexico. Okay, we get here to the final part, scientific expeditions. Well, in this part, we have all this accumulated knowledge, but also we start having new questions to ask about language. And one of these questions became, what is language giving us about a culture? What kind of information can we get from the language itself? So now, texts were not just written in Spanish about cultures, but people of other cultures were asked to give their text in their own language, and a lot of scientists dedicated themselves to do this new form of documentation. The way language was collected was first by elicitation. It's like when a researcher stays with someone and says, okay, how do you say dog? How to say house? And from these, they gather vocabularies and they work with people to get dictionaries and then to gather texts in the native languages. But suddenly something changed because the new technology that was able to record voice appeared. Here, I'm gonna try to play. I need help. Okay, this is a recording of 1906 of a Cora ritual song, if I can play it. Just like an example, but I'm going to continue with my talk, and if we can hear it, good, and if not, I'm sorry for you. Okay, this is a phonograph. This is one of the first technologies with which we could record voice. People needed to put the whole head inside of this cone. Sí, claro. And, okay. They put the head inside, and then they had to speak very clearly and loudly. And the vibrations of the voice were conducted to a needle who was in the point of this machine. And the machine was like the size of a sewing machine. And in this machine here, you inserted a wax cylinder. You activated the mechanism turning this, and then you put play, and then the people speak inside, and the vibrations were recorded in the wax cylinder. You could only register 2.5, 3 minutes. That was the most. And then, okay, here we go. to hear the recordings, what they had to do, don't worry. Okay, they had to produce copies of the original cylinders. So they have to destroy the original recording in order to do a negative in metal that were called galvanos. And from this galvano, you could produce copies and hear the copies. You could only hear them 4 or 5 times, then the needle will break the cylinder. This collection, I studied it in the Phonogrammarchiv in Berlin, and there are 100 of recordings of the Kora and Huichol people. The researcher who did this, Konrad Theodor Preuss, could never use his recordings to work as he thought he could. He did all this effort of like taking the cylinders, the machine, recording, sending them to Germany, cataloging, etc., doing the copies, but the sound was very bad. What you were supposed to hear, I'm sorry you couldn't, was like one of these recordings. The quality is actually very bad, and these copies were already digitalized, cleaned, filtered, and so on. 100 years later, I was able to have this new version of the cylinders, and I could translate and transcribe and compare with the same ritual songs that are sung nowadays, and prove that these oral traditions are intact, and that songs that are 12 hours long are still sung the same way that Preuss heard. Well, in any case, the problems with technology were a big deal, but they opened a new field. And this is a further development in this part that I'm going to treat in a different set. First, we have the establishment of the International Phonetic Alphabet. Here you have the chart of 2018. This society was founded in 1886, and they decided they needed to have a universal alphabet to write any possible sound of a language. So that's what they did. So here you could see, okay, these are consonants, these are vowels, these are aspects of the language, and these are diacritics that we use with these symbols. It's inspired in Latin alphabet, but there's a lot of sounds. And the way it works, it's that what it's marked is the places of articulation of every possible consonant and every possible vowels. This is a chart of English. The green vowels are the English vowels. English is one of the languages with more vowels. And for example, this is the E. So for an E, you have to close your mouth, and then the language position is at the end, at the front, and these are round vowels, so you can produce any possible vowel, and you can have any possible sound in this chart. And it's every 2 years is revised, because when we find new sounds in new languages, we include them in the chart. So then we have the acoustic analysis of speech. This is very modern and very useful when you're studying languages that are not like yours, because sometimes there are sounds that people can hear, but you can't hear. And for example, in Kora, there is this vowel that it's like an A, but it's creaky. Creakiness, it's a quality of voice that you do with the glottis. And so, for example, A, 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 A. There's like a little creakiness in it. Sometimes when we're transcribing a text, it's almost impossible. And if you put the wrong A, the meaning changes because it's a significant vowel. So these kinds of technology are helping us. And the last part of my presentation, just to finish, is this new way of analyzing languages that allow us to do multimodal analysis. That is not just the language, but also the facial expression, gestures, intonation, and so on. So here you can see the different, well, this is the segmentation of the speech to have when you have a dialogue. Here you can have the intensity of voice, and so on, no? So, well, just to close, like when I heard everybody, I saw that the starting point of your analysis, this wave and wave field, and actually in this field, it's almost at the end, and I was like, this is kind of weird, but then I realized, and I talked to some of you guys at the dinner, and I realized that when you need all these machines to analyze waves, actually linguists and anthropologists studying languages, we just need ourselves, the machines to understand language and to segment and to analyze is ourselves. So these machines are allowing us to go deeper, in particular when we analyze languages that are not ours, because one of the things of human ears and brain, it's that you get used to the sounds you're in contact with, but you lose the capacity of hear, recognize, and distinguish sounds that are not from your language. And well, this is my final remark. Thank you.
Thank you very much, Margarita. It's a very nice talk. And now we are almost closing the circle that when we started. So,
at what age you lose the capacity to recognize sounds, reproduce them?
9 months. To recognize sounds that are
And
not in your
reproduce
language?
them, yes.
Reproduce, when you're 9 months, you cannot reproduce. Sorry. Recognize and produce are processes that are completely different. Recognizing, you learn to recognize when you're a baby. 3 months old, you already recognize a lot of things of your language, the syntactic structure, sometimes morphology, and so on. At 9 months, babies stop hearing sounds that are not significant for their language. Bilingual, trilingual babies have the ability to keep all the sounds that are significant in all the languages they are in contact with. And what was the? 9 months. To produce is something else because the production starts at 1.5 years, depending on the baby. No? And when you learn a second language, if you're very young, it goes very fast. Mm-hmm.
I have already.
Ah.
It's actually more adding than a question. The Cátedra Humboldt is actually supporting the translation of the Mexican grammar of Wilhelm von Humboldt into Spanish, as well as the Wörterbuch.
Yeah, there's already a new print of it in 2005, I think.
There's one of Otto Mee. There's one of Otto Mee.
There's a lot. He did a lot of grammars, but the Mexican one was published already in Germany.
Yeah, no. We are translating the German one into Spanish
okay,
to bring it back to Mexico.
Oh, nice.
That is
That's
exactly
great.
the project.
Thank you.
So.
Yeah.
Oh, thank you, excellent presentation. I have a question as well about the age at which you lose the capacity of recognizing new sounds. So if 9 months is that age, how can you learn a foreign language when you are 20 or 30 years old?
Yeah, well, actually, you can always learn new languages, but you have to, again, be in contact with the language and your brain starts to that's why we can produce new sounds. I mean, it's not closed, but in a natural process, the baby needs to know what sounds or what noises he has to be aware of. So he discriminates what his brain believes it's not important to understand something.
Yes, just to follow up with this idea. Yeah, actually, there are experiments done with babies, and they can reproduce the vowels of the different languages that they were exposed to only in this window, and they can learn like us, like we are speaking with English, but with a horrible accent. So it's what happens. I mean, you think that you are speaking with the same vowel, but the person that speaks the other language can recognize that you are not pronouncing like saying in German, like Gemüse. I mean, I'm sure that I am not saying Gemüse with the right U with umlaut. I mean.
So more questions?
I have a question. It's just to get your opinion, because it's not really a question. I learned recently that there is a mathematician from Universidad Metropolitana who is from Oaxaca, is Zapotec.
Okay.
It has a project to translate Newton's Principia to Zapotec. I think it's very difficult because you mentioned that the culture is breathed into the language construction.
Yeah.
The problem, maybe in the afternoon we can discuss how technology So can a Zapotec in Zapotec learn calculus, differential
Yeah,
equations?
of course.
And
I mean, the problem would be that Zapotec won't have the concepts of it, but then you have several options. Either you, we call it préstamo, I forgot the English word, but you can take it, lend it from another language, or you can create neologisms. That's what the missionaries did when they were trying to translate the Catholic ideas to languages. So you invent a word using sometimes the grammar of the local language, but concepts that actually refer to your culture or to the other's culture. Anyways, translations are always reinterpretations of things.
Another question?
Yeah. There was someone.
Just a non-specialist question. So how far back in time is it possible to go with these methods, and what's the earliest proto-language that we're able to get to?
Oh yeah, I'm not an expert in philology, but I mean, they know now that all these Greek, Latin, Sanskrit, and so on were part of one language. So I guess they know, and what I know more is what's going on in Mesoamerica. They can do reconstructions very far away. But the problem is that then, at the moment you don't have evidence of a language, you cannot go further back. So, I mean, the latest evidence of a language that we can read, it's Maya in the stelas of the archaeological sites, and some Olmec writings, but we're not sure we can decipher these things, so you cannot know.
I have another question. What about the modern language? Which one do you consider is easier to learn, for at least in the Occidental world? Like Spanish, for instance, because, for instance, in German or in English, they have more phonemes than we have in Spanish.
I don't think there's an answer. I think everything is relative to the language you speak and to the contact you have with this language. I mean, for me, the most difficult language I've learned is one of these indigenous languages because their structure is so different to my language and the languages I know. So that's why it was harder, but maybe for a Zapotec, that would be the easiest one, no?
But talking about the sounds.
It's
not
also
the structure.
relative. It's like
also same.
you're used to a set of sounds and not to others. For example, these African languages with the clicks, for me it's very difficult to hear and to translate, and for them it's like the easiest thing. They don't know how to put accents in French maybe, but they do the clicks perfectly. So it's like we got formatted with the languages we got when we were born. And this format will stay always with us.
Yeah, more questions there. No, I just wonder because Russians normally learn Spanish, English, German super fast.
Yes. So maybe some Russians do, yeah. Maybe others don't.
So I'm curious. In machine learning, there was a recent development that are called transformers, which is a structure of neural networks that are very useful in making translations in different languages. This is the boom that now you see in software that allows you to speak to someone in one language and the machine will translate to you.
Yeah. That's very, very difficult to do. That's why we don't have a perfect Google Translator yet, because, well, English is the most studied language in this sense. The problem is that you cannot give the context to the machine, so it will always make mistakes.
Correct.
You can have like easy to translate sentences when the context is not needed to get the meaning, but once the meaning is involved, the only thing you could have is like in these Japanese machines, they give you possibilities of translation, and because you know more the context than the machine, then you say, oh, it's this one. But there's no way to, well, until now, maybe later they will invent something that will do the thing.
But my question is related to what you mentioned in your talk. You were saying that all the languages that are spoken here, the ancient language, the original language in America, were derived from a single language.
No. What I said, all the grammars were done based on the same grammatical work did by Lebrija.
Only the grammar, not
only
the
the
words.
Yeah, no, the language. No, you have 11 families in Mexico, And we have like the Vasco in Spain. Here, the Huave, for example, a language spoken in Oaxaca. It's isolated. There's no related language around. We don't know where it comes from or why is it there. We have 2 isolated languages in Mexico that are there, just there.
So all the comments that I was making is because I'm quite curious to see some languages are easier to translate than others. There are patterns that are not obvious because, as you were saying, the context is important and transformers are supposed to be good in picking up what the context is. They have a module that is called attention that is supposed to do that.
Yeah, I don't know about those things. I just imagine that if a language is easier to translate with a machine, it's because the machine has more information about this language.
No.
Because there's a lot of grammatical structures that we still don't know about languages, so that would be so hard to do.
Thank you, Margarita. So I think you will have a lot of people talking. Thank you very much. So our next speaker is Felipe Orduña Bustamante. Now we are moving to music, the physics of music. So he's a senior researcher at the Acoustic and Vibration Group here in UNAM. He has a degree in physics, a master and doctorate in sound and vibrations from the University of Southampton in England. He works on instrumentation and acoustic measurements, digital signal processing, musical acoustic and music technology, author of articles, reports, and as everything that we have to do as researchers. He has a lot of students, and he's an amateur musician, plays the guitar, the barocca flute, and also the pig flute and the keyboard, some keyboard instruments. And he does computer music and choral singing. So it's a time to make more questions, please.
Thank you, Alejandra, for the introduction. Thank you for the invitation. Also to Alicia Ortega, who kindly invited me to this meeting. Thank you to the Humboldt Foundation and to the Institute of Geophysics. I will talk, as Alejandra said, about one of the topics of the work we do at ICAT, which is musical instruments. Sorry, I don't see my presentation here, so let me. Okay, I just jump ahead here. All right. No, I think I need to have the presentation here because I'm not using.
No, pero él necesita ver aquí. Esta no es de él, esta es la de Margarita. Tendrás más. No te preocupes.
Gracias.
¿Cómo se llama?
Ese es un PDF que está por ahí.
¿Prefieres así?
Sí, aquí está. Sorry. Okay, this is my second slide. This is an announcement only. This year is the International Year of Sound. So just to remind us to be aware of that sound is always present in our lives. it is useful for communication, for entertainment, but it is also potentially annoying and dangerous. So we have to be aware of all that. So I leave that slide there. Okay. This talk will we'll delve briefly upon some elements of diversity found in the physical analysis of musical instruments, and we'll also focus on particular examples offering concrete illustrations. The contents is roughly like that. I will give a brief introduction, then I will talk about three particular subjects, not related to each other, more with the intention of showing the diversity of the field, and then finish with some comments. Musical instruments, including the human voice, display oscillatory and wave phenomena of great diversity, involving different material media and properties. Some examples: elastic solids in violin bodies, marimba bars and bells, organic tissue in the human vocal folds and lips, flexible materials in strings and membranes, like in drums, periodic and granular structures, like the rows of finger holes along flutes, grooves in scratchers, granules in rattles, etc. Also air as a compressible fluid in wind instruments, and even water, like in bird flutes. Most musical instruments also display or are defined intrinsically by two or more interacting subsystems. For example, vocal fold vibration and vocal tract resonance in the human voice, string and body vibration in string instruments, bow and string interaction in bowed string instruments, like in the violin, lip or reed vibration and acoustic tube resonance in wind instruments, air vortex shedding and oscillatory airflow in flutes and organ pipes, and a big etc. Okay, I will talk about the first of my three examples. Making harmonic bars out from initially inharmonic ones. Bars used in marimba, xylophones, and other similar percussion instruments exhibit flexural vibrations with free ends. Basically, the bar is free, floating in the air, not floating in the air, of course, but supported by very thin strings, textile strings. Flexural waves are dispersive. Propagation phase velocity depends on frequency, precisely like the square root of the frequency, and display spatially evanescent vibration modes with exponential decaying displacement from boundaries and discontinuities. All this boils down in that overtones of bars with free ends follow a series of non-integer ratios written there, which are not musically harmonic. So when you try to do harmonic music, play with other instruments and such, with a bar, it just don't work as it should. However, overtone frequencies of some of the lower modes can be brought into a harmonic relationship by using bars with a purposely designed non-uniform thickness. These are two examples. These are the thickness profiles and flexural vibration modes for uniform and non-uniform bars, which in fact produce different mode shapes, but also different overtone ratios. So this is an example of how we did some design of variable thickness bars. So we have a parabolic undercut bar with normalized parameters of width and thickness, as shown in the figure. And then sets of parameters are sought that give integer overtone ratios, at least for the first three modes. And we did some numerical work to calculate this diagram. Sorry. this diagram where we have normalized width of the undercut and normalized thickness. And these curves here are, for example, the combinations of width and thickness that put the second mode into a relationship of 3, a multiple of 3, a harmonic ratio of 3 with the fundamental vibration of the bar. This is the second mode in a relationship with a multiple of 4 and 5. And the thin or dotted lines here correspond to harmonic ratios of the third mode with the fundamental one. So what we want is both the second mode and the third mode being in an integer ratio to the fundamental. So we pick this intersection point here as a possible candidate or possible solution for a harmonic bar. And you can find also another one here, for instance. We skip these ones because then the bar is already very thin, and so it's structurally weak. And these are the 3 designs I pointed out there, and these are undercut marimba bars with harmonic overtones ratios as shown there. And you will see here these dots are actual measurements of thickness of actual bars that we built and measured, and we could in fact prove that the harmonic ratios are as predicted. That's the first example. Next example is coupled string body vibration and the tuning of guitars. The main factors that affect the tuning of classical guitars and perhaps other instruments as well, but I will talk specifically about the classical guitar. We can divide in 2 main groups. The first is subjective and musical factors, such as the tuning method, the auditory cues used to judge tuning, psychoacoustics of pitch perception, and musical temperament or the tuning system used to play music. And also physical factors such as fretting and fret compensation, string overtension in fretted tones, string body vibration coupling, which is the topic I am going to talk next, inharmonicity due to stiffness, and also the time frequency uncertainty principle, which means that if you have very short sounds or very short tones, then you cannot determine the frequency very precisely. So there is that uncertainty which occurs physically, but also subjectively. When you perceive the pitch of sounds, if they are very, very short, then you have some ambiguity in judging the pitch. This is an example of the frequency spectrum of a guitar tone, and you can see the main components of the sound, which in the textbook you will read that they are harmonically related. I mean, exactly integer multiples of the fundamental, but in fact they are not. Overtones are not always harmonic due to vibration of the string at the resting points. This is an example of the input mechanical mobility, which is the ratio of vibration velocity against over the vibration force applied, measured at the string resting points at the knot and bridge, which are the extreme points or resting points of the string in a guitar. I won't explain much about this, but you can see that there are resonances, and this will affect the tuning of the string, and in fact, the harmonicity of the string as well. This is a diagram of a calculation of how this string body coupling will affect the tuning of the different harmonics this is frequency, and this is a tuning shift in cents from -20 to 20 cents. 100 cents is 1 semitone. So this measure of cents is a micro-tuning measure for representing very small but significant tuning shifts. So the string body interaction causes that the harmonics are shifted. The reference line is this one, which is a tuning shift of 0 cents. And you can see that because of string body coupling, the harmonics or the overtones of the frequency components of the string are shifted the way. So that affects tuning. So we did an exploration of tuning shifts due to string body coupling. Input mechanical mobility was measured at the top plate bridge, nut bridge, and over all frets of a classical guitar, because the frets are also possible resting points of the string, right? Frequency shifts due to string body vibration coupling were estimated for the frequency components of all possible open and fretted guitar tones. The perceived musical pitch and tuning shift in cents was estimated for these guitar tones using a psychoacoustic based model. And then we got these diagrams. We have a diagram for each one of the 6 guitar strings, and for the different frets of the guitar. 0 means the open string, and up to 18, the 18th fret. So this model predicts that there is no significant shift in strings 1 and 2, but you start to see some effect at string 3, the open string mainly. In the 4 strings, when you press the 4 and 5th fret, string 5 here, and string 6 you get these effects, and these are musically important. I mean, you can hear this as important artifacts of tuning of the guitar. This is another experiment which, in a certain way, corroborates our previous result. These are actual tunings by 15 guitar players tuning the same guitar 10 times. And each time they tune the guitar, we measure the tuning of the open tones. And there are several things that we can observe here, but I mean, there is very significant dispersion of the results, but what I want to point out is that this one is the average of all the results, and we can observe these trends which can be related to the effect of string body coupling in the guitar. So that's an effect that, in fact, is at work in actual guitar playing. Last example, and this is the quantum mechanical analogies of electrons in a trombone. I will go very quickly over this. This is a wave equation adapted for like a trombone, which has a non-uniform cross-sectional area. You can do some mathematical substitutions, and you can put that exactly in the form of Schrödinger's equation. And that allows us to do some very, at least amusing analogies between the acoustics of a trombone or instruments of that kind, even the human voice, with a quantum system. This is an example of the parameterization of the ending flare or horn in a trombone. We have this as an approximation of the spherical wavefront coming out, if you we think about that that way, I mean, from the trombone. And these are very different, at least 3 different coordinates that we can use in the previous equations, which is exactly this, this coordinate along the x-axis, or the wave front coordinate, or the arc length coordinate. I won't stress that too much, but just let me go ahead and show you that analogous to the energy potential, for instance, for an electron trapped inside an atom or something like that, you have this, what energy is for an electron for sound inside a trombone is frequency. So what we have here is a frequency potential. Keeping sound inside the trombone will go in that direction, and this is the outside of the instrument, and this is the region of the ending horn. So the different parameterizations predict different shapes of the frequency potential, as we if we think that way. So that sound will stay inside the trombone if it is not of an enough high frequency, but sound of very high frequency will go out from the trombone and do not resonate. And that is exactly the way these kind of instruments work. At higher frequency, you only hear the poofs and burps of the lip excitation, but at lower frequencies, you hear the different frequency resonating in the sound. And instruments like this have what is called the cutoff frequency, which is the maximum frequency above which the instrument do not resonate. This can be, this is an actual measurement of the reflection function of a trombone, and you will see that the reflection inside the trombone is of a significant value, or close to 1, up to around 1,000 hertz. If we go back to this one, it means that the more accurate prediction of that is this one, which corresponds to the arc length coordinate used to parameterize the geometry or the coordinate for the sound coming out from the trombone. And this is what is called the input acoustic impedance, and it shows the ability of causing resonances, also limited to frequencies roughly below 1,000 hertz. And that's basically the end of my talk. Just a few last concluding remarks. Musical acoustics is a very rich and varied subject. There is much in terms of the physics of material media, oscillations and waves, but it also incorporates elements of human perception, cognition, musical culture, history, art. But above all, musical acoustics is tremendously fun and intellectually amusing. It invites many travels of exploration and discovery as a very fitting continuation of Alexander von Humboldt's legacy. Thank you. Yes.
About the guitars that you use, yes. What kind of quality you use? Because the guitar is a very sensitive instrument, and then you, besides, when you don't put your finger where you have to put, you are already getting a different sound. Yeah, and the strings, also the quality of the strings are important, and the height of the bridge, and so do you control the quality of the guitars you use and the quality
yes.
of the strings?
For this experiment, we used a commercial Spanish guitar of which is known for a good quality. Manuel Rodriguez is a famous guitar shop. Yeah. And also we used, I don't remember the quality of I mean the brand of strings, but we used the top, I mean, guitar and strings were of very, very high quality. And also the guitar players that participated in the tuning experiments were professional players. They were professors or advanced students at the Faculty of Music here
because
at
I
UNAM.
noticed in your graph that, for instance, the first and the second string, they don't have any changes, but of course the material is different. When you have the first and the second and the third are made of nylon, and the other ones have this torch, they have kind of very fine, no, it's not nylon.
You mean this one or in this one?
It's metal. It's metal.
Yes.
Yeah. But it's a torch material.
Yeah, in the it's common for the top for the strings 4, 5, and 6 to be metal wounded, metal, and 1, 2, and 3 are bare nylon.
Yeah.
Yes.
So it could be this completely different response.
You mean if we used metal strings or?
Yeah, because you are changing the materials, then you are not expecting to have exactly the same response.
But well, this effect is happening only because what I said is the string body interaction. The fact that some strings are metal wounded and
but they are interacting with the woods.
Yes, but the interaction happens at a dimensional scale which is very bigger, much bigger than the detail of the wounding of the metal wounded strings. So I don't know. Perhaps
because you were saying
what I should say is that I don't know. Strictly speaking, I don't know. But I guess that the effect is not as big as this one. And I must stress also that this is only one of the possible effects that affect guitar tuning. I mean, in this plot here, there are many effects, more than 8 effects that I mentioned at first, which are playing a role here. Yeah. And what I am just saying is that the fact that we have these notches here are because in this guitar and in most guitars, there is a body resonance around the open third string and also around the open 6th string. So these notches here observed as an average of more than 150 tunings experiments by professional guitarists mean that this is a physical effect which is intrinsic to this string body coupling. I don't know.
Okay. Okay, more questions now.
Just precisely on this figure, precisely on these results,
yes.
How do you explain, so the different people, the different professionals sounds very different? So they have a different sensibility or sensitivity?
These are professional players. And what this reflects is that this notion of a perfect zero error tuning capability is simply a myth. So even professional players have show a dispersion. For instance, each one of these circles and error bars correspond to a single player, and these results show that a single player has a certain interval of reproducing its own tuning, and also when comparing with different colleagues of them or with different players, each of them obtain a different result, and that I think is produced by a combination of all these factors that I mentioned here.
Well, I think that among professionals, the technique in playing the guitar is very important. So
Yes,
yeah.
that's true.
So this is just a comment.
Yes.
I used to play a little bit of fretless bass guitar.
Yes.
And I always got the feeling that the tunings on some of the strings were at just slightly different positions for certain stops.
Yes.
And I find it very encouraging that you see this on the frets as well, because I just assumed it was because I wasn't very good. So I'm pleased to hear that it's not just because I wasn't very good. Thank you.
Yes, let me quickly show. I had a slide at the very end, which I won't go in detail into this, but in fact that there is this string over tension tuning shift, which, I say here for fretted tones, but in a fretless bass, this effect happens as well.
Okay, well, let's say thank you very much to Felipe. Oh, who? Sorry. Sorry, come. Turn the microphone on, please.
Were the experiments conducted in an anechoic chamber? And I'm wondering about the effects of the room acoustics on feeding on these results for the player or for the instrument.
Not in an anechoic chamber, but in a very acoustically damped room, more or less like a recording studio. So you're right in saying that the room resonances can have an effect, but in this case, I think they are not playing a role.
No more questions? Okay, let's then go to...
Thank you.
Yeah, thank you very much to Felipe. Thank you very much. So, now our next speaker is not here physically, but he's sick and, well, he's a diabetic person, and the doctor didn't allow him to come, to travel his long trip. So, but he was very interested in coming, and he just sent a very nice video of him playing the sound rock. So I'm going to show you. He sent with Bjorn Krull, who is also sick, this small model of the sound rocks that he used. And you will notice that in the video. These are amazing material. It's a gabbro, this one, and you can get music from them. I cannot play it. You have to spend kind of, you need to practice to come out with the sounds from the rock. I try with the big ones. With this small one, it's more difficult because it's producing only high frequencies or more high frequencies, but maybe you can hear a bit, right? But this is not the way you have to play this instrument. So this is something really amazing. They found this gabbro. This is particular from India, and maybe the expert here, like Don or Dave, can say why this the microstructure maybe here. This is like a 12 kilos. So why just this produce this fantastic sound? So there are another rocks like tonalite or serpentinite that also are very fantastic producing sounds, but no better than the gabbro. And the geometry that they do, it plays a very interesting and very important role in how this instrument sounds. And you will see just an example of very similar shapes like that. But you can go to the webpage of his studio. Klaus Westman is a professor in Mozarteum in Salzburg, He's German professor, and it is really, really something. Well, at least for me, I hope for any earth scientists also getting music from the rocks. If anyone wants to check it or see it, you just can do it. Don't worry. Ay, no me digas. Tenemos que conectarlas. Entonces no vamos a poder oír. ¿No se puede? Ah, ok. No, ese no es. Es que yo abrí las dos. Pero eso nada tiene que ver. Sí, yo sé. Este es el de... Ah, ya te entendí, ya te entendí. Es un movie. No, no, no. Es un movie. A ver, espera. Ah, ya te entendí. Entonces que no se va a oír bien porque es... no tenemos bocinas. Es que... me hubiera traído las mías. ¿Alguien traerá una de sus celulares? No, o sea que este computador tiene bocinas, ¿no? Sí. Es un video. ¿Yo lo puse bien? Ah, no, no lo puse. ¿Por qué no se ve? Porque esto hay que pasarlo a la otra pantalla. Ah, es que lo cambiaste de lo que le tuviste que hacer. Ahí está. Aquí ya está.
Can you hear something?
Yeah. Tiene que poner el micrófono.
Hello, ladies and gentlemen. I'm Klaus Seismo, composer, live in the southern part of Germany. You see me while I'm speaking, playing.
¿Sí? So you can see, but you cannot hear, so I need to make some changes.
Yes, 8 sheets. They play it with the hands, taking water on the stone, water on the hands. To have no force by developing these wonderful stones.
¿Dónde está el mouse?
Del otro lado. Del otro lado. Ahí está.
Entonces
lot of different overtones there. And with my both hands, I can play 12 different things, 12 different structures, layers, patterns, sounds at the same time. I can hear it, I can understand it, and I can compose it. For me, this music is the oldest music in the world. Just before this earth came out, and I hear this evolution. When I work with these tones, I found out that they are coming different sounds each day, new ones, and have to look out that they are growing up, that they are sounding well for me and for the stone. When I play piano, I play also with the hands. I play these parts of my hand. But when I play stone, I play with all the parts of it. The fingers, they are this middle one there, this thumb thing. It's so fantastic to look out. When you play here, for example, it sounds very different. Now I get with those fingers there. And I play a whole symphony of this earth, of water. The water also sounds. And I love to do it. I love to do it very much. I think it's one of the greatest things I ever found. We play concerts so that we can bring this music to the people of the whole world. We can combine this with the orchestra, with the voice, with the harp. And we also can play many stones together. We made a recording 2 years ago where we played 11 artists played together, 11 musicians played together with 11 different tones. And that's a wonderful harmony coming out of this cooperation. When I think I should combine 11 or 12 pianos or other instruments, and they play all the same thing, the sounds of each instrument, that's not so good to combine. But you can combine different forms of stones just around me. You can combine it. It sounds very good. can teach everybody to play stone. Everybody can learn it. You have to have so much knowledge of music, not to know about harmonies, not about sounds, not about the rhythms or so on. You come here and you can begin. I give you water and we play together, and we only have to lift our whole force out of this movement. When you have force, you hear it sounds like this. When you don't have force, I developed forms of touching it. For example, this one. Both hands are doing the same. You see my thumb? It's playing melody. The other are playing the harmony. Then we have the third movement, going just like walking.
It's the same. No, I mean it changed depending on the instruments. I mean, you have been saying that it's the same since the beginning, right? No, but I mean, he did this, and I think we have to see it, no? So, well, hope you like it. So, show this, just enseña esta foto. Just going to show you the studio that he has, where there are other forms of other shapes. And the big ones produce so very deep sounds that are so nice. I mean, you feel like they are using it like for therapy. They are using it for concerts, as he said. And many people are buying them, and especially people from the United States. Well, okay. Yeah, because some people just go into the esoteric part, you know, but in fact, I found it, this is the studio, and they are using it also like a background music for singers or combining with different instruments, so that's why. And going to that place, and when they are playing more than one at the same time, you really feel it in your body. And it's a very nice sensation, because, well, at least for me, many people feel it. Okay, so I think this is our last session. Now, Klaus Siebe is going to talk about the everything we are going to do tomorrow, and his presentation about Popocatépetl. You know that, can you move this? Our one of our senior geologists, senior professor here in the institute. He studied his PhD in Arizona State University in Tubinga. Well, how is this thing? No, I don't worry. No. Okay. Yes, because you sent this. So.
Yeah, don't worry. I'm Klaus. I'm your, excuse me, I'm your fearless field trip leader tomorrow. Of course, it's hard to beat singing Gabros. In all honesty, I'm glad he's not my neighbor. And I hope my 10-year-old son doesn't learn about this.
Okay, so it's going to be a one-day field trip. I've done this field trip many times with students and with groups of different sizes. And I know we can see only as many outcrops as we can see in a certain amount of time. And larger groups usually is fewer outcrops, unless you're kind of disciplined. But that's up to you. I will not be pushy. And the idea is to see different outcrops related to Popocatépetl's Plinian eruptions. And ¿cuál era el para adelante? We will depart here in the south of Mexico City, and you can see there is a mountain range, a volcanic mountain range that divides the valley of Mexico from the valley of Puebla. This is called the Sierra Nevada, and the southernmost volcano is Popocatépetl, and we will drive along here to Ameca, and from here we will cross over a saddle that separates Ixtaccíhuatl from Popocatépetl, and then we will drive down towards Cholula and return on the freeway to Mexico City. And between Ameca and Cholula, we will try to see some outcrops. And now I will provide you with a little bit of background information. Yeah, here again. Ameca, here is Paso de Cortés. This is the pass that there was an old road, an old Indian road, and that's the one that Cortés took that when he conquered Mexico on his way to Tenochtitlan, and that's where the name comes from. And coincidentally, Humboldt also took this route, and this is the present paved road, but essentially it follows this old route. And so coincidentally, we are going to follow Humboldt's steps, who also took this route from the west to the east. No. Okay, so after decades of dormancy, Popocatépetl started erupting again a little bit more than 25 years ago, and essentially what it has been doing is emitting periodically ash. As you can see here, this is a picture I took from a commercial plane, and this is what the crater used to look like. Essentially, there was a small crater in the crater. The crater had these very steep walls, almost 300 meters high, and as of 1996, when a first dome started growing there, from then till now, I think more than 90 have been growing there. And these domes periodically explode, and then you see that it's not very smart to run around there, whether you have on a helmet or not. And the largest that we measured is 9 meters in diameter. So it's not a safe place to be near the summit cone. And that's also the reason why the road from Paso de Cortés onwards is closed. Some people have been killed there. There have been also, on one occasion, there was a small pyroclastic flow that you can see here entered the forest and burned the trees. And this is more or less the way the crater looks like today. Look at this topographic accident here, how it used to look like and how it looks today. So one wonders, you see this crater, it has about 1 kilometer in diameter, and this type of activity that we have been observing over the past 2 decades and a little bit more, obviously did not form this large hole, and we have to ask what kind of activity did that. And the answer lies on the slopes of the volcano, which we will be visiting tomorrow. And when you look at these sequences here, these are pumice layers. There's one pumice layer after the other. And we have studied these in greater detail. We have dated them. We have analyzed the chemistry, the mineralogy, and all kinds of features, and have come up that these are mostly Plinian deposits, and Plinian deposits stem from Plinian eruptions. And but what is a Plinian eruption? It is not precisely defined, because every eruption is essentially different from the other, but a Plinian eruption in general terms is an eruption that is similar to the one that Pliny the Younger described at Vesuvius in the year 79 Anno Domini of our time. Yeah, this is very famous because it destroyed several nearby settlements, including Pompeii, which is the most visited archaeological site in the world today, and it nicely preserved many, many things. Hence, we have learned a lot about Roman culture from the excavations that have taken place there. So this is in order to give you an idea by images, by showing you some images. This is the present cone of Vesuvius, and this is the rim of the crater formed in the year of 79. This is the archaeological site of Pompeii. All of these structures that you see here were completely buried by pumice fallout. And so you can see they had to remove several meter thick deposit in order to bring to light the ancient city. In the background is the volcano, and this place is 11 kilometers away from the volcano. And tomorrow we will stop at places 11 kilometers away from the summit crater, so you can get a perspective. Here's Pompeii, 11 kilometers as the crow flies from the volcano. This is Ercolano, another famous site. This is the crater that formed in the year of 79, so you can see the present volcano is much smaller than the one that existed. What you can also see is that the area heavily impacted in the year of 79 is today very densely inhabited. At Popo, it is similar, although not that extreme. This is a typical Plinian pumice fallout deposit. This is a type of deposit we will see tomorrow, and as you can see, it's quite friable. You can scratch it and it will fall apart. And this is the type of deposit from which these casts were obtained. So essentially, when they were excavating down into the pumice, they would find hollow areas in which sometimes was like a gold ring or something that would not rot away. And at one point they discovered that these were not burrows made by animals, but that there was something hidden behind. So some person had the idea of putting gypsum into it, and this is the casts that then came to light. And I'm showing you these two particular ones because they show that these people, before being covered by the pumice, this person died by asphyxiation. put his hands in front of the mouth, and the same the dog. The dog was chained, could not escape, and so they were dead before being covered. And the question is what killed them? And what killed them is a turbulent pyroclastic flow that was extremely hot. So when they inhaled it, they became asphyxiated, and they were only later they became buried. And I'm telling you all of this because these turbulent pyroclastic flows, they produce layers that one can easily oversee. But I will show you tomorrow that at Popo also, at the base of the pumices, at some of these pumices, we can find these pyroclastic surge layers. So a Plinian eruption essentially is one where a column, an eruptive column forms that intrudes into the stratosphere. And the stratosphere is, this layer is not everywhere at the same altitude, but it is important because there the winds are more constant and more prevailing, and if you inject substantial amounts of fine material into the stratosphere, it has a good chance of circulating around the globe. And usually when you look on a clear day into the sky, the highest clouds you will see are much below, and airplanes crossing from one continent to the other will also fly way below. So Plinian columns reach altitudes where we usually don't see any objects. They are really large. They can reach between 40 and 50 kilometers, but most of them reach between 20 and 30 kilometers. What else? Well, and they rise essentially by buoyancy. So this means until their density, the density of this mixture of hot gases and particles, pumice, etc., reaches the density of the nearby atmosphere, and from then on they expand horizontally and mostly in the direction in which the wind is blowing at the moment. Sometimes this is a subplinian one. They have this anvil shape, and this is Mount St. Helens, this is Pinatubo. Here you can see very nicely, this is a Plinian column where the wind is blowing in that direction, that you could almost stand here, but not on the opposite side of the volcano, where most of the material is falling. So the distribution of the material is not radial around the volcano, but it's towards the direction in which the wind is blowing, and tomorrow we will see that too. So this is an example of El Chichon, excuse me, for this dispersal of ash. Underneath, day can turn into night. That's another thing that one should consider. These columns eventually collapse, and then they form pyroclastic flows, which is a mixture, again, of pumice and ash, very hot, and they are gravity driven. They come down the slopes, and essentially they destroy anything they encounter in their path, and they can reach far away from the volcano's cone. This is an example from El Chichon. Here in this circle you can see a church, and this is what remained of this town. You can hardly see the foundations of the church. Yeah, these, even at great distances from a volcano, you can have strong effects from a Plinian eruption. Many, many kilometers away, as these pictures show. And after such an eruption, where a few cubic kilometers of dense rock converted into particles has been deposited around the volcano. If it then rains, this material gets removed, and it essentially gets removed in the form of lahars. And this is like the, this is also, excuse me, this is also at Pinatubo. This is higher up on the mountain. These are these fresh, young deposits, and it just started raining, and you can see these torrential mud flows initiating. When they go down the slope, on the upper slopes they are extremely erosional, and when they come to the break-in slope, to the plains surrounding the volcanoes, they are very depositional. And this is exemplified by this picture. Look at the roofs here. And this does not occur by one lahar, but by sequences of lahars. Whenever it rains, a new lahar is coming down. And these are pictures of one and the same town. It shows always this road. So gradually, these lahars inundate the plain, and the level, the surface level rises within a few years by several meters. And that's exactly the origin of the plain of Puebla. Yeah? After each Plinian eruption, the level has risen suddenly, or in geological terms, very suddenly by a few meters, yes? And well, you can. So this is just to show you that this is the youngest Plinian eruption at Popocatépetl. This is just to show you that the deposit is also several meters thick, just as at Pompeii. This is almost at the same distance as Pompeii, and the thickness is very similar also. This is the same place. This shows at this distance, at the distance of 10 kilometers, the maximum pumice diameter. This is something we usually measure, but it turns out what we measure is usually smaller than what actually came down there. If you imagine a piece of pumice this size, and I drop it here on the concrete floor, it will break into many smaller pieces. The same occurs with dense lithic fragments, not always, but sometimes, like in this case here. These are fragments that come like from the walls of the conduit, and so volcanoes essentially tell us something of what is underneath them also, because they bring these rocks to surface. We will see that tomorrow too. We will learn something about the basement underneath Popocatépetl, what kind of rocks there are 2 or 3 kilometers under our feet. And well, some of these, in total, we have detected at least 7 Plinian eruptions for the last 25,000 years. Some of these we have studied in greater detail, and tomorrow we will have a closer look at deposits from this eruption, which occurred around 14,000 years ago. And that is because the dispersion was here towards Mexico City. So when we drive up from Meca to Paso de Cortés, these are the deposits that prevail on that slope of the volcano. While when driving down from Paso de Cortés, we will mostly see deposits related to these 3 eruptions, the last of which occurred 1,100 years ago. And by the way, these 2 directly impacted human populations that were already living in the vicinity of the volcano. yeah, similar to seismology, there's been an effort to have a scale for the magnitude of eruptions, and they came up with the so-called volcanic explosivity index. And according to this index, Plinian eruptions at Popocatépetl range between 4 and 6, which is pretty, it's not the highest, but it's pretty severe, yeah? And towards the south, we have, but we won't see this, the white pumice. This is at almost 25 kilometers from the volcano. Here you see it's also very thick. These are the isopac and isoplat maps for the white pumice. An isopac map is a map of equal thickness for a certain deposit. And here you see that they have this ellipsoidal shape. Here is the cone. And this is due to the prevailing wind during the eruption, this kind of distribution. And yeah, so this is the kind of work we do. We go out, measure at as many places as possible to come up with these types of maps. And from these, we then can compute height of the, not only the volume and the distribution, but also height of the column and other parameters. These are the deposits of the Tutti Frutti Plinian eruption. We call it Tutti Frutti because the pumice is full of all kinds of xenoliths, fragments of foreign rock that come from the basement. This is a very complex eruption. This is the one that also where the deposits, the wind was blowing towards Mexico City, and where we can find, if you go downtown and make an excavation, you can find a thickness of 10 centimeters. Yeah, this is the isopac map for this eruption. You see here is Ameca. We will be there tomorrow. This is Mexico City. This is the 10 centimeter, 15 centimeter isopacs. This eruption originated from this crater, not from the summit crater. Yeah, here's this deposit. By the way, farther, this is the Tutti Frutti, 10 centimeters. This is in the Colonia Condesa, so a few kilometers north from here. And by the way, there is also the Upper Toluca pumice, which is this here, and that we measured 125 centimeters. So this is 125 centimeters of a Plinian eruption that occurred at a volcano that we cannot even see from here. This is to give you an idea about for those of you that are not geologists or volcanologists, what a Plinian eruption essentially means, yeah, in practical terms. Well, yeah, this is the Valley of Puebla, where if near Toluca you start digging, you find the pumice. These are the pumices from the last two Plinian eruptions, and you always find pottery underneath each of them. This is a small village. Tetimpa, here you can see more than a meter of Plinian fallout pumice. This was produced around 2,000 years ago. These are the isopacs for the last three Plinian eruptions. So here's Paso de Cortez. We will be there tomorrow, and then we will drive down. So we will see deposits related to the one that we call the ochre pumice, which is 5,000 years old. And then we will see deposits related to this yellow one, which is the 2,000-year-old pumice. And then we will see deposits related to the pink pumice, which is the youngest. And this essentially, you see, there are three of these. That's because we had 3 times after the other columns rising, and while this was occurring, the wind shifted from the northeast towards the east. And now imagine pumice falling on a slope like this, and then later precipitation, rain, etc. It will all go downhill, and it will go in this direction. This is the valley of Puebla, and this is actually what occurred after each of these eruptions. So all this area was inundated by lahars, and if you make a deep trench there of 10 or 20 meters, as they do when they do construction, by building bridges or I don't know what, you see these thick sequences of lahars interrupted by paleosols, and each of these lahar sequences corresponds to one of these primary Plinian sequences at the volcano. So here, this is again, so this is this laharic plain, and you can see here from Ixta, so Popo erupts, but from Ixta also lahars come down, not only from Popo, also from Ixta. And you see these drainages coming down there. They are completely insufficient to carry all this load. They were cut down by normal rain, and they usually conduct the amount of the usual precipitation, but if you add all of this loose material, the volume increases significantly, and these channels are not enough to keep them in, and that's why they overflow and inundate such vast areas. And that's what they look like, and in some cases they are quite coarse. You can still recognize the pumice. Pumice gets rounded very quickly due to friction when it flows. Yes, I'm almost done. And inside, it is possible to find frequently remains from human occupation, but many of these are more fine-grained. If we have enough time, we will visit the largest pyramid on Earth by volume, not by size, which is Cholula. And at the base of Cholula, you find these lahar sequences. This particular one, we dated at 1,150 years. So this is a little bit to exemplify these lahar inundation effects. So they wanted to protect the bridge. No need for that. This is a few weeks later. This is months later. The lahars did not take away the bridge. They just buried it. Yes. So this is the Plinian eruptions at Popo in comparison. This is the white pumice. This is the tutti frutti pumice. These are the isopacks, the 10 centimeter isopacks. This is the ochre pumice. So you can see these already reflect the differences in magnitude. So this is about magnitude 4, and this one is about magnitude 6, and this is in between. So if you compare this with the ones that have occurred at Vesuvius, they are not identical. They show some significant differences, but fundamentally they are of the same magnitude. So it is amply justified to call them Plinian. Yeah, here's some data in terms of volume, etc. So if we compare these with other large magnitude eruptions that have occurred during the Holocene or even more recent times, we see they are not comparable to this one, for example. But yes, these eruptions are still worth taking note of, and that is the main reason why we should keep putting an eye on Popocatépetl. That's why there is the hazard map. And last but not least, Popocatépetl is not the only Plinian volcano in the area. There are plenty more. These arrows depict dispersal axis of Plinian eruptions that have been detected and studied for the last 35,000 years. There's one that is of considerable magnitude. This is Ilopango caldera. It is totally understudied. It certainly destroyed a large area around the year 500 of our time, so when Mayas were already highly developed. And I know a few colleagues of mine that are studying it, and we will certainly know more about this in a few years. So thank you for your patience, and yeah, see you tomorrow. Before we leave, I know we are all tired, but a few practical issues. Paso de Cortés is at 3,500 meters. It can be kind of chilly up there, but if the weather is like today, at midday, when the sun is strong, it might also be quite warm. So the strategy is, yes, bring different layers so that you can feel comfortable at any time. And at 3,500 meters, and if the sun is bright, for those that have not the appropriate skin, help yourselves with something to put on. Otherwise, I've seen some that when they have their glasses on, they discover later at night that they have a face like a panda bear. Yeah. So yeah, take your precautions. We are not gonna do rock climbing or anything like that, so your sneakers are just fine, but don't bring sandals. I would pumice in your shoes is not nice, but you don't have to. We are not gonna do mountain climbing. That's what I want to say. Yeah. But bring appropriate shoes for. And yeah, we see each other at 7 o'clock in front of your hotel, I understand. Is that correct, at 7? Seven, correct? Yours. Panelistas, los invito de la manera más amable.
Our last activity inside the auditorium. We have tomorrow our excursion still. So we have this round table, and I don't have to introduce of the panelists because they all spoke before, so we know them by now. And the name of the round table is Time Machine, German-Mexican Scientific Networks Then and Today. And that can mean different things for anybody. So I just wrote 4 points that I want to ask the panelists their opinion, but they can talk about something else if they want. I want this to be very informal, open, and also I expect some participations from the people here in the auditorium. So I will give 4 minutes to each panelist, then 10 minutes back to the people, and then we come back with 2 minutes for responses or comments, okay? I'm gonna use my clock to control, my telephone to control the time, and I will say time when you finish your 4 minutes. So the first one is define networking, because maybe, I don't know if we all understand the same thing about this concept. The next one is networking in the best interest of science, or it is to fulfill some personal interest. Can you really trust all of your peers? And I say that for personal experience, not always this interchange of communication is really worth. And the last one is to comment about positive and negative impacts of technology for networking. So we are not going ladies first, but Klaus first.
Of course not. I mean, it's very simple. Can I trust all of my neighbors? No. Some of them I do, some I don't. but I'm not going to come up with examples, isn't it? I don't know who came up with this questions, but this is an easy one, and now it's your turn.
Okay. Is networking in the best interest of science or to fulfill personal interests? You don't have to go in order. You can talk about any of those. Like go through all and give
Pick the one you like.
define networking. Okay. It's the ability or possibility to create relations and relationships. Like I would define relations as the linkage between knowledge or techniques or experiences, and relationship as the linkage between people.
I think I will talk about is networking in the best interest of science or to fulfill my personal interests. I think it is both, of course. I do network mostly, I mean, depends, like different kinds of networking also, I would say. So that relates to the question number one. We are doing, of course, a kind of networking here, which is probably not going to relate to my work, of which I haven't talked here at all. So there are different kinds of networking. I would like to talk about the scientific networking that I do, because that, of course, fulfills my personal research interests, and does also, ideally, is in the interest of science that all persons who work on the same or similar topics than I do talk with each other. But sadly enough, I have to say that happens very seldom, because not everybody is trusting. That relates to question number 3. And we do have sometimes incidents of people copying or people stating that someone stole ideas. But I personally keep trusting, because I think that's the way how we can only exchange. If we don't trust, even if we have bad experiences, we cannot really share. And if you don't really share, there is no common going ahead in science. Yeah, and I think now I have talked about 3 points and 3 minutes at least, so I give ahead.
Okay, I take number 4, positive and negative impacts of technology for networks. So from the point of view of a geologist, networks are sometimes very advantageous. For instance, when I want to know when which volcano has erupted, I only have to look at a lot of different networks, but I will get information which is very useful for this purpose. But there are also other networks. For instance, every scientific analysis gives a number. For instance, age dating, for instance, chemical investigations, chemical determinations of elements, concentrations. And then, if I use uncritically these networks, especially the example I told you in the morning about age dating, then I run in problems, because honestly you have to look at every data. How was it obtained? Is it really valid that I can use it? And this is a lot of work. And in this case, networks are complicating my life, because I have to see what is the quality of this data.
Okay, just to make it very... Well, I agree, networking is kind of a complement of the scientific or research activities, and it is the way to get really in touch with the actors that produce knowledge, that generate new ideas. And it certainly depends on luck. I think I'm very lucky, because I have been connected in different in my own experience, I never could interact with some other colleagues if not because of the recommendation of someone else. And so, in my sabbatical, I was able to know or to meet Keiti Aki, who in turn introduced me to Kojiro Rikura, who invited me to Japan. And so in such a way that I was just habitué of the University of Kyoto. And so, and then network implies a lot of patience, because understanding different positions, attitudes. And it happens that I inherit the students of my colleagues. When they retire, I continue interaction with the students of my colleagues. That's interestingly how networking works in time. I think it's in the best interest of science and research, and also it is not conflict because this fulfills my personal interest, and I trust my peers. I share data. All my programs are distributed freely. I never mistrust on colleagues. Sometimes I get disappointment, but I think it's not, this didn't mark me a lot. I don't worry about copying or that they copy my ideas. I think I distribute the things I do freely without any restriction. Maybe it's not good. Maybe it's not good to make money, but positive impacts of technology. I think technology is quite an advantage to get communication. Actually, maybe it's a kind of plague. Everything is very fast, too fast that we don't have a chance to think.
I would like to add something.
Can we? Yeah.
Yeah, I mean, I think this with the networking, that's actually it seems a trivial question. It is inherent to our species, networking on all levels, including gossip. I mean, we wouldn't survive without it. So it is establishing a scientific network is only one of the many networks, and it is fundamental for advancing science, as it is also in political terms. I mean, there's no politics without networking. Yeah, in this sense, I want to thank the Humboldt Foundation for contributing to a network, and also Alejandra for having organized this and giving me the opportunity of knowing more of my peers, and hopefully others will join. I think that was probably maybe the intention of this question, right? Yeah.
Well, I also wanted to go back to the foundation, because one of the greatest experience I had as I was in Germany was, of course, the archives and all the things I could do and all the support. But for the first time in my academic life, I had the chance to be with people who weren't part of my discipline. So in this German trip, for example, I met all the people that were also studying and with a fellowship, and that were chemicals or physicians or volcanologists. I met Alejandra there. And we did this Stammtisch, so we met once a month in Berlin to talk. And it was great, not just because I was meeting people, I already had a lot of friends in Berlin, but because we were talking about our research with people with whom we were sharing not the subject, but the experience of being researchers. And that was great. And actually, now I believe that this experience really gave me the possibility of having the network from all these colleagues that are also my friends now, that live and work in different parts of the world, and with whom I'm in touch, and we organize things. And I think my experience as a researcher grew in this personal way, also in the professional also, but also in the personal way.
Well, I cannot add to the experience of networking in a time when I was a Theodor Lynn fellow here, because there were no other fellows. I was alone. That happens more of people going with a Alexander Foundation out of Germany than in, that you are also more united. But I do have to stress that I also like that about the idea, not only with the Humboldt Foundation, but in general, like exchanging ideas with researchers from other areas. Of course, I didn't get a lot of many of the talks in this colleague, which is probably normal, but you take tiny pieces of information, and you know, if you want to ask someone, you know whom to ask, and it just broadens also the perspective. And what I want to say is, in a time when we're getting more and more specialized in the areas of science, what we need also are scientists that get more general. That, of course, it is impossible to grasp all the knowledge that is going on in the specialities. But we have so many problems that we now have to face as humankind in the world. And I think that we have to work over the specialities more together. And for that, we need the people who are like more or less overlooking what is happening. And I think that is one of the things that universities and academia should teach, like more generalized people, and not so much only the specialists. And that ties back to Humboldt. In general, the networking ties back to Humboldt. He would never have been able to write the Cosmos without the knowledge that he got from all the people he talked to outside of the specialities. And it ties also to today. If we want to solve the problems, we have to work together, and that means we have to learn to talk with each other, and in a way that we can understand each other, meaning, like Humboldt, not to use too much jargon. And that would be maybe my idea for future Humboldt colleague is, how can we do that? I mean, how can we develop a better kind of working trans or interdisciplinary to be able to solve future problems? Because we're talking a lot about climate is destroyed, but we still don't talk about the solutions, for example, and that is just one of the problems we're facing.
Well, networking is also a generation problem. When I see the young students, they are pretty much faster than in using network data than I'm now 67. I think I will not learn it in that way. The young guys are doing it now. But any information, of course, is also, Paco is even older, huh? Any information, of course, is we are going with the time, but we are not so rapid. So there are network using groups which are pretty fast, and there are other groups which are pretty slow, like we. Huh?
Yeah, so you just released the information that I am a little bit older than you. But I actually, earlier this week, I was thinking about the decision of starting using Facebook. Because so far, I never used that, neither. And even I have some friends that, you know, our friend Dante Moran, use Facebook. And yes, another network is networking, social networks. But I have to learn, I have to get some information. I am about to get all the information because I'm afraid of that. But anyway, I think, so networking, science, all the examples of the attitude toward information, of measuring the world by Humboldt, may be kind of inspiring to understand and solve the problems we have as a species. So we are risking many things, and we apparently we don't learn easily, and then this is a problem for all us to solve all the problems. For instance, the Sustainable Development Goals of the United Nations. Today I bring this pin. Seems that nobody cares. So also there are groups that are working for it, because it is it sounds very obvious that I think networking, advance of science, you know, communication, we have to be very original, because there are problems that can harm our species, the very existence of our species. And this is, I think, the communication and to find solution is actually the challenge we have. I think the example of Humboldt is, I am reading Kellman's book, not finished yet, but another some writings by Humboldt, and it amazed me how, in the worst of circumstances, he measured the things, the pressure of the air near the top of the Chimborazo, even if there is a storm, and risking his life is measuring the boiling point of water. So Bonpland is complaining about this. It's crazy, is it? Actually, but I was reading about Humboldt. I wonder about the motivations, and actually he was very conservative. I've always repressed Bonpland for his dissipations, and apparently I don't know if you know about Humboldt, who was as a human being. This is my question. I have a doubt. I maybe have to read more. I changed subject, of course.
Peter, you said you wanted to comment something about Wilhelm. I don't know if you want to do that still.
I didn't get you.
You said to me before you wanted to talk about Humboldt's brother, Wilhelm. You still want to do that?
Well, I was wondering that the KOLLEG is very focused on Alexander von Humboldt. In Germany, his brother Wilhelm, 2 years older, died earlier, but he was very important in human sciences, and he was the founder of the Berlin University, which later called Humboldt University. I think both brothers, they grow up in a very wealthy family with private teachers and so on. They contributed a lot. Humboldt in natural sciences, Alexander von Humboldt in natural sciences, and Wilhelm von Humboldt in social sciences and humanism. So I wonder a little bit that the Humboldt Foundation, at least here in America, is very focused on Alexander von Humboldt, while in Germany, I would not say that Wilhelm is more cited or more mentioned, but a lot more than here. This is one of my observations, and maybe there is something who can explain it, why this is so in Mexico.
It's very simple, Peter. The foundation is named after Alexander, and his birthday was recently, so his birthday is being celebrated. I think that's the only reason.
No, but I think many people in Mexico work about Wilhelm von Humboldt, but it's more in the humanity context, you know? Like people studying language and philosophy of language. There's a lot of people working on Wilhelm also.
Well, one of the problems might be that there is no translation of Wilhelm von Humboldt into Spanish. So it is rather, very little. So coming back to the point that I made before about the Mexican grammar, we're currently making a choice of the work of Wilhelm von Humboldt to translate it and to publish it in Spanish. So maybe that helps that more people here could read about, easily at least, about Wilhelm.
Well, there's also a cultural issue. Wilhelm was Lutheran. He transformed the German educational system, and this country is Catholic and didn't want to know anything about Lutherans. So a natural scientist that actually came here is obviously more revert. I mean, there's no major mystery behind all of this, I think.
But probably there are no patterns, because I think one of the main reasons that Alexander von Humboldt have been more published is because of the efforts of Jaime Labastida, the president of Siglo XXI, who is passionate about Alexander's work. Yeah, but more Alexander's. Yeah, But like all the work he's done to publish Alexander von Humboldt, it's in a big part his effort.
Okay, now I would like to give the opportunity here to, yeah, I want to know who wants to, Alicia, you wanted to say something?
I was concerned about the very spontaneous answer of Klaus about the trusting of the peers, and I think he was spontaneous and right? So the other answers can be political correct. You are not. So no, I noticed that now. So. Well, it's just have to see how have been developing the science and the economy in the two continents. And so the Latin American part have been trusting a lot the European part, but it's not the opposite. When Alexander von Humboldt gathered all this information, he was very good in networking in Europe, but what's happening with the people in America? So there is a lot of information that he got that took it into Europe, but was not in the opposite direction. So the interests were very different. No? So and I think also that one of the reasons why Alexander von Humboldt is very important in Mexico is because he was Mexican, right, by nationality. He got the nationality from the New Spain.
Somebody else? Don't be political. Say what you think.
No, I want to.
You want to say?
He was called Benemérito de la Nación. He got some official title.
Yes, he did.
Yes, I know. So I can't remember, but it was a very pompous title that you wouldn't give anybody. So a very distinct. Kind of I think it was like Benemérito de no sé qué cosa. Yeah. Something that you would really, only a very few people would get this kind of distinction. And he got this while being here.
And it was the only colony that gives this kind of distinction.
Exactly.
Other comments, opinions, please? Yeah.
It's more of a question and also maybe part of the discussion. How would you use your networkings to minimize the gap between sciences and humanities? Because maybe that gap that we have today is part of the reason why we put more attention to Alexander than his brother. So how would you use your networkings to minimize that gap and starting to working some solutions like you were saying?
They are still thinking. I think the Alexander von Humboldt Foundation is actually a good answer to it, and other organizations like the DAD as well, that all alumni and current scholars work together, come together more often under maybe smaller workshop themes to talk about it, maybe in a less presentive way, that we don't give talks on our topics, but that we have like issues we are talking about and come with the solutions from each of our areas without talking in our expertise areas. I mean, of course, I have it now easy because I haven't been talking in my expertise area for a year now. Alexander von Humboldt is not my expertise. So I got already a kind of schooling of talking about things which I don't feel like totally comfortable talking about. It is also a learning process to talk about things academically which are not your own research area. But I think that is what we have to do, and we have to come from the knowledge that we have together and share on the areas where we coincide to solve problems.
Yeah, I can give you an example. There are thousands of examples, but one, like a volcanologist, eruptions, if I would only focus on, I don't know, the density of magma or something, and would be cooking my own soup, I would not get very far. Because eruptions occur in a political environment, social and political environment. So if you want to really have some impact in terms, for example, of civil protection and how to evacuate people, you cannot rely on your small little doings in the laboratory or I don't know what. You have then, by necessity, to broaden your horizon and be aware of all the others that participate in this and their specialties. I mean, it's just a necessity.
Other questions, comments?
Well, I was thinking actually in like to break this gap, it's very complicated because there is a reality. Most of the budget of states and universities go to hard sciences. Like humanities, we are always the smallest amount of, we get the less money, we are less people, and the questions we try to investigate sometimes seem less immediate or less mediatic, maybe, I don't know. And I don't know, that's a question we could answer from the academic perspective. It's a political question.
Well, even before, most of the scholarships goes to humanities. I was surprised when I learned that.
In Germany, it's the other way around.
In Germany, but I was surprised.
Well, the new government is something that we're still looking at. We don't know what's going to happen, but like the projects for humanities are very pointed to certain areas, and it's very hard, even if you, like, most of the projects are for indigenous people, and I haven't been able to even think about one of these projects because they're so limited and blocked in so many aspects that it's almost impossible to go for them.
And I think you cannot count the quantity because the projects, human science projects, are really cheap. So it might
No,
be
I
that
just mean
100
the
projects in
graduate
human
program scholarships, the amount of money the students receive is the same. So more goes to humanities than to natural science. I was surprised to learn that. I thought it was the other way around, but no.
But maybe there are just more students in the humanities.
Still.
I mean, the thing is,
Yeah.
there are few people in mathematics.
Yeah.
That has always been like that.
My wife just said, "Oh my." And she knows me better than I know myself. Just one statistic from the ERC, which claims to be world-renowned. They roughly break it down 40-40-20 between life sciences, physical sciences, and humanities and social sciences combined. So roughly 20% of the budget of that, and I think roughly 20% of the budget of the DFG, total budget, I think, because I think that's how Vinegar built the ERC, is for social sciences and humanities. I just wanted to Lanze brechen. How do you say that in English? I want to speak up for, I want to take Alexander von Humboldt and use him for something. I think he's a beautiful example of somebody who was able to move enormous frontiers with bottom-up research. He had been trained, I'm sure, to do a lot of state priorities in terms of his mining inspection and so on. But he ended up being really the opposite of that, somebody who knew no boundaries as to what he was allowed to or should be looking at. And he just drove ahead with all of his energy, I think, without ever questioning whether he should prioritize it politically or to satisfy his hosts. Maybe there are data which refute that. It would be very interesting to know. It would be an interesting subject to perhaps inquire into as to whether he felt that he had to do certain kind of research for other people's definitions of priorities or not. Because I think today there's a huge amount of research which is for other people's priorities and where we are more or less the executors of other people's research priorities. But losing that fraction of the research budget or the research initiative or enthusiasm, which is completely bottom up, simply because it's the thing we want to do most,
that's probably a very dangerous thing. And the thing that we want to do most, and that we prioritize individually as scientists most, is undoubtedly the thing that we will do best. And we need to do the best. Anything else is a waste of money.
Well, he was lucky enough to be what we call independently wealthy. Yes, and he made wise, in my opinion, very wise use of his money. He lived long, I think more than 80 years, and at the end, he didn't have much left. And he invested it continuously in his science, in his interests, and his publications. He spent an enormous amount of money in them. He translated his own books. He made sure that they would become translated in at least another 2 languages. The lithographies were all made by the top artists of his time. Even the bindings of the books were of utmost quality. And so he could do that because he had this inherited wealth. And that's something I've always dreamed of. So I would send all the administrators to hell. But yeah, it used to happen at least. Maybe it still happens, but I don't know any colleague that is in that lucky situation.
What I always stress in at least one sentence, part sentences, he was never part of a university. So he did everything outside. I would believe if he would live today and he would have his ideas, he would not be funded by anybody, even not by the Humboldt Foundation. I think thinkers like him, they just go quer to everything and they don't fit. And with him it was just a happy coincidence that he managed to leave such a bound of work that we even recognize today. But what we do now, especially in the last year, is that we use him very much politically. And what angers me in this very much is that especially the universities claim him, who have never founded him and would never found him, and or fund him, that's what I meant. And I think what we should go back to is especially fund this kind of work, because we never know. We had one of this in Berlin, one of this talks by the Humboldt Foundation also about peak in the sky research or blue in the sky research, I don't remember exactly, about the necessity of doing the groundwork of that is not related exactly to the research interests of somebody, because we never know where it leads to. And that is what we lost. The research in the academia is, at least in the human sciences, so orientated to waves of what is fashionable and where you can get a quotation index, that someone who's like, let's say, working on the Reformation in Strasbourg in the 16th century, he will never get a quotation index, but that doesn't mean that his work is bad. We have to also rethink the way how we qualify work, a scientific work, because a citation index in the humanities cannot be it, especially not because usually it's the English-speaking word that is cited, no? There are so many things that we have to rethink in general that, yeah, I think the Humboldt Foundation, once again, could be the place to start thinking about how to get context and reasonable and reason back into the scientific landscape.
Beforehand, my English is really bad, so I'm sorry if something you say can't say it right. But last year I went to a conference where an investigator was reading mercury in a river, and he found high levels of mercury in the river, in the atmosphere, in the soil, and in the food that people were eating. So I asked him, since the
since the levels of mercury were so high, what kind of disease were the people experiencing? And he said, I don't know. A medical investigation should be conducted to know that. And then I thought, what if medical research does not trust his results and try to make them again, and by the time they get the results, they don't have any money. And meanwhile, the people are getting more and more ill, and the loan is not doing anything. My question was about networking. The Dr. Klaus said that he has to make use of a networking, but I think that so far the networking is still very narrow. In science, the networking goes as far as volcanology in that case, or goes as far as geology, but doesn't reach medical science, doesn't reach loans. So what is stopping science from reaching this point in which a community can actually understand what's happening and can do something about it?
One part of your question is can be answered in this way, that networking is also causing conflicts. So in your case, when you mentioned the contamination, there are, of course, some parties which will not know this, and they would like to ignore this network information. And the other part which is affected maybe has not so much political impact to push their claims through. Yeah? This is maybe this has nothing to do with the basis of networking, but the use of networking.
But in this exact problem, there's a third part who knows about the problem, and because of economic, how would you say, interest, yeah, would not say, I would do everything to block the researcher that found that there was a high level of mercury. So we are going back again to politics. And I think what's happening to science is that for some reason, and science, humanities, and everybody in the university and the research system, we lost our capacity to communicate with politics in the same level. There are so many interests. We're in a network, we're lost, and we also are like pressured by all these things you were mentioning. No, we're asked for results and points and quotations and all these things. So we're like responding to different interests. Our own interest in our subject, but also political pressure, economic interests, and so on.
I just wanted to make a quick comment about blue skies research, or as I would like to characterize it for now, curiosity-driven research. I think all of us here who presented over the last 2 days would feel that our research is being driven by curiosity. You know, we're doing things because we're interested in it. As Don says, the stuff that you're interested in, the stuff that really excites you is the stuff that you do well. I think probably of all the people who presented, my research is probably the least applicable to anything of use for society. So mea culpa, my apologies for that. But whatever we do, when we do curiosity-driven research, it is absolutely incumbent on us to find those aspects that we can apply it to. So I was very pleased for your question at the end of my talk about low pressure stuff. You know, I'm really very surprised that nobody's looked at anisotropic diffusion creep before, and it is a fundamental solution for this problem of failure of printed circuit boards. You know, many of my colleagues would not have gone to look for these applications, but it is incumbent on us if we want to protect curiosity-driven research, it is incumbent on us to then also apply the results of our research. So it's not applied research, but it is applications from our research that we we have a responsibility to our funders and to society to actually then make those applications.
Well, I want to say something about the application and the relation with the science or research area and the society or the politics. Well, one point is that I think we know about the problems and some of the groups, for example, in the case I am in Natural Resources Department, and we are in groundwater research group. And we know, for example, we can give sometimes solutions for example, now we are working in the basin of Mexico, and there is some part in Mexico that the water is really, really very bad. But it is one of the main problems is that the people who have the money and can help the solution doesn't have the knowledge. Not the knowledge the knowledge in the sense they don't know anything about science, about application, about chemistry, about isotopes, about volcanology. They don't know, and they don't care. So I think in the Geophysical Institute, we have a link with different areas. And we have, for example, in my department, we are related directly with the water, and the water have a lot of problems. But we try to solve, and we work every year, every time, in different projects, and try to solve problems and recognize, but we are not going to solve directly the problems. We need the politic solution, and there is money for that. Even the different institutions or different international, like United Nations, like International Atomic Energy Agency, European Community, have foundations for research. So one of the things I understand is the people, the most of the research people, first, you should ask for the money. You should know what do you want and what do you want to solve. And well, this is a problem, and I don't know if you understand me, but I think there are ways to do the things. And of course, we need a link, a network to solve, to propose solutions for the problems. And well, one of the things different like this I want to say is about Humboldt. Dante Moran is a very, very important people in geology, and he's working in a book about the history of the geology, asking for the National Science Foundation and is the Geological Society of America. And he talked in one of the presentation I was, that Humboldt was, I don't know if somebody knows how many times he was in Mexico, but he said he was some kind of racist, because he says that he never want to come back to Mexico. And I don't know how many times he was here. But the other thing is that they say he take a lot of information from Latin America, but they don't give the information to people in Latin America.